Hello. Hi, everybody. Can you hear me? We're live on the new stream?
We are live on the new stream. Take it away, Becca Jackson.
Okay, awesome. Well, thank you, Margaret, and thank you so much to all the organizers of this amazing event. It's really inspiring, and we're here in the 51st hour, 49 more hours to go. I'm Becca Jackson. I'm an oceanographer at Tufts University. I study the ocean, particularly the ocean where it meets and comes into contact with ice, around glaciers and icebergs in the polar regions. I'll actually be talking about this work on Sunday morning at 8:30 in the morning for any of you early risers. But most importantly, I'm here as the host for this segment where we've got a great lineup of talks. And I'll just start with just a quick disclaimer that all of our speakers are appearing, in their personal capacities, not representing their universities or employers, and expressing their own views, so not necessarily representing other participants. And I'm just really briefly reminding that we're here to raise public awareness about the importance of weather and climate research. I'll just jump right, since we're running a little bit behind, I'll just jump to mentioning that I encourage you to reach out to your representatives to convey the importance of this weather and climate research for the greater good. You can look at this link streaming at the bottom of your page and call your representatives. But without further delay, I want to introduce our first speaker of this next segment. Dr. Uma Bhatt is a professor of atmospheric sciences at University of Alaska Fairbanks. And she'll be talking about actionable climate science in Alaska and how it relies on collaboration across many groups. So hopefully, I'm getting a little word that we're a little behind on her coming in. So I could have actually slowed down. I'm hearing that she's just about on. Okay. Hi, Uma. So I just briefly introduced you, say that you're a professor of atmospheric sciences at University of Alaska Fairbanks. We're really excited to have you here today talking.
Sorry, I forgot to click that last button. Thank you very much, Becca. I want to begin by thanking the organizers of this event, which really comes at a critical moment in U.S. history to support science. Today, I'll share my story of conducting climate variability research in Alaska, work shaped by close collaboration with and inspiration from the people who use this information. And much of what I'll focus on is developing seasonal fire weather outlooks, and I'm speaking to you from Troth Yada, the unceded ancestral homelands of the lower Tanana Dene people, where the University of Alaska Fairbanks is located. And wildfires are part of life near Fairbanks. And in these photos, last summer we had the McDonald fire. It flared up just south of the city. And it was a stark reminder of how quickly conditions can shift. Smoke from the fire led to periods of unhealthy air quality in Fairbanks and the nearby town of North Pole. And since the record-breaking 2004 fire season, when 6.5 million acres burnt, which is the size of Massachusetts, we've learned a lot about the dangers of wildfire smoke, particularly PM 2.5, the fine particles that pose serious health risks, not just to vulnerable groups, but to everyone. And so installing air filters in homes and public buildings is now common, whereas in 2004, we stayed outside in hazardous air. We wouldn't do that today. And it's really through science that we've gained this knowledge, and through science that we've changed how we live. And our paths as scientists are often shaped by lived experience. In the early 80s, I planned to study solar energy in graduate school, but before continuing, I joined the Peace Corps in Kenya and taught from 1983 to 85, during which there was a major El Nino drought in East Africa. And this drought led to real consequences for my students, many of whom were from farming families, and they had to pay school fees to go to high school. So seeing firsthand how climate affects livelihoods inspired me to pivot towards studying climate variability, first in the tropics and then in the mid-latitudes. And eventually I came to the University of Alaska Fairbanks, where I focused on high-latitude climate. And it's really only in the past decade that I've had the chance to pursue research that's directly co-produced with and shaped by those who use this information. Alaska has warmed significantly. Are my slides not going forward?
We're still seeing your title slide. Yeah.
I am not sure.
Oh, now it's going. Now it just advanced. So now we see wildfire in Alaska.
It's not on the right slide.
Hi, Uma. Just say next slide or something, and we can do it for you.
Okay, I should be back as another slide. This went, yeah. Yes. Okay, little technical difficulty. Most of the warming has occurred from September through May, and in Fairbanks, for example, the number of days below 40 has dropped by 69% since 1930. This warming is tied to sea ice loss. Next slide. Click. Next click. And while summers have warmed also, the change has been less dramatic. Precipitation is also increasing, though trends vary by region and season. These shifts are affecting many parts of Alaska's environment. One immediately is the wildfire. And now we're on the right slide. So since 2000, we've had 13 large wildfire seasons, each burning more than 1 million acres. That's nearly double the number recorded between 1955 and 1990, when only 7 such seasons occurred. As climate scientists, we aim to understand these trends and develop seasonal outlooks to help anticipate the fire weather and lightning-driven ignitions. Next slide. Most wildfires in Alaska occur in boreal forest, though tundra fires are becoming more frequent. And these fires differ from those in western US because the fuels are unique. In Alaska, the main burnable fuels lie in the ground in the duff layers of live moss and dead accumulated organic matter, which can sustain deep burning fires when dry. Because of these fuel characteristics, Alaska fire managers use Canadian Fire Forest Danger Rating System, which is better suited to boreal conditions than the system used in the lower 48. Next slide. From the start, we engaged directly with fire meteorologists from Alaska's fire management agencies. And this collaboration was made possible by the Alaska Fire Science Consortium, a boundary organization based at our university that connects researchers with fire managers. And their role really was essential in ensuring that our work is grounded in operational needs. Early conversations with the fire managers revealed that they needed outlooks in March to support the upcoming fire season in June and July, which is a pretty severe ask of seasonal forecasting. And to meet this demand, we taken a two-pronged approach. First, we use seasonal forecasts from 3 global dynamical models to generate outlooks of the Canadian fire weather indices, which are standardly used in Alaska by management to assess the risk. But because these models often struggle over Alaska's complex terrain, we also conduct diagnostic studies of climate variability. And these studies focus on identifying large-scale climate patterns that influence fire-relevant conditions, such as snowmelt timing, summer rainfall, seasonal temperatures, and lightning activity. And I'll share a few key results from the work next. Next slide. The plot on the left shows daily accumulated acres burnt during each of Alaska's recent large fire years. What stands out is how different extreme fire seasons can unfold. In 2004, shown in light blue, the burning extended well into the cool season. In contrast, 2015, Alaska's second largest fire year, shown in green, intense burnings started early in the core season and ended abruptly with the arrival of the rains in July. And these varied seasonal trajectories suggest that large-scale climate drivers differ from year to year. And by analyzing fire seasons alongside a range of teleconnection indices, we begin to identify kind of the climate indicators that could inform statistical forecast models. And for example, on the right, the East Pacific, North Pacific pattern, EPNP index for May through July, is positively correlated with Alaska's air temperature. And the scatter plot on the right shows that roughly half of the high fire years occurred during the positive phase. But what's interesting is that the strongest positive years were especially likely to coincide with major fire years. So similar signals appear with many other climate indices, reinforcing the potential for advanced statistical approaches to improving seasonal fire predictability. Next slide, please. Conventional wisdom in Alaska has long held that the snowpack and snow-off timing don't really influence the fire season. And that's because our snow tends to have really low water content and soils can dry out quickly from not having rain for even a week. But we wanted to test this assumption with data. And the plot on the right shows the relationship between snow-off timing and fire activity. Colors indicated red, the red bar shows early snow off, gray average snow off, and blue late snow off. And it shows the percentage of acres burnt between 1959 and 2020. And what we found is that the influence of snow off varies by region. On the North Slope and in South Central Alaska, over 80% of the burnt area occurs in the early snow off years. So that's the blue and the green lines. And in Eastern and Western Interior, about 60% of the area burnt is also tied to early snow off. Whereas in Southwestern Alaska along the coast, the relationship's weaker, with about 40% occurring during early snow-off years. So while snow-off timing isn't a perfect predictor, it clearly matters, especially in some regions and in some years. And it really deserves a place in our seasonal fire potential toolkit. Next slide. Next, we turn to the question, can large-scale climate patterns help us develop seasonal outlooks for lightning? Lightning occurrence in Alaska has a really strong spatial gradient, with most strikes occurring in the eastern boreal region, shown in deeper red colors. Because lightning is such a localized and episodic phenomenon, we need to explore it in the context of broader weather patterns embedded within the climate system. And to do this, we use tools like self-organized maps, which I'll spare you the details of today. What I will show you on the top right is a composite of sea level pressure and 500 hectopascal heights anomalies for days leading up to and including high lightning activity. And these patterns really help us understand the typical large-scale setup that precedes lightning outbreaks. And now in the lower right, you see a time series in bars of observed high lightning days. And it's compared with dots that are predicted values that are derived from how often these weather patterns occur in June and July. So based on a diagnostic observational study, the prediction aligns reasonably well with observations. So this suggests that if we can skillfully forecast seasonal distribution of upper heightened surface pressure patterns, we might be able to develop useful lightning outlooks, which is really key for anticipating fire activity. Next slide. Now we turn to forecasting buildup index, a key component of the Canadian Fire Weather Index system, calculated from standard meteorological variables.
I'm going to just sorry to interrupt quickly, but there was a little sound interference. I don't know. Do you maybe have your hand near the mic, or is it possible?
It's possible my paper is close to it. Sorry.
Oh, it might be that. Okay.
I will move
Thanks.
it.
Sorry to interrupt.
No, thank you. So our graduate student, Cecilia Boris-Striegel, developed BUI outlooks using dynamical seasonal forecasts initialized in early March. For 5 years running, she presented them at Alaska Spring Fire Management meetings. So it's really, putting your feet to the fire by showing these to managers. And after her fourth presentation, one of the managers said, "Oh, I finally understand what you mean by an ensemble." And that really highlights the value of sustained engagement. It took a while for that to be communicated. And forecast skill during the peak of the fire season, the duff season, was modest, with getting the right answer about 20 to 40% of the time. And the wind and the drought seasons had the highest skill. And while these forecasts used only minimal post-processing, they really enabled a thorough evaluation of how well dynamical forecasts perform in Alaska. And at present, statistical models tend to outperform dynamical ones, particularly at higher latitudes. The gap is narrowing as modeling systems improve. And we also observed that forecast skill varies a lot from year to year. And our current research is focused on understanding that variability and how it might be used to improve forecast outlooks. Next slide. While most of our work is focused on the buildup index, the fire managers asked us to take a closer look at the initial spread index, an understudied but operationally important fire danger metric, fire spread metric. Our graduate student, Jacob Coffey, analyzed ISI's climatology, seasonality, extremes, and trends. And ISI is influenced by temperature, precipitation, and particularly wind. When winds are strong and rain is absent, ISI values spike, really signaling high fire spread risk. And that's why fire meteorologists monitor it closely throughout the season. Seasonal ISI forecasts remain a challenge due to its sensitivity to short-term weather, but by analyzing ISI behavior under future climate conditions, especially with changing wind and precipitation, it really offers a valuable look into understanding future fire risk. And this research has really only been possible through sustained collaboration. For over a decade, we've met regularly, currently bi-weekly, with Alaska Fire Service meteorologists, National Weather Service incident meteorologists, and the Alaska Fire Science Consortium. And federal funding from NOAA, NSF, and the Department of Interior has made this possible, supporting the people, the data, and the tools required. And without this support, this work would come to a halt. And a decade of progress depends on continued investment in infrastructure we build together. Next slide. Second topic I'd like to highlight is the essential role rivers play in Alaska for transportation and community connectivity. Those should be movies on the right, but you can just imagine people traveling along the Kuskokwim River, frozen river. The map shows Southwest Alaska centered on Bethel, a regional hub along the Kuskokwim River near its outlet to the Bering Sea. In this region, there's no connected road network. Instead, rivers function as roads, especially in the winter, when frozen channels support travel, freight, and access to essential services. The videos on the right, taken in Bethel this past March, show just how busy these vital ice roads are, and I really was surprised about how fast people travel on the Kuskokwim. Because these rivers serve as critical infrastructure, it's vital to monitor ice conditions as spring approaches. National Weather Service plays a key role in tracking breakup and issuing guidance on when river travel is no longer safe. And this work is increasingly important as climate change introduces more variability into spring conditions, directly impacting public safety and community resilience. Next slide, please. Understanding when river ice breaks up in spring has long been a topic of interest, most famously through the Nenana Ice Classic, started in 1917 by bored miners betting on exact breakup date during the deep winter. And this quirky tradition even made it into Last Week Tonight with John Oliver in 2022. Beyond the novelty, the Ice Classic provides real scientific value. Its consistent 100-year record makes it one of Alaska's longest-running climate indicators. In recent decades, however, forecasting breakup has become more challenging. Warming spring temperatures are pushing breakup dates earlier, not just at Nenana, but across the state, highlighting how a warming climate is reshaping prediction of seasonal events. Next slide. This project is another example of close collaboration, this time with Alaska Pacific River Forecast Center. A now retired forecaster had developed a degree-day model to predict river ice breakup using weather stations shown on the left and the corresponding breakup locations on the right, colored by breakup date. These span Alaska's major rivers, including the Yukon and the Kuskokwim. Through sustained Zoom-based collaboration, we work with the Forecast Center to modernize the model. Our researcher, Chris Weigel, translated the original spreadsheet-based method into a fully automated Python system that selects the most predictive stations objectively for each site and streamlines the forecast process. After 2 years of development, the Forecast Center successfully tested the model operationally this spring. And with just a few tweaks remaining, it's really ready for full handoff, demonstrating the lasting value of academic federal partnerships and deliverable actionable tools. Next slide. This slide shows how river breakup forecasts evolve for Bethel. And it's a video which may not be working in 2025. The model uses cumulative degree days, specifically the sum of temperature above 25 from nearby stations. Forecast began in March 14th and initially projected a breakup of May 9th. As more temperature data came in, the forecast got refined. It ultimately narrowed on the actual breakup date of May 7th. And this method has proved impressively accurate. For example, it predicts the Nenana Ice Classic breakup within a day. Great for science, though not quite precise enough to win the big jackpot, which really requires you to get it to the right exact minute. Next slide. My final scientific topic is the Sea Ice Outlook, a collaborative forecasting effort that began in 2008 after the record-breaking ice minimum of 2007. The idea was born at a scientific meeting where NOAA program manager John Calder proposed a forecasting pool for the upcoming September minimum, not just for fun, but to engage the community and advance sea ice prediction. Since then, the SIO network has grown to include a wide range of models and contributors from around the world. and it's made real progress. Sea ice predictability has improved. Still, forecasting Arctic sea ice remains a tough challenge, and there's much left to learn. And what's at risk now is the infrastructure that makes this collaboration possible. Without continued funding, the coordination and community built over nearly 2 decades could dissolve. And we've learned that retrospective forecasts often outperform real-time ones, highlighting the importance of sustained collection of these sea ice outlook forecasts. And preserving this time series in the research community is essential for improving Arctic sea ice predictability. Next slide. In the last 2 slides, I want to shift focus from science itself to people behind it. I believe science careers are fueled by both curiosity and a strong sense of service. This screenshot shows 4 of my high school friends from Bethesda, Maryland. We all grew up as children of civil servants, and each of us went on to pursue fulfilling careers in science. And now as we approach retirement, I find myself reflecting on how fortunate we were to have those opportunities and feeling concerned about what lies ahead for the next generation. If federal support for science continues to erode, young people may no longer have the same chance to follow these paths. The future of science depends not only on new ideas and tools, but on the people we empower to carry the work forward. Next slide. I want to share the story of my student, Amy, who completed her PhD studying climate variability in southwestern Alaska. Beginning in 2017, she met annually with Chilista elders in Bethel, sharing her findings and learning from their indigenous climate knowledge. These meetings, along with her passion for education and service, inspired her to apply for a NOAA position in Bethel after finishing her degree in 2024, December. It was her dream job, serving as a liaison between the National Weather Service and the community as a climate expert, ensuring that forecasts met local needs. But soon after moving her family to Bethel, Amy was let go during her probationary period, part of recent cuts. It was a loss for NOAA and a blow to Amy, who had invested deeply in this community and this role. Fortunately, she has since found other science-related work in Bethel, but not with a federal agency. Her position has also been critical to bridge a new forecasting-focused undergraduate program we're launching at UAF this fall. And when her job ended, that connection was severely damaged. This story illustrates how consequences of budget cuts ripple outward, disrupting people, programs, and the partnerships that take years to build. Next slide. In response to a need identified by the National Weather Service in Alaska, we launched a new undergraduate program in atmospheric science specifically designed to homegrown forecasters. NOAA in Alaska has long struggled to retain meteorologists from the lower 48, many of whom naturally prefer to live closer to home. This new program, starting this fall, focuses on high-latitude forecasting and emphasizes hands-on applied skills. And it's taken the efforts of many committed individuals to bring this program to life, and to continue support will be essential to ensure its success. Without sustained federal funding, we risk losing our capacity to train the next generation of forecasters, professionals who play a critical role in protecting lives and property across Alaska and beyond. These forecasters depend on science developed by researchers nationwide and on forecast models produced and maintained by our federal laboratories. Our fates are deeply intertwined. To sustain our science enterprise and public service it underpins, we must act together and halt the erosion of federal science funding. Next slide, last slide. Federal funding sustains not only research, but also critical data collection that allows science to serve the public. Strong scientific enterprise has powered America's economy, innovation, and global leadership since World War II. Defending U.S. science isn't just about supporting early career or future scientists, it's about securing lasting benefits for all Americans. And I'll close with this thought. We now have the opportunity and a responsibility to rethink our science culture. Let's move towards a model that's more collaborative and less transactional, one that truly serves the public good. Finally, I'll share something my father used to say when I needed encouragement. Words I've come to appreciate more with age. Keep your courage. And thank you for your attention.
Oh, thank you so much, Uma. That was wonderful and really great to hear about all these different thoughts, and amazing to hear about the connections and collaborations you've built that really make your science so actionable to Alaskan communities. We've got great questions in the chat. Unfortunately, in the interest of time, we're gonna have to skip the Q&A. But thank you so much for joining us.
Thank you.
For your work. All right. Well, thank you everybody for being here. And if you're just tuning in, thanks for joining for the 51st hour of the Weather and Climate live stream. I'm Becca Jackson. I'm an oceanographer. I study the polar oceans, where oceans come into contact with ice. And I'm your host for this segment. If you're just joining in, a couple kind of reminders. The first is just a quick disclaimer that our speakers are appearing here in their personal capacities, not representing their employers or institutions, and expressing their own views, which of course might not be those of other participants. And then a brief reminder about kind of why we're here on your computer screens. We're here to raise awareness with the public about the importance of weather and climate research, and to hopefully spur action that helps remind Congress why this work is so crucial. So good weather and climate forecasts benefit everybody, kind of at a whole variety of scales, from the micro to the macro. Day-to-day weather forecasting, what's the weather going to be like tomorrow, accurate warnings for extreme events like hurricanes, tornadoes, floods, and then longer-term planning for farmers, what to plant, where, and when, city planners, how to build coastlines that can withstand rising seas. Americans deserve good weather and climate forecasts. And historically, U.S. scientists have really been world leaders in this field. Just a few examples, the U.S. has developed the first computerized weather forecasts. We've also developed the first computer models of carbon emissions and carbon pollution, and how those impact the climate system. We've developed this huge network of cutting-edge observations of both the atmosphere, the ocean, all parts of the climate system, using weather stations, satellites, planes, balloons, ships, floats, autonomous platforms. And this excellence is really because of an investment by you, the public, by U.S. taxpayers, and U.S. federal funding for science is really essential to this whole enterprise. But right now, funding cuts are affecting all areas of weather and climate science in the U.S., things like short-staffed weather stations, shrinking and shuttering of climate labs. So this is where you all come in. We encourage you to use the banner at the bottom of your screen. To go to this website, you can plug in your zip code and find your representatives, and we encourage you to make some calls to your members of Congress to communicate to them how important these weather and climate forecasts are to our country. So I think with that, hopefully the next speaker will come online soon. I'm going to introduce Dr. Robert Wood, who's a professor at University of Washington. He'll be talking to us about aerosol mitigation policies and their effects on warming. So thanks, Robert, for being here.
Great. Thank you very much. Do you advance these slides for me? Or
I think it depends on how you're sharing them. I think you have it. Yeah.
Yeah, great. Thanks. And I really appreciate the organizers of this event, which is a critical event, I think, for setting up what is 100 hours, and it seems like I'm splitting this almost right down the middle, 51 hours of continual talks about the importance of science, particularly in weather and climate areas. I work at a public university. I'm a professor at the University of Washington Department of Atmospheric and Climate Science, and public education is critical. Not only is the educational aspects of training the next generation of scientists and workforce, American technologically skilled workforce, but also educating the public in what climate science is all about and where's the truth in here and what's actually happening in climate science. And so those roles I find very important personally to me, and I'm extremely worried about cuts to federal funding, because most of our funding is provided by the federal government. And so I'll try to illustrate where these things are particularly important as I go through this. So I'm going to be talking a little bit about a recent paper from 2024, where it's a little bit different from a lot of the stuff I work on, which is more the physics of clouds and aerosols and the small scale processes. But we're really trying to look at kind of climate models and think about what's the consequences of cleaning up our aerosols, which is going on very rapidly at the moment. So this image here is a sort of a mock-up of what in 1990 on the left, the Smoky Mountains National Park would have looked like on the most hazy days, or the 20% of hazy days in 1990, and now what it looks like today. And you can see it's much clearer. It's not completely cleared up, clear of particles. But what you're seeing here is the effects of aerosol particles. These are tiny little particles of materials, solid or liquid materials that have formed in the atmosphere or have been emitted as particles. And they're very bad for human health. So it might be easy to think we cleaned this up so we can see the Smoky Mountains, but really the cleanup has been done in order to save our human health, respiratory problems and health, heart problems. And that's the main reason for cleaning up the aerosols. It's been a great environmental success story. The only problem is those aerosols do other things to the climate system, namely they scatter light, which is what you're actually seeing there in the image, and they also affect clouds and the scattering of light by clouds. And it turns out that those effects of cleaning up the particles are meaning that we're reflecting less sunlight back to space. We're actually trapping more sunlight in the climate system. And the question we wanted to ask is how significant could that be for preventing us staying below 2 degrees C in the near-term future, so the next 30 years or so. So this is the temperature warming record. We're all familiar with this. It's the warming rate is increasing though, right? So the steepest slope there is towards the end. So we're not only warming the planet, we're probably warming at a faster rate than we've ever warmed before. And I will argue here that some of that increased warming is likely driven by aerosol cleanup strategies, removal of particles that would otherwise cool the planet. We know that Earth is absorbing more sunlight over time, and this is the last record was an incredibly complicated record to get, right? It's the global average surface temperature. This is the global reflection of sunlight from the planet. So imagine how you're going to actually do that. You need satellites that are going all around the world, making measurements over, see the length of this record is 20 years almost. So to do this, it takes an incredible amount of teamwork. This is from NASA. So this is a satellite record spanning from several instruments that go into this. And it's, and I've not even told you what's in it, right? So what it's showing here is the red line is what I wanted to focus on. Basically, it's telling us that in the last 20 years, Earth is reflecting less sunlight back to space. So it was earlier at the beginning, it was 0.5 watts per meter squared more of sunlight, and now it's minus 0.5. So it's dropped by almost a watt per meter squared. That's quite considerable. So what that means is that Earth is now absorbing more sunlight. So greenhouse gases are mainly acting in the infrared part of the spectrum. And that's actually also warming the planet. But this is sunlight, and this is primarily also warming the planet in the last 20 years. So we've got these things pushing in the same directions, which is problematic because in the past, they've actually countered each other, as I'll explain. It turns out that mostly this is because the clouds are reflecting less sunlight back to space. It's not really the clear sky portion of the world. It's the cloudy part that's actually reflecting more sunlight back to space. Radiative forcing is a way of expressing how much a given agent in the atmosphere, so for example, carbon dioxide at the top, how much that's changed since pre-industrial. But what it's showing here is not how much it's changed in terms of the mass of carbon dioxide, it's how much energy it's imparting, it's trapping in the climate system, how much radiative balance. So is it affecting? So things on the left have basically are increasing the trapping of radiation in the climate system. And you see those are the greenhouse gases. They're the primary reason for the world warming. But you can see this bar here, this blue bar, is a cooling agent that's changed since the pre-industrial times. That's the aerosol particles. They're emitted typically with the fossil fuels, but we're able to mitigate those emissions much more easily than actually getting rid of the carbon from those emissions. Because sulfur in the fuel is one of the main sources of this aerosol pollution, and we can remove the sulfur from the fuel before we burn it, and that reduces the amount of sulfur emission. And that's been done in numerous power stations and various ways in which places that fossil fuels are being burned, including cars, vehicles, power stations, etc. Smelters. We can clean up those aerosols more readily if we remove. This is a big source of uncertainty. Right, so this error bar tells us not only is this potentially quite a significant cooling agent, but we don't really know its magnitude very well. And so when you look at the overall, this is the sum of all these agents, and this will tell us, on balance, are we warming or cooling? Well, we're warming because greenhouse gases have increased much more rapidly than the aerosols in total. But actually the story about the aerosols is they're actually decreasing already. By the time this was made, they'd already decreased by 30% since their peak. And so we're warming, but the uncertainty bar is really caused by aerosols. Aerosols are these tiny little particles in the atmosphere, as I mentioned. So you can see them here in the just in the Central Valley. This is not their effects on clouds. These are just the aerosol particles themselves on a polluted day in the Central Valley. You can see the milkiness structure. That's really the aerosols reflecting sunlight back to space. But their main effect is through the clouds, at least that's the consensus. And you can see evidence of that with these ship tracks. Each of these tracks here, this is a low cloud deck off the west coast of California. And each of those tracks is created by aerosol particles that brighten the clouds. And so clouds getting brighter will reflect more sunlight. So if we take away those pollution sources, then the Earth gets darker. And that's the absorption of sunlight that we're seeing, the more absorption over time. Clouds basically reflect more sunlight because every single cloud droplet has to form on an aerosol particle. And so the number of cloud droplets concentration that you get in a given volume of cloud is dependent on the aerosol population. And if you reduce the aerosol population, you'll reduce the cloud droplet concentration. It's pretty easy in radiative transfer to express the reflection of sunlight from these clouds as being just proportional to the surface area of the droplets. So it's really a geometrical problem of can you figure out what the volume or surface area of a droplet is? Well, it's a sphere, so it's not a particularly difficult calculation to make to show that this cloud with more aerosols should be more reflective. And that's partly what you're seeing in these tracks, these ship tracks, basically. Air pollution, we know, is a major source of early death worldwide, and this is driving the cleanup efforts, and it's a great success story, and a lot fewer people are dying of aerosol-related pollution. So air pollution, of which aerosol is a major part of it, is one of the leading sources of death worldwide. And trends in these emissions have dropped significantly. So you can see in the US, North America in general, and in Europe in particular, since 2000 to 2019, there's been significant decreases of multiple, almost 10% per year in some of these, right? So there's very big changes. Nevertheless, in other areas, the pollution has been increasing. Now, I think, in another 5 years, China's emissions have decreased again considerably since this record. We can see this in the total amount of sulfur on the right, SO2. That's the gas that's primarily emitted when we burn fossil fuels and make these pollution aerosols are mainly driven by this. And that's reduced now by almost 50% since its peak, which was around 1990. So already aerosol reductions are the way forward, what's going on right now. So really aerosols now are warming the planet. So it's easy to talk about aerosols as a cooling agent, which is true, but now we're removing them. So it's actually a warming agent. And if we had stronger aerosol cooling in the past, that would be essentially a strong negative radiative forcing. So the reds here, then the future tends to be warmer. This is showing a kind of a way of showing warmer simulations. Stronger aerosol cooling in the past leads to stronger warming because we're unmasking it, right? See, the aerosols have been masking some of the CO2, the carbon dioxide, the greenhouse gas increases, and have been driving the overall cooling rate down. When we take away those aerosols, if they were having a strong effect, then you're unmasking a bigger part of the radiative forcing from CO2, so you get stronger warming in the future. So we really need to know what our aerosol forcing has been and what it is doing right now in order to predict the temperature changes. So we've been looking at cleanup in climate models, and we're using the CMIP6, again, another huge community effort, much of which is sort of essentially funded federally by grants and contracts to agencies and universities, etc., modeling centers to make these simulations across the world. It's not just a US effort. And we're going to look at primarily two of these scenarios. So what these scenarios tend to reflect are potential futures for the Earth. And they don't reflect just the climate uncertainties in the physical climate system, but they also reflect uncertainties in how humans are going to behave. So for example, SSP 126 is it's got a strong amount of mitigation in it. We're removing a lot of the CO2 eventually. We're removing the emissions quickly. We're also cleaning up the aerosol very effectively in that. So the aerosol cleanup in this is very much goes hand in hand with the greenhouse gas cleanup. But that's not really how the world's working. We're actually still increasing aerosol and greenhouse gas emissions, and yet we're decreasing aerosol at this point. And so 126, we really need to decouple the greenhouse gas changes from the aerosol changes, because they're very different policies that cause them. They're easier to do for the aerosol case. So we need to think about changing those. We need to think about thinking about greenhouse gases increasing with SSP 245, which is probably more aligned with what the greenhouse gases are doing, and yet think about using aerosol changes from SSP 126, which is decreasing quite strongly. This is a measure that we can use from the climate models of the aerosol, and you can see the stronger decreases in this cleanup case than in SSP 245. And yet what's probably happening in the near future is we've got more like an SSP 245 greenhouse gas trajectory and a 126 aerosol trajectory. And so we're trying to look at that and see what would happen. I'm not going to go into a lot of detail here because it's kind of technical, but we're using an APRP. It's a radiative transfer approach that you can apply to climate model output and then separate out. The idea is to try and ask how much of this changing shortwave radiation that we saw, the extra absorbed radiation, is coming from aerosol changes versus cloud feedback changes. So as the Earth warms, clouds also go away. That's a part of the story that I haven't really talked about because it's physical climate feedbacks that I'm not, going to dwell on here, but that's also important. So we need to separate out those changes. I won't talk about this here, but what we've been able to do is show that the top of atmosphere, the multi-model mean, so we're using the multi-model mean from the 18 climate models from CMIP6, and we're able to show that in the future, the change in top of atmosphere shortwave, that's essentially the same as how much absorption is being held in the climate system, is we can partition it very accurately into a temperature-dependent component and an aerosol-dependent component. Thinking here that there's the climate feedbacks, the clouds are changing because the temperature's warming. They're also changing because of the aerosol changes, but those are two separate effects. One is through temperature, and so we're able to separate those out pretty accurately. So now we're able, with this APRP method, to actually attribute these to these changes partly to aerosols, and we're able to separate out what the effect of aerosols is. So this is showing you with that, the solid lines just focus on the SSP 126 here. So this is the future now, going from the present day here on the left to the 2100. This is the change in aerosol forcing. So positive numbers means we're going to be driving more warming in future. And so you can see SSP 126 has the strongest, and we're solid lines here, focus on the solid lines for now, has the strongest increase. So by 2050, we're going to expect a whole 0.4 watts per meter squared more of aerosol warming, according to this. That's a significant warming rate over only a few decades. On the other hand, SSP 37 doesn't have any aerosol cleanup in it. And so the aerosol forcing remains almost, change in the aerosol forcing remains almost the same. So we're not going to expect any cooling or warming in future from that scenario. But we know that our approach here gives us different answers from Smith, which is one way of getting at that aerosol forcing. That's the difference between the dashed line and the solid line. So this is, again, telling us there's a lot of uncertainty still in the climate models here. We're trying to get to the bottom of that. I'll leave that. The difference, or rather the difference, could be explained by changing aerosol emission locations, which is not fully accounted for in the Smith approach, but we tried to account for that with the approach we did. And so we can explain quite a bit of the difference in aerosol forcing by where the aerosols are changing their locations in the 21st century. They're going less from Asia, and they're likely to increase over Africa as that becomes more industrialized. But of course, that depends on cleanup policies as well, so we don't know always the outcomes. I just focus on the bottom right here. This is where we try to now put these forcings into simple climate models that are basically emulating the actual climate models. And we can then ask the question of, if we didn't have any aerosol forcing, here the green, this is showing the decadal warming rates for each decade here, since 1900 to the future. If we don't have any aerosol forcing in the climate system, we would have expected a lot more warming in the 1950 to 1980 timeframe, because that was up, but with the aerosol forcings, that actually offset a lot of that. So we didn't see the warming. Essentially, we're delaying the warming. Now we're seeing the warming is now accelerating because we're not only increasing greenhouse gases, we're reducing aerosols, and that's actually increasing warming rates in this scenario where we're using greenhouse gases from 245, which is best estimate of what we think the near future is going to do, and the aerosols from a rapid cleanup. We can get 30 or 40% more warming rates in the next in the decades now, right? So that's pretty important, and ultimately it could mean that these are cumulative probabilities that take into account the uncertainties in the feedbacks and the ocean heat uptake, all of that. And on the right, this is with the SSP 245 greenhouse gas increases. If we don't have any aerosol cleanup, that would be this dotted line. We would get a 30% chance of passing 2 degrees C by 2050. If we clean up our aerosols in accordance with 126, deep and rapid, we increase that to 80%. So our chances of passing 2 degrees C are increased from 30% to 80% by strong aerosol cleanup, which is actually what we're doing, right? So whether this plays out depends on a lot more than what I just said, because there's a lot of uncertainties here. So that spread in the cumulative figure, i.e. the width of this curve, is actually telling us there's a lot of uncertainty in this. And so we don't really know what it's going to do, but this is telling us that aerosol cleanup is likely to be driving us towards dangerous warming. Okay, so this is the final slide. And aerosol changes, what we did is isolate them from other changes in existing simulations with all those changes. But that's a bit of a challenge. I didn't get into that in a lot of detail because it's technical. But aerosol cloud interactions, it's really the clouds that dominate future aerosol changes from cleanup policies, and the likelihood of maintaining warming to below 2 degrees C is strongly reduced by implementing these cleanup strategies, unfortunately. Thank you.
Great. Thank you so much, Robert. We'll take a few questions from the chat. Let's see, early on in your talk, someone asked, I wonder why clouds are reflecting less when you showed the plot decline. I think to some extent you addressed that, but do you want to just
yeah, clouds are reflecting less because we're moving really from a world in which we had this situation where we have a lot of aerosol particles. Each droplet forms on one of those particles, and so it's the number of those is controlled by the aerosol population. So if you have more of them, you have smaller particles because there's only so much liquid to go around in this cloud. And so you divide the liquid by more particles, each one smaller, and you can show there's more surface area in that case. And the surface area is what reflects the sunlight back to space. Hopefully that's explained.
Wonderful. Yeah. And then we had a question, if we capture that sunlight with things like solar panels, does that affect the warming?
So the idea here is that solar panels are absorbing light, right, rather than reflecting light. That's a desirable property of a solar panel, right? It's to absorb the light and turn it into electricity. Yes, if you covered enough of the planet with solar panels, you could probably do that. But bear in mind that clouds cover 67% or 2/3 of the planet. Mm-hmm. Not all of them are perturbed by anthropogenic aerosols, but by some estimates, half of them are, or 20%. Think about how much solar panels that would have to be, right? That would be a lot more than. I mean, right. There's a thought that you can power the whole of the US with solar panels the size of one state, right? Small mm-hmm. state. So,
yeah, question of scale.
Yeah.
Yeah. Okay, and then Sage asks, what got you into researching aerosols in this field?
Yeah, that's a great question. I originally, I'm a physicist by training, and I wasn't enamored by theoretical kind of lab-based work. I really wanted to do something on the Earth. I don't know. I just did a seismics class at one time, geophysics class at undergrad, and we did a seismic experiment that was kind of remote sensing, basically. It is remote sensing, and it really turned me on to the idea of studying the Earth, basically. And then I got into a PhD program looking at sea breezes and nothing to do with clouds, and then really wanted to work on clouds. I don't know what got me into that. And then aerosols. So, yeah. So, thanks.
Great, thanks. And then there's a question from Bob Hudson. What does your work imply for ECS? Is your model's value closer to 3 or 4.5?
ECS, yes. So the way this works is the ECS is essentially I'm using the ECS of the average ECS of the climate models that I'm using. So it's emulating that, or the emulator essentially will use the climate. So the central value, well, if we think the average value is something like more likely than an outlier, then that should be reasonable. I'm not making assumptions about that other than using what is the 18 models average, which should be a reasonable estimate, I would think. Of course, we don't know that.
Great. And then maybe I'll end with one question for me. I'm curious how you think about both like sort of the policy implications and sort of communicating on a topic like this that's, aerosols are multifaceted it's good to clean them up for the air quality, but it's bad for the warming. And so how do you think both about connecting that with policy and the communication with the public?
Yeah, I didn't offer any policy guidance because, I'm not really a policy person. And to be honest, I don't know what I would recommend. I'm certainly not an advocate, but others have suggested that you could potentially deliberately brighten clouds to make to bring back some cooling. Maybe you would do that with salt. I don't know whether that could work. I mean, I'm interested in working on it. I'm interested in work on that topic, but I just don't know whether that could possibly work. I think I read it as we really need to double up on our mitigation efforts, right? Because we've now got. I'm talking about the greenhouse gas mitigation efforts.
Right.
We've got to keep them up with the airs. We got to double, potentially 30% more warming to deal with now. So yeah, it's sort of, I look at it like that.
Yeah, a call to action on that front.
Yeah.
Right. Well, wonderful. Well, we're perfectly on time. So thank you so much, Robert. It was wonderful to hear about your work. Thanks for joining the live stream.
Thanks.
So we are at 4:00 Eastern, which means we're, I think, just entering our 50. Well, it still says 51 hours. We're on, I think, the cusp between 51 and 52 hours into our live stream. Up there it goes, 52 hours. Of the weather and climate live stream, 48 hours to go. And if you're just joining, I'm Becca Jackson. I'm an oceanographer. I study the ocean and the polar regions where the ocean interacts with ice around glaciers and icebergs. And I'm your host for this segment. If you're just joining, a couple of reminders about how this all works. So first, just a disclaimer that our speakers are here talking in their personal capacities, not representing their institutions, and expressing their own views, which are obviously not those of all the other participants. And then a reminder, most importantly, about why we're here. We're here to raise public awareness about the importance of weather and climate research and forecasts, and to hopefully spur action to help remind Congress why this work is so crucial. And so good weather and climate forecasts benefit everybody across a whole range of scales, kind of locally, day to day, what's the weather going to be, predicting accurate warnings for extreme events like hurricanes, tornadoes, floods, and all sorts of longer term planning, farmers thinking about what to plant, where and when, city planners thinking about how to build coastlines that can withstand rising seas. Americans deserve good weather and climate forecasts. And historically, U.S. scientists have been world leaders in this field. Just a few examples. The U.S. has developed the first computerized weather forecasts. We've developed the first computer models of how carbon emissions and pollution impacts the climate system. We've developed a huge cutting-edge network of observations of the atmosphere and the ocean and the whole climate system, from everything from weather stations to satellite, planes, balloons, boats, floats. And this excellence is really because of investment by you, the public, U.S. taxpayers. U.S. federal funding for science is really essential to this whole enterprise. But with current funding cuts, kind of all areas of weather and climate science in the U.S. are in jeopardy. We have short-staffed weather stations, shrinking and closing climate labs. And this is where you all come in. So at the banner at the bottom, you can see a link to go to look up the phone number for your representatives, to call your members of Congress and convey to them how important we all think it is to support our weather and climate research and help save these important forecasts for our country. And so with that said, I'm excited to introduce our next speaker in the lineup. We have Dr. Lucas Vargas Zeppetello, who's an early career scientist, assistant professor in the Department of Environmental Science, Policy and Management at University of California, Berkeley. And we're excited to have you here, Lucas. Thanks.
Hi, Becca. It's really great to be here. I just before I get started, I'm going to focus on this topic that I've been thinking about a lot, really since graduate school, about heat waves and climate change. But it was great to see Rob up here earlier. Rob and I actually played in a band while I was in grad school, which is hilarious to see him up here. But I think one of the things that I've been really, honored to be a part of this community, like you say, is that everyone, at least who I've interacted with in my community so far, my journey through science, takes the part of this that we are public servants extremely seriously. There's not a lot of glibness about the fact that we get to do really interesting stuff that's incredibly meaningful at the expense of the US taxpayer. And I think that's been a common theme throughout certainly my career and the careers of, all of the folks who I've had the privilege of working with. So I'm very honored to be here today, and I really thank you all for putting this together. So my talk's going to be about heat waves and climate change, and I sort of glibly titled this, "Will heat waves get much worse under climate change?" The short answer is obviously that yes, that's in the cards. Any kind of metric of temperature is going to get worse as the mean state warms up. But what I got really interested in over the past year or so is thinking about how do departures from the mean change as the average temperature warms up. So trying to think of a metric that you may not think would get worse under climate change and see how those evolve. So how does the extremity of an event change as the average climate warms up? And the motivation for this really started when I was thinking about exposure to dangerous combinations of heat and humidity. So these are from historical observations. Basically, all I've done here is just counted using observations starting in 1979 and going through 1998, how many days per year at each land surface point across the globe falls into a category that the National Weather Service and OSHA consider to be dangerous and extremely dangerous, using a quantity referred to as the heat index. So I'm not going to get into the details of what exactly the heat index is. It's complicated, but it basically measures thermal stress on the human body. So how does the combination of temperature and humidity affect our ability to basically sweat and cool ourselves? And what you'll notice, and not a too surprising thing here, is that your amount of exposure to this particularly dangerous days depends on where you live. So if you're a citizen of the global south and the subtropics, chances are there are several months every year that you experience dangerous combinations of heat and humidity, at least for some portion of the day. So you can see lots of places in India, parts of Australia, South America, et cetera, Africa, anywhere from 25 to 100 days a year. So sort of a seasonal phenomenon. You could think of a warm season in these places as being, potentially a significant chunk of your day. It's difficult to be outside, which people have adapted to this over time. And then when you look at extremely dangerous days, when the guidance from the National Weather Service is basically like, don't go outside, essentially, and you need to get in air conditioning pretty much immediately, you can see that these events are very, very rare. They don't happen that much on average. Maybe one day a year you get close to this boundary on average. And you essentially have to be in the middle of the desert, which is what that little region of South Asia is showing, or right next to some of the warmest waters on Earth in the Arabian Peninsula. So these events are not regular features of the climatology in the historical record. But when you go out to a 3-degree warming scenario, the picture changes considerably. And this is something that I made right as I was finishing grad school. And this still, I'd be lying if I said this didn't keep me up at night. So when you warm the average temperature by 3 degrees Celsius, you really fundamentally alter the Earth's and the people who live there's exposure to both dangerous and extremely dangerous days. You can see that in a 3-degree warming scenario, large chunks of the global south and even parts of the global north go from heat being, a seasonal feature of the climatology to the climatology by itself. So we're talking about almost the entire year, people being exposed to dangerous days where it's, can be unsafe to work and exercise and do things outside. And I think the even more sinister part is when you look at these extremely dangerous days, which again are extremely rare in the contemporary observational record. But when you go out to a 3-degree warmer world, there's, considerable chunks of the human population that are going to be exposed to events like this on a regular basis every single year. And we don't know what happens when, potentially in this figure, billions of people with low adaptive capacity are exposed to events like this all the time. So from a science perspective, the question that this posed to me was, okay, I've made these plots assuming no changes in the temperature distribution other than increasing the average value. So what happens to those temperature distributions as you get warmer and warmer in the mean state? Just as an example of this, this is from the Central England temperature time series. This is the longest continuously running daily temperature observation time series that exists. And what I've done here is just basically plot each year one on top of the other. And then you can take the long-term mean. This is the seasonal cycle. And I'm just focusing here on the warm season, which is essentially just the 100 continuous warmest days of the year. And then what I did here is basically just say, what's the biggest temperature anomaly in each year as you move forward in the year? So I've done a decadal average. You can see here in the black lines moving forward through time. And you can see that in this time series, and this is with the mean removed, right? So there's no a priori expectation that these changes in the time series should be driven by global warming. And yet we see that the maximum temperature anomaly starts to creep up as you go further along in time. And so the question that this sort of raised to me was, in this particular weather station, the extremes have warmed faster than the mean value. And my question is this general behavior that we should find around the world, everywhere, all the time? Can we predict this behavior? What physical processes are responsible for this? So this is what I was going after. So you can make a map of what I'm calling the extreme event climatology. This is the long-term average of the biggest warm season daily temperature anomaly. So this value ranges from basically 3 to 15 degrees Celsius, basically saying the hottest day of any particular summer is going to be anywhere from 3 to 15 degrees in terms of Celsius, warmer than that day in the seasonal cycle. So again, everything here is taken the mean out of the equation here. So we're just looking at departures from your expectation on any particular day. And right away, well, first of all, I should mention that the dots here are from long-term observations, which are only possible with significant funding. These are sort of to me, I think of them as like the crown jewel of any society's capacity to monitor its own weather. These weather stations are just an incredibly valuable resource. And we're very fortunate in this country to have long-term weather stations and made investments in those that have enabled us to make a lot of progress on understanding not just temperature variability, but all sorts of climate variability. And you can see how, the map of these stations just by itself, before you even look at the values, tracks places in the world that have the capacity to make long-term investments in weather and climate research. I mean, they're disproportionately located in wealthy countries. There's historical reasons for that, but this is just an invaluable resource that would not be possible without long-term federal funding for this kind of stuff. So I did want to mention that. I put these points backwards. That's fine. So from a physical standpoint, the main feature here is that there's high values of these temperature anomalies in the mid-latitudes, so as you go closer to the poles, and there's lower values in the tropics. So the tropics tend to be less of a noisy place from a weather standpoint. We're looking at daily anomalies here. And the mid-latitudes tend to be a little bit more noisy, even in the summertime. So that's the general pattern of these temperature anomalies. And now I'm just going to do some quick explanations of why we think that this pattern exists. Before I get there, this is a map showing projections by climate models of how these events will change in time. So I'm basically plotting here. You can think of these values as the percent changes in the maximum temperature anomaly with respect to the mean. So anywhere that there's a positive value it means that extremes are warming faster than the mean. Anywhere that there's a negative value, it means that the extremes are warming slower than the mean. So there's a lot of really interesting stuff in this pattern. The main thing that sticks out to me is that, first of all, there are changes. So just the idea that the extremes will warm exactly as much as the mean is not a totally accurate a priori hypothesis. And then the second is that the models seem to be saying that amplification of extreme events is disproportionately going to happen in the tropics relative to the mid-latitudes, where you sort of see differing patterns across space. But the models tend to agree that the tropics extreme events, extremely high temperatures, will become more so under climate change. And in the higher latitudes, it's not so clear. So what's going on here? How can we sort of think about this? I'm going to break it down into three main processes, and hopefully I'll have time to zip through some of these. The first is just what we call thermal advection in the atmospheric sciences. This, you can essentially think of this as just mixing of air parcels with different temperatures across space. So if you're sitting in the middle of this diagram right here, and there's a hot place to your left and a cold place to your right, when you preferentially get air from a hot place, you'll tend to have bigger temperature anomalies. The second process has to do with something that Rob just talked about, which is basically variations in cloudiness. You can think of this as more you have preferentially really, really sunny days if you live in a place that's very cloudy. For most of the time, you might expect to have a bigger, extremely high temperature anomaly in the long term. And then finally, we call this energy partitioning at the land surface. You can essentially think of it as variations in soil moisture that drive preferential atmospheric heating or evaporative cooling. So how do all these three processes work together to influence the changes and the climatology of extreme events? So just thinking about advection, first of all, basically the only question I'm asking here is how hot is it on average around your place in space that you care about? So it's easy to visualize this if we just pick a location in space. So arbitrarily, I should have chosen a place in America since this is about US science funding, but I chose London, England. It sits right in the middle of this map here. And basically all I said was, how hot is it relative to London, England, and the Bay State everywhere in this sort of circle that I draw around the country? And how far are those places away? So I weight every place by how far away it is from London, and I'm only looking at places that are within a 4,000 kilometer radius. I can explain why I did that if folks are interested, but there's no surprises here. What you find when you use this metric is that hot places in the desert sing out as being potentially very influential on extreme events in London. So if you get an air parcel that's being advected by the atmosphere from somewhere in the Sahara over London, you're preferentially going to have a very hot day there. So essentially what I've done is average this quantity at every place in space. And that leads us to a map of basically how much does advection contribute to these extreme events over space. And so when you do that, this is what this looks like in the observations on the left over here, and then in the CMIP6 models, as Rob mentioned, an enormous community effort that's largely underwritten by the federal government on the right here. And you can see that if this is all that's going on, the models do an okay job at reproducing this sort of observational metric, which I should note has this pattern that we're looking for of low values in the tropics and higher values at the poles. The idea being that places in the higher latitudes can have more of an influence of thermal advection on extremely high temperatures. So that was kind of nice. It suggests that thermal advection might be playing a pretty significant role in the extreme event climatology based on the fact that these two metrics are sort of singing the same song. And when you go out to future warming, things actually line up pretty nicely because the changing temperature patterns will influence how thermal advection is able to influence the extreme event climatology at each place in space. And so when you look at this metric of basically taking the average temperatures in hot places relative to each place in space, and you sort of project that forward in time using climate models, you start to see some of these patterns that sung out to us at the beginning of this exercise, where you've got decreases in extreme events in the higher latitudes and increases in the poles. So when I sort of found this, it sort of suggested, okay, we've got something here. There's a reason to believe that changes in thermal advection, just based on changes in the mean temperature pattern, can go a long way at explaining these changes in the extreme event climatology. So I thought it was nice that something so simple as just the changing average warm season temperatures across the globe could have such explanatory power on these individual events that are so disruptive and catastrophic. So that was a nice thing to see. I'll move on now to radiation and its role in understanding extreme events. Again, you can think of this basically just as how variable is the cloud cover in your place in space. And to do this, I used observations from the Ceres satellite, which Rob also showed in his talk right before me. I should note again that this is a project that involves enormous collaboration and is just integral. Federal funds are integral to this observational data project, which is incredibly vital for all sorts of climate research. I mean, Rob and I are not in the same field, and yet these two talks are invoking the Ceres observations. You can see just how vital these instruments are for our capacity to understand our global environment. So I should just make sure I give a shout out to Ceres before I keep going here. But nevertheless, what am I using it for? To try to understand how radiation influences heat waves, I'm going to ask this question: what is the largest amount of excess energy into the land surface on average? So what, in sort of the average sense, is the biggest departure in terms of excess energy coming in to the land surface? And we can measure that from Ceres, which is really great. And again, both the Ceres observations from satellites and the CMIP6 climate models are pretty good at estimating this quantity. There's some biases in the CMIP6 that I'm not going to get into, but essentially, there's, you can think of this, these are big energetic variations at the land surface, right? So Rob was talking about a 1 watt per meter squared anomaly. This is getting to the order of 25 watts per meter squared every month. So if you get a 25 watt per meter squared anomaly at the land surface, you're going to be hot, and that's going to likely translate into some pretty extreme heat waves. And you can see that the average value of this quantity is around the order of 20 watts per meter squared across the global land surface. So there's a contribution of these events just through radiative input into the system, which is kind of nice. And then when you go out to climate change, you find something that I did not expect and thought was really interesting, which was that this quantity goes down basically everywhere across the global land surface. This has to do with low cloud burnoff that is found throughout the CMIP6 models. I'm not making statements on whether I think this is a real phenomena or that we should expect this. Clouds, as Rob just alluded to, are enormously complicated and very difficult to get our handles on. It's one of the biggest uncertainties in our estimations of how much the world will warm. But nevertheless, what the climate models are saying here is that this quantity of excess energetic input into the land surface will be reduced. And you can read that as basically saying the average will go up, but the extremes will go down, right? Because there's a harsh upper limit on how much energy you can pump into the land surface that's set by the clear sky maximum value. So this quantity is going down a lot, and this is the estimate of how much this will influence extreme events. So you can see here that basically anywhere you have reductions of this quantity, your extreme events are going to go down relative to your change in the mean temperature. So this kind of goes against some of the stuff that I had found earlier. So we saw that changing advection patterns line up very nicely with our expectation from the CMIP6 models. But now I'm throwing a wrench in that because it seems like radiation is driving down the extreme events relative to the mean. So how do we square this circle? What's missing when I have time? I'd like to shout out some work by Adam Bauer, who's done some really nice work on the relationship between temperature and soil moisture. I'm not going to get into this work, even though it's really been fantastic working with Adam. I did just want to mention that Adam's work and some of my own PhD stuff has shown that there's a nonlinear relationship between soil moisture and temperature. And the question is, how does this relationship influence extreme temperatures? You can see, just focus on the black line in this. I'm pointing at the screen. You can focus on this black line here, basically showing that as you dry out your soils, your temperatures really start to go up quickly as you get towards the dry side of the soil moisture spectrum. And I'm going to talk about how that influences heat waves in a second, but I also just wanted to mention before I keep going, unlike the observations that I've just been singing the praises of, that's not the only investment that's required from our National Science Foundation and other scientific institutions. It's also investing in people. So Adam's PhD work and my own were largely underwritten by the NSF. And I can't really say enough about how important this is for junior scientists to get 3 years of funding to basically explore themselves and explore the things that they're interested in. It's not an exaggeration to say that this opportunity and those 3 years that were underwritten by the NSF completely changed my life. And I think I can speak for Adam when it said it changed his too. It allowed him to take risks and get out of a program that he wasn't interested in and do something else in generative. So it's not just observational platforms. It's not just technology. It's also investing in people. And I think that's something that maybe others have talked about, but I really did just want to make that point, that the money that goes into these institutions is not just so we can build better platforms and build our fanciest toys. It's also investments in the people who are going to carry this work forward in the long term. So shifting gears back right in the front. You can see the relationship between temperature and soil moisture changes as you go out to warmer and warmer climates. So essentially all I've done here is just add energetic forcing to the land surface as you go from these yellow lines down here to these darker red lines up here. This is an example of sort of an extreme version of climate change where you're really rapidly warming the mean temperature. But what you'll notice is that the curvature of these lines start to change as you go up into these warmer and warmer temperatures. And in particular, if you assume the same amount of variations in soil moisture, you will get more extreme temperature events as you go out to a warmer and warmer world. So if you increase the energetic input into the system, you will cause larger temperature anomalies when you have dry soils relative to when you have wet soils, based only on the curvature of this line alone. So I'm not saying anything about how soil moisture itself will change as the climate warms up. It's the curvature of this relationship that dictates everything that I'm about to say. And we can actually quantify this. So one of the most fun parts of working on this project was I was able to develop just a very basic equation to quantify how much your extreme events will change based on the curvature of this line relative to the mean state. And when you do that, you find increases in the extreme events relative to the mean basically everywhere. And the argument that I'm making here is that this essentially cancels out the negative feedback from solar radiation. And so all you get in the end is the mean temperature pattern associated with thermal advection. So these three processes are working in tandem, but two of them largely cancel one another out. And so you can combine all this to make a full prediction of the changes in extreme events driven by these three processes here that explains about 60% of the variance in the zonal mean changes, which I was pretty gratified by, considering these events are sort of inherently meteorological in the sense that they depend on sort of short-term forcing, and yet we've been able to sort of boil them down to these three patterns that you can explain largely with monthly observations and climate model data. So I was pretty pleased with this. I think we've been able to make some real progress here. And I did want to highlight, this might seem like a different problem, but I promise that it's not. We have a real problem in climate with thinking about rainfall projections. And I can illustrate this best by just looking at the spread of 100-year-long trends in rainfall across the globe that are predicted by climate models. And the argument that I'm making here is that this really affects our capacity to understand all sorts of terrestrial processes, where either you think about ecosystems or agriculture or heat waves. It all ends up being connected to uncertainty in these rainfall projections. So when you look at the local maximum trend across climate models, you find this picture, which suggests that basically everywhere, this is in percent, so the deserts really stand out, but don't worry about that so much. But even in the continental United States, I mean, this is a chance of a 40% increase in rainfall over the next 100 years. That's a big number. And then when you look at the minimum, it's almost exactly the opposite. So this is a 40% reduction in rainfall over the next 100 years, potentially associated with climate change. And so, like I said, this is an example of a really, really big science question that, if we are to get better at this stuff, is going to require just an insane amount of investment in people to tackle this problem and observational platforms to get better at observing all of the relevant state variables to get it. And I bring it up because it does have a really important role to play in this heat wave stuff, but I just think this is a classic, and I'm not claiming that this is the only one of these problems, but there are so many problems like this in climate science that really, really matter for people, that the cuts that we're experiencing right now are going to directly inhibit our capacity to understand. So we may think of certain things in climate science as the story being over. We're probably not going to make that much progress in certain areas, but there is real opportunity here to make impactful and scientifically interesting progress. And so I'll just leave it there and basically just do 2 take-homes about the processes that are responsible for heat wave changes in a warming world. And then, again, just to reiterate this point before I run out of time, that this work depends on federal funding in all these really important ways that I think are really important. So I'll leave it there, and I'll thank everybody for their attention.
All right, thanks so much, Lucas. That was great, and really nice to hear both about kind of the amazing progress you've made in your research and the open questions that require ongoing investment. Maybe we'll start, since you alluded to the NSF funding during your graduate studies that was so crucial. And there's one question from Sage saying, what got you into your specific research topic that you're presenting to us here today? So do you want to elaborate a little bit on that path?
Yeah, I can. Good question, Sage. I think it's always good. We think of ourselves as objective people, right? But our interests are often, have nothing to do with that. I'm incredibly fortunate to be at an academic institution in the place that I grew up in. That doesn't happen for everybody. It's a hard world out there. And growing up in California, water resources were just in the air. It was something that, was not far from the minds of, many, many people. And so I think I gravitate towards these problems of understanding water variations because I just grew up in a place where that was something that everyone was thinking about all the time. And, I'm fortunate to have had a lot of exposure to, outdoor stuff growing up as a kid and all that. And I think I gravitate towards problems that I can see a little bit, if that makes sense. I hope that answers your question.
Yeah, great. Thanks so much. Well, in the interest of time, we probably have to move on to the next speaker, but thank you so much, Lucas, for being here and joining the live stream.
Thanks for doing this.
And thanks for everyone out there asking great questions. Sorry we didn't get to everybody's. So it's 4:30 Eastern, and we're in the 52nd hour of the Weather and Climate live stream, 48 hours to go. If you're recently joined, I'm Becca Jackson. I'm a physical oceanographer. I study ocean in the polar regions where ocean and ice interact. I'll be talking actually about this work on Sunday morning at 8:30 in the morning Eastern, if you want to get up early and hear about that. We have the banner up front. I should mention right now, we just reached over 6,000 calls made so far from the link below. And so encourage you, if you haven't already, to follow the link below to find the phone number to call your congressional representatives and tell them the importance of climate and weather research. So before we get started, just a couple of reminders. Just a disclaimer that all our speakers are appearing here in their personal capacities, not representing their institutions and expressing their own views, which may or may not be those of other participants. And a reminder too about why we're all here on your screens. We're here to raise public awareness about the importance of weather and climate research and hopefully spur action, like increasing that number up from 6,000 through calls to Congress, conveying why this work is so crucial. And as you probably know if you've been on here, good weather and climate forecasts benefit everybody across a whole range of scales, from sort of the day-to-day, what will the weather be, accurate warnings for extreme and dangerous weather events, long-term planning for everybody from farmers to city planners, how to build coastlines that can withstand rising seas, where and when to plant crops, and what to plant. These all depend on accurate and developing improved weather and climate forecasts. And historically, U.S. scientists have really been world leaders in this field. Just a few examples are the U.S. has developed the first computerized weather forecasts. We've developed the first computer models of carbon pollution, emissions, and the impacts on climate, and a huge network of observations of the ocean, the atmosphere, the whole climate system through weather stations, satellites, planes, balloons, floats, ships. And this excellence is really because of investments by you, the public, U.S. taxpayers. U.S. federal funding for our science is really essential. But with funding cuts, this is affecting all areas of climate and weather research in the U.S. Things like short-staffed weather stations, shrinking and shuttering of climate labs. And so this is where you all come in, and the banner below. Please, if you haven't already, take a moment to follow the link. You can plug in your your zip code, find your representatives, and make some calls to help convey the importance of weather and climate research to our country. And as you saw earlier, we've hit 6,000 calls from this event so far through that link. And we'd love to see that number keep going up. So with that, I'm excited to introduce our next speaker. Dr. Todd Emmenegger is a postdoc fellow at the National Center for Atmospheric Research. And he's going to be talking to us about the future of extreme precipitation and the importance of model diagnostics. So welcome, Todd.
Awesome. Thanks, Becca. Hi, everyone. Yeah, so as Becca said, I'm currently a postdoctoral fellow at the National Center for Atmospheric Research. And yeah, my talk today is going to be titled The Future of Extreme Precipitation and the Importance of Model Diagnostics. And there's a lot of sponsors down here on the bottom. So all these sponsors are kind of agencies that really helped me get through my graduate degree. I was sponsored through NASA. I had the opportunity to kind of do internships with the Department of Energy and was live in a more national lab. I also had the opportunity to learn from and collaborate with peers at NASA Jet Propulsion Laboratory. And I also was able to actually be funded and continue to live as a graduate student through NOAA grants and National Science Foundation grants. And currently at NCAR, which is operated by the University Cooperation for Atmospheric Research. It's also an NSF lab. So I'm going to kind of get into the importance of all this funding later in terms of what this is on the international scope. But first, I just want to kind of get into some science. So just to really quickly, what we're going to go through is I'm going to just be talking about the basics of moist convection and precipitation. This can be kind of complicated. So I really want to kind of get the basics down to everyone watching. And then going to get into global climate models, kind of introduction into what those actually are. Then going into model diagnostics, which is something I did my PhD on at University of California, Los Angeles, under Professor David Nealon, really kind of diagnosing what's going wrong in these global climate models that are used to kind of project future climate and how we can make them better. And then I'm going to get into what the models actually say about futures of extreme precipitation. All right, so first things first, a little science lesson. So this plot right here on the y-axis is water vapor, on the x-axis is temperature in Kelvin. And this is these curves are defined by the Clausius-Capellan relation, which just describes how much water vapor the air can contain before it starts to form liquid water. So you can think about this in terms of relative humidity. So at some temperature, your relative humidity, as your temperature increases, your relative humidity starts to increase. And there's no units here, it's kind of just a schematic. But basically, once you're at saturation, if you have more water vapor than what's determined by your saturation water vapor, then you're going to start having condensation. You're going to actually start to form liquid water. You can think about the saturation as being 100% relative humidity. So when air cools, it needs less water vapor to form liquid drops. And this is kind of like your dew point temperature you see on a weather forecast. And water vapor at saturation and around the current global temperatures, if you were to increase the global mean temperature by 1 degree, that corresponds to about water vapor saturation that increases by about 7%. So for every degree, you're really increasing the amount of water vapor you can hold by 7%. Now we're going to get into a crash course just on tropical moist convection. So the atmosphere is stable when it's stratified by density. So you can think about just more dense air kind of lying below less dense air, and usually that's kind of determined by temperature. So the sun heats the ground, and then the ground gets heated by the sun and warms the air directly above it. And then that air gets warmed and it starts to rise, right? It expands, it becomes warmer, it becomes less dense, and it begins to rise until it reaches a level of equal density in the atmosphere. And that's the basics of convection. So as the air rises, it expands and starts to cool. And for this rising air to remain buoyant, the environmental temperature has to cool at a quicker rate than that purely from expansion. So this might be a little confusing. I'm going to show a plot in just a second, but this is usually pretty rare. The atmosphere doesn't really cool with height at a rate quicker than how air just cools by rising. Otherwise, it'd be just very unstable all the time. Usually it's kind of at a rate that's higher than air doesn't cool as quick as just how air would rise. So it's usually pretty stable. But in the tropics or with moist convection, if the air is moist, it starts to rise, right? It expands. We talked about this earlier. When the air cools, its saturation vapor pressure drops and it carries with its water vapor and it reaches saturation, and you start to get these liquid drops that start to form. Now, those liquids start to form, it releases something called latent heat, which actually heats up the air parcel a little bit more, and it kind of fuels it so it can keep rising. So its temperature doesn't decrease as much as it rises. It actually compensates a little bit. So what I mean by this is you can think about this rising air here, this cloud, as being this red curve over here. And this plot on the left is temperature on the x-axis and height on the y-axis. So as your particle starts to rise, so just the air is rising from the surface, if it doesn't have moisture, it's going to follow this red line and then just kind of follow this magenta line. You can kind of see this blue here. This blue line is the environment. It's never really warmer than the environment. And since it's never warmer than the environment, it's not buoyant, it's not less dense. But if that particle has moisture and it reaches something called the lifting condensation level, it starts to form liquid air drops. It starts to heat up the air parcel, which compensates for what would happen if it was just rising and cooling by expansion. And this cooling happens at a slower rate. And eventually the air becomes buoyant or convex, and you start to get these clouds. And that's kind of the basis of tropical convection. It's called conditional instability if anyone's look more into it. So I'm going to dive into climate models. So global climate models are possibly our most important tool for predicting and adapting to climate change. This is kind of how they work. So you can think about, you have the Earth and you have the atmosphere, and you split it up into a bunch of boxes horizontally, usually by latitude and longitude. And it's about a degree by degree, a little bit more usually. And you also split it vertical grid. So you have this like giant kind of gridded atmosphere. And each box has a corresponding system of mathematical representations of different climate variables. And those mathematical representations determine how each box interacts with its neighbors and then other forces in the box. So you can think about maybe there's soil moisture that's kind of evaporating from the ground, that's kind of entering the box. There's all these fluxes and different things coming from the neighbors. And really it's just a large system of equations that are usually solved by computers, and you kind of run this forward in time, and you just kind of see how the whole atmosphere kind of changes, just pattern amongst these boxes for different types of variables. Now, some of these variables or some of these processes in the atmosphere are very important, but they can't really be resolved on such a large scale. You really need a finer scale resolution. So those are called subgrid scale processes. And a good example of this is atmospheric convection, clouds, something I was just mentioning. So usually these subgrid scale processes are represented by parameterizations, and that just means a simplified physics scheme. And its point is to kind of model the effect of the subgrid scale physics on the large scale. So for example, here we have convection. So convection kind of reorganizes air according to density, as we saw earlier, in the vertical throughout the column. And what that does is if the air starts to rise, you have this inflow from the bottom. So you're getting inflow in from neighboring boxes, and it reaches a point where it stops and starts to pile up and it pours out. And what that does is it kind of has this outflow, and that's going to interact with the neighboring boxes as well. And these are usually determined by parameterizations. Now, the couple model intercomparison project is basically this international climate modeling project, and helps us kind of better understand current and future climate under different greenhouse gas scenarios. So here's an example that I got from climatescenarios.canada, just of like how they kind of determine these scenarios. If you look closely, it just has like the different names of the scenarios, relative concentration pathways, and it has kind of like the greenhouse gas forcing for CO2 in the middle, methane on the right, nitrous oxide. So the kind of these future scenarios describe the levels of greenhouse gases emitted in the atmosphere, human activity, whether that's we start using renewable energy tomorrow and we stop kind of using greenhouse gas or emitting some type of greenhouse gases, or if we kind of just keep on going business as usual. So the most recent CMIP phase, which was phase 6 a few years ago, had 52 institutions participate. And these subgrid scale parameterizations I was mentioning earlier are unique amongst all the global climate models, GCMs. So the idea is we have all these different global climate models from all these institutions kind of representing these processes differently. And we can compare the simulations between the models to see which results are well agreed upon or robust and which are a little less certain that we need to kind of investigate more. But if the models are simplifying convection and rain so much, how can we kind of trust them? Well, something that I've been working on in particular is something called model diagnostics, which is when you compare the output of the model simulations under its current climate runs to observations that we actually have with us. And this allows us to evaluate how well the models, what representations kind of capture that part of the climate system. So I'm going to get into a model diagnostic, just an example, and this is called the pickup. So over here on the right, I have a plot on the x-axis column water vapor, so just the total amount of water vapor inside atmospheric column. And on the y-axis, I have expected precipitation. So you can almost think about this, and this is at the Nauru site. It's a site sponsored by the Department of Energy. It's actually not really taking any measurements anymore, but it's an island in the tropical Western Pacific. And what this plot is telling you is that, let's say you're at 50 millimeters calm water vapor, how much precipitation do you expect? Well, you kind of expect close to zero, but you start to notice that as you start to increase your amount of calm water vapor, you get a rapid increase in the amount of expected precipitation, or the precipitation begins to pick up rapidly once some critical humidity value is reached. And here I'm just saying humidity is calm water vapor. We call that the pickup. And the idea is, okay, if we want to see how models are looking, we can kind of come up with some metric, and we can kind of just fit a line to how rapidly the precipitation picks up. And we can just say where it crosses the calm water vapor axis, and we can say, okay, that critical value here is around 60 millimeters. And now I can do that with a bunch of different models. So this is from a paper I published in 2022. And this is from the latest generation of the CMIP project models. And here I have them ordered. The colors are the models, and the black lines are kind of observational products and a mix of satellite data and whatnot. But the important thing you need to look at is just they're in an order of their pickup value. So kind of the estimated where they start to kind of ramp up and really increase their precipitation. And you can start to see that a lot of the models, a lot of the colored lines start to kind of pick up or increase their precipitation a lot earlier than observations. So there's this bias here that models are kind of raining too quickly. And there's been some idea or some earlier work that's looked at the CMIP5 models, the last generation. And they said, okay, models have this drizzle problem where they kind of rain too frequently and at too weak of a rate. So if we think about that, it's like, okay, maybe the models are just raining too frequently at too low humidity. Maybe this is why they're starting to increase their precipitation a little earlier. Well, actually, he was able to, in this paper I published in 2022, along with some other people at the Department of Energy and Lawrence Livermore National Lab, I was able to actually find that, okay, actually, a lot of these models have a large temperature bias that accounts for this error. So if we kind of normalize the calm water vapor, the humidity, by its temperatures, we kind of get it in terms of calm relative humidity. Just think about being at 100, you're at saturation, kind of we mentioned earlier. You start to see that, okay, well, now the kind of observations lie in the middle of the pack. And there's a bunch of models that kind of lie a little before and a little after the observations. So they're doing actually very well compared to how they did in the CMIP5. Some earlier work showed that the CMIP5 models actually all picked up much earlier. But now it looks like in the new generation of climate models, they're starting to increase their precipitation a little too late. So our question is like, what errors kind of persist? So now this is some very, if you're familiar with probability theory, this looks pretty nice to you and easy, but if you're not, it's okay. This is just the law of total expectation. And basically, it just says that your average value can be decomposed into weighted averages. Here, we have the pickup or the kind of average precipitation as being the product or the sum of the mean rain during raining times the probability of raining plus the mean rain during non-raining times the probability of not raining. And you might notice I just said the mean of non-raining times not raining, and that doesn't make any sense because this is nearly always zero. So you can kind of delete this term and you get that the pickup or the increase in precipitation is really just something I like to call the conditional intensity. So how strong your precipitation is when it's raining times the probability of actually raining. I'm going to decompose this here in those plots we looked at in a second. This allows us to kind of view these biases in climate models as biases either in a raining regime, so the sensitivity of the intensity and precipitation to moisture, or a non-raining regime bias, which is kind of the frequency of convection, how often your convection is kind of shooting off. And we can kind of see, okay, if you hold one constant, you can notice if you just have a constant intensity and you just increase your probability, you can get a quick increase, and same vice versa. So we actually kind of look at how these look like in the climate models. We start to see, okay, on the left is the pickup we were looking at earlier. It's really kind of the product of two other rapidly increasing quantities. The conditional intensity starts to kind of increase rapidly, and the probability of raining increases rapidly as well. But the climate models look a lot different than the observations. Remember, climate models are the colored lines, and the observations are the black lines. You start to notice there's a later pickup in intensity between the models, and they often initiate convection too often at too low calm relative humidity. So what this is telling us is that there's low intensity rain, and it's happening too frequently, which indicates that drizzle is kind of still a problem in the latest generation of global climate models. So models are able to reproduce this pretty good looking pickup here just by compensating their insufficient sensitivity to moisture. So in the raining state, they're not really raining too intensely with increasing humidity, by just raining more often. So it's really important to kind of understand the physics and kind of dive into the model diagnostics so we can really understand where models can kind of be improved. And actually, it looks like they might be doing well at first, but this is actually a very good tool to help modelers kind of improve how well their models simulate climate processes such as convection. So far we've talked about saturation vapor pressure. That's going to increase 7% per degree warming. Okay, that's the first thing we talked about. Clouds are going to continue to go up in the atmosphere. They have enough moisture. If they can keep condensing water vapor and turn that into liquid water, which can in turn stop it from cooling too fast. And global climate models simplify cloud physics using these parameterizations. And as we just saw, models drizzle too often, but they still capture these important correlations between convection or between humidity and precipitation. And that is the precipitation rate ramps up rapidly once some critical humidity is reached. So I'm going to get into the future of extreme precipitation. And all of these slides are from a class I taught at UCLA with Professor David Nealon. So here, heavy precipitation events, they're dominated by moisture convergence, or kind of this vertical transport of moisture. And you can think about it as precipitation in that way. If you think about kind of a very large convective event, is really just the vertical average of moisture convergence, how much moisture is being transported up through your column. Convergence, for those that aren't aware, is just kind of an accumulation of air in the lower atmosphere, and it has nowhere to go, so it has to go up. So you start to transport the water vapor up, a lot of water vapor, and it eventually condenses, forms clouds, and you get rain. And that's really kind of the factors that set these really intense storms. So if we think about the future of extreme precipitation, pretty much the factors that kind of set convergence, they say roughly similar in the future. Extreme precipitation can be thought to increase according to increased moisture, so otherwise around 7% per degree warming. And this is, of course, us taking the assumption that the dynamics are really the only thing kind of driving, or the dynamics are staying constant between now and future climates, which might not be the case. And I forgot to put the source here, but this is from Heldon Soden from 2006. So when we kind of look at how models, we can take the strong precipitation events, so the 99.9 percentile changes, and we can compare it between the historical climate run between 1980 and 2009 to the statistics between 2070 and 2099. So this is a future run, the most intense scenario when we kind of just continue business as usual. And these are from two different climate models that kind of have really similar climate parameterizations. One is the Community Earth System Model 2, which is kind of built and programmed here at NCAR. And the other one's E3SM, the exascale system model that's built at the DOE. You can kind of see, okay, well, according to this theory we just presented that says they increase around 7%, which is this light green, the E3SM model looks like it increases the precipitation about that rate, what we expect, besides the exception of this little part in the Pacific, whereas the CSM model kind of is all over the place in terms of where it increases precipitation. Oftentimes you get these departures well above what's expected, or above 7% by the Clausius-Capeyron or saturation vapor pressure relation. So the question is, like, what's really going on in these models? There's a lot of regional variability, and it's possible that those factors of convergence I was talking about are actually changing in the future. And if so, how do those change, and what will the future precipitation look like? And more so, where will these, what regions will be most affected by increases in extreme rain events with warming? And so really we need to come up with some diagnostics, need to kind of narrow down which regions can expect most intense precipitation events, so we can kind of better prepare ourselves and prepare for mitigation efforts in the future. And that's my presentation. I just want to kind of keep this up because I thought it's a pretty cool slide. It's fun to look at maps. I mean, though it is extreme precipitation change is a little dire. Yeah. Thank you all.
Great. Thank you so much, Todd. That was wonderful. And we have some questions in the chat. We'll start with, so there's one early on question asking for what is a clarification about what is a parameterization. And I think there actually was some discussion in the chat then helping answer that, but do you want to maybe discuss a little bit about what a parameterization is and maybe elaborate a little bit too on like what's so unique about the CMIP approach to kind of collaborative science and comparisons?
Yeah, of course. So parameterization is basically, where was that slide? So you're kind of trying to describe the effect of these clouds in this grid box without actually running a simulation of the clouds in the grid box. So you need to come up with some simplification. Some convective parameterizations kind of are similar to the plots that I showed earlier, the pickup plots, which is that once kind of this critical water vapor is reached or some value of humidity or relative humidity, you start to convect and you start to kind of reorganize the boxes in the vertical and the column and the grid. So it's kind of just a way of simplifying a bunch of really complicated processes of what you expect to happen in those big grid boxes on smaller scales. And then I think, Becca, you asked about, you wanted me to elaborate on the CMIP project?
Yeah, just how kind of the overall, how that sort of, how that fact that you need to parameterize a lot of things then fits into this idea of comparing different models that have slightly different approaches. Do you want to just comment on sort of like, it's such a unique, well, maybe not unique, but cool way that lots of different science communities come together to try to compare their different models.
Yeah, exactly. So the idea is that if you're kind of able to have your own unique way of representing these subgrid scale processes that are affecting, the climate system is very nonlinear, right? So these small differences in the subgrid scale or these parameterizations should have a large effect kind of on the total climate. And the idea is that if you have these kind of parameterizations that are working in different ways, but some of your results remain robust, or a lot of models kind of agree on it, you can say, okay, this is a pretty well agreed upon thing that's likely to happen in the climate system, no matter how you represent some of these smaller processes. It's kind of like the law of large numbers, where you kind of just average together a bunch of different outputs and you expect to kind of get the real answer. That's almost what I kind of view the CMIP case being like. You're kind of averaging a bunch of different model outputs and you're kind of going to get the mean of that should be somewhere close to what you expect. And I think going back to funding and things like that, I think it's been really important because the diagnostics that I've been able to produce at UCLA and here at NCAR have been really important and integral towards like improving climate models all around the world. It's really part of an international effort to understand our climate system and how to better prepare for it. And I think it's something that's really beautiful, actually, in terms of scientific collaboration that you don't really see in a whole lot of other fields.
Awesome, thanks. Next question from Michael Evans was, would the errors in modeling convective precipitation decrease if we could have finer resolution, like smaller grid boxes in your model?
Theoretically, yes. Theoretically, if you were to actually resolve these cloud systems, you would be able to turn off the parameterizations and just have basically a bunch of little boxes kind of reorganize themselves in the vertical, and you wouldn't have to simplify the process. So yes, the models should be better. The convective precipitation errors should decrease, but the problem is that there's the way the equations are linked, kind of the different boxes are tethered together. You really aren't sure if it's actually going to have a better output, because a lot of the times the parameterizations are kind of tuned or kind of nudged a little bit so they look more like the observational output. So actually, I worked with this data set last week that was really high resolution, where they kind of got rid of the convective parameterization, allowed everything just to kind of convect, as you were saying, without the parameterization, with a really fine scale. And I was looking at the climate model output, and actually looked pretty promising. So there is a lot of effort going in towards increasing the resolution. The other thing is that a lot of times the computational power needed to run that model at such fine resolution is going to take longer than what you actually want to simulate. So it might take more than 100 years to simulate 100 years of climate. And in that case, it wouldn't really be worth it. So.
Yeah. Okay, there's also a question. How much of the drizzle problem is a matter of apples and oranges comparison between gridded and point precipitation?
Yes. So when I look at, for example, this drizzle problem that happens between these models in the observation. So I guess by point precipitation, we're talking about kind of like what the observational product is. If it's a rain gauge and it's actually measuring precipitation in situ. So I actually take the trim satellite precipitation. And so the solid line here is the ARM data. So it's an in situ product kind of measuring on the island, combining it with the satellite precipitation. So I'm actually averaging over different domains, and it really doesn't have a large effect. So we've tested this in this paper in 2022, and we found that really the results are pretty robust no matter what the spatial resolution of the model is.
Oh, interesting. Okay, we have a question. Can you briefly discuss how the history of the current scientific paradigm around climate modeling has been reached?
the history of the paradigm of climate modeling.
That's a
That's a big
hard
question.
question for 2 minutes, but how do we arrive at these climate models?
How do we arrive at the climate models? I think the first one was made at Princeton by Manabe, I think. And he won like a Nobel Award for it,
Yeah.
I believe in the 60s. And that was like a single column kind of simulating climate. I don't really know how we got here. It seems like if you try to
rather than making you go through the whole history, can I ask you a slightly different question, a variation,
yeah.
which is, you talk about model observation comparisons that you do for diagnostics. Are there certain observations you kind of have like on your wish list, things that we don't yet have, but if we could get, maybe are achievable, that you think would really improve your ability to test these models?
Yes, yeah, actually. So my boss would be proud that I'm going to, or my advisor, that I'm plugging my current project in called the Inform project, which is integrating field observations, research models, and we're using aircraft data to kind of come up with these diagnostics, which is something that really hasn't been done before. So the goal would be like aircraft data would be amazing because you have aerosol data there, and we can kind of dive more into microphysics in convection. Microphysics would be, the little cloud particles actually forming. And then also there is a satellite product called Cosmic 2, and it has amazing coverage, pretty much it takes 5,000 really high resolution vertical profiles a day. And it's great. The only problem is there's some errors that's still kind of in the retrieval in terms of how the product is done. But I think kind of using more high resolution or having more vertical observations, like high resolution vertical atmospheric profiles from satellites, along with aircraft data would be ideal. And those are kind of like the holy grail right now of model diagnostics.
Awesome. We just have one final minute, and so maybe I'll end with the question, what got you into your specific field of research from SAGE?
Yeah, so I actually, this is another really good story, I guess. So I was kind of lost in undergrad. I went to University of Georgia. I didn't know what I wanted to do. I wanted to get into like some kind of climate research, but at the time, or do myself. So there was no atmospheric or meteorology program at University of Georgia at the time. So I was actually able to apply for some outside internships, and I was able to do research experience for undergrads. It's like an internship put on by the National Science Foundation at Penn State. And there I got to work with some great scientists, Michael Mann, Jenny Evans, and Gregory Jenkins up at Penn State. And I was able to work with these hurricane data sets, these like simulated climate model tropical cyclones. And I was, as an undergrad, I was just going to play with data first. And they got me really into kind of like tropical meteorology and convection. I decided to study math at the time, and I really enjoyed doing the math there. And I got into this kind of research because my advisor at UCLA was really into stochastic modeling. So kind of like, random forcing and kind of shooting off clouds and convection and things like that. And that's something I wanted to do. So I got into the research just because I enjoyed the math, and I thought it was something meaningful to do for society. Yeah.
Cool. Well, thanks. Thanks so much for being here and for sharing your research. And we're on the hour now, so I'm going to actually be passing off the hosting duties, I think, to Margaret Duffy, I believe, who will hopefully be on in just a second.
Oh, hi.
Hi, Margaret.
All right, let's all thank Professor Becca Jackson for that amazing job of hosting. Hearts for Professor Jackson. So we have a really exciting talk coming up. Before I tell you what that is, let's just remind ourselves why we're here. So let's see, we're entering, I think, hour 53, is that right? Of 100. 47 to go, but I think if you round 53 to the nearest 100, you get to 100. So does that mean we're done yet? I don't know. And okay, so before we get to our next speaker, we want to talk about why weather and climate forecasts are so important. We all rely on our weather forecasts every day, and a lot of decision makers rely on climate model projections. The climate's changing faster than ever, and so if we want to enter this new era with good information, we need those climate model projections. And weather forecasts and climate model projections have been improving steadily over the last couple of decades. And a lot of that is thanks to research we do right here in the US. And a lot of that research is funded publicly. So so it's a really great achievement, but it's being threatened right now, unfortunately, by funding cuts. And if we want to keep seeing these improvements in our weather forecasts, improvements in our climate model projections, we really need to make sure that these cuts don't happen. So there should be a little link rolling across the bottom of your screen where you can call your representative and let them know how you feel about weather and climate science. That's optional. We mostly just want you to learn something. But if you like what you see, please do that. All right. So next, I'm going to welcome Hannah Joy Warren up to the screen. Hannah is a polar oceanographer, and will be talking to us today about the Southern Ocean, what it is, why it's important, and why there are phytoplankton there. Take it away, Hannah.
Thank you so much, Margaret. I am Hannah. I'm a postdoctoral scholar at the University of Washington, but I also sit at NOAA's Pacific Marine Environmental Lab here in Seattle. And I just first off want to mention that I can only do any of this with public funding. My postdoc is funded by the National Science Foundation, and my previous postdoc was funded by NOAA. So I for my research, I depend on this. And I'm going to introduce you to the Southern Ocean. If you haven't met the Southern Ocean before, it is a fascinating place, and I hope to convince you of that. And then we're going to talk about phytoplankton a little bit and what they are doing there. Surprised they are there, if you didn't know that. And all of my science is in situ data. So I'm looking at data from the water in that place. But the overall goal of all of this is to be able to get better information to put into these models. So we can't model the climate if we don't understand what's happening and especially where is the carbon. So that's one of my big questions, to be able to provide some information for modelers like Todd, who you just heard from, to improve models. All right, so we're going to do a little bit of background first. Here we have the ocean, a sun, and in the ocean we have water. I probably don't need to tell you that. But we also have carbon that starts in the atmosphere, and that carbon can move from the atmosphere into the ocean. And this is really the key point here, is where is the carbon, how much is in the atmosphere, and how much is in the ocean. And our phytoplankton are going to help determine one piece of this. So water combined with carbon, that C there, undergoes photosynthesis, and that is how we build our phytoplankton bodies. This is organic carbon. So the carbon that was just CO2 in the atmosphere is now in the bodies of our phytoplankton. So these are photosynthetic organisms like land plants. They're growing through photosynthesis. They can die and sink to the bottom, and I just put a little blob here sinking down, and they take their carbon with them. This carbon is called particulate organic carbon, or POC, and you don't need to remember this very much, but just putting it out there. So sometimes the phytoplankton will die and sink down, and they'll take that carbon with them that's in their bodies. They're also eaten, which we'll talk about briefly later, but we're not worrying too much about getting eaten. And they can also undergo something called remineralization, which is little bugs, microbes in the ocean can eat on that organic carbon, just like we have things on land that take apart a fallen tree log, that it can eat it up and use that carbon. So remineralization, and then that carbon is put back into the ocean. We call this dissolved inorganic carbon, which is what it is when it moves from the atmosphere into the ocean. This is just if it's not in somebody's body, it's not organic, it's not poop or mush or anything like that. It's inorganic carbon. So the one key to remember here throughout my talk is that dissolved inorganic carbon is what we care about. And we care about if it's in the atmosphere or if it's in the ocean. And we're trying to understand how phytoplankton determine if it's in the atmosphere or ocean. So this is your photosynthesis background and the couple of key terms there. Now I will introduce you to the Southern Ocean, which surrounds Antarctica, and I have a map later. I should have put a map earlier. It's far away. It is very remote. It is such a cool place. And here's a little diagram that I made, and I'll just label some parts of it. So this medium blue color, the light blue is the atmosphere. The medium blue is the surface of the ocean. So that's something that can exchange carbon with the atmosphere. Then we have our sea ice to the left here. That's ice covering the surface of the ocean, which is important in the Southern Ocean. We won't get too much into that, but I will tell you a little bit more about sea ice. We have the deep ocean, and the deep ocean can't really give things to the atmosphere back and forth. It's too far. It's separated by the surface ocean. So if we get carbon into the deep ocean, we call that sequestered. And that's like out of the system for about 1,000 years. We have the ocean floor, where if our organic carbon sinks down there, that's excellent. That is out of our system. And then we also have the continental shelf back over on the left here. And so this is kind of like closer, more surface water. This is where a lot of the activity can happen that I pay attention to in my research. So now that we know the parts of this diagram, I've thrown up a phytoplankton bloom in green here at the surface of the ocean where it can get sunlight and photosynthesize. And in the Southern Ocean, we have high but very episodic production on this continental shelf. Episodic meaning sometimes it's happening, sometimes it's not happening, which is another very interesting thing to look at that I focused on in my PhD. Now we're just focusing on that it's there. So 30% of organic carbon of the whole world, and I was telling you earlier, this organic carbon is in bodies, in phytoplankton bodies, in fish bodies. That's all organic carbon in poop. And 30% of that, of what happens across the whole world, is in the Southern Ocean, moving from the surface to the deep. So that's a huge fraction there of thinking about where the carbon is on our planet. Then, and this is a really cool, interesting physics part, we have deep water mass formation. Here's where the ice comes back into play. So as ice forms, that's just water. It's just H2O, makes ice crystals, which means it rejects the salt. And when you have very, very salty water, that's called brine. So that gets rejected, and it's super salty. It sinks to the bottom because it's really dense. And we call this downwelling. And so that kind of mixes the surface water down, and then it can flow down off the continental shelf into the bottom of the ocean. And again, that water at the bottom of the ocean stays down for about 1,000 years. So this is like really taken out of the system for timescales that we're thinking about right now. And that water that started in the surface with phytoplankton has very, very high organic carbon. So now we're taking our organic carbon really out of the surface ocean and atmosphere system. And remember, we have a lot of high phytoplankton blooms. We've got a lot of this carbon. And that makes the Southern Ocean a potentially very large carbon dioxide sink. I've got CO2 here I had it in yellow earlier here. It's in these kind of light blue bubbles. And so if we're taking carbon out of the surface ocean, that means more carbon can dissolve from the atmosphere into the surface ocean to turn into organic carbon. So in the Southern Ocean, there could be a lot of this carbon moving into the ocean, which means that this will influence global climate. So it's happening at such a scale that anywhere on Earth, we could have less carbon in the atmosphere, which will lead to less global warming, less heat trapped near the surface. So what's happening in the Southern Ocean really determines what we experience at the surface of the Earth anywhere in the world. So now you know why I love the Southern Ocean so much. Here's a very similar diagram, but I've divided it up a little bit more. So we have waters. You don't need to worry about the names of these water masses too much, but we have waters that flow from the north towards the south. So the right side of this figure is north, the left side is Antarctica all the way south. And in those waters, they cool, and cold water takes up more carbon. If you think about a soda or a pop, if it's warm, all the bubbles leave, and that's not so tasty. If it's cold, it can keep more of the bubbles. That's carbon dioxide bubbles right there. So we get carbon uptake there from the atmosphere into the ocean. But these middle waters, they're called intermediate and deep waters. These are coming up from depth. So actually, they're really old waters that have taken carbon throughout their life of going through the ocean. So some of these old waters are coming up. And like I said, Southern Ocean waters will come up somewhere else in 1,000 years. These waters are coming up. So they have some carbon in them, but it's about 50-50 of how much carbon goes in and comes out in that region. So overall, we have more carbon going in, but some of it does come out. And then there are a lot of physical processes that affect this. This includes ice cover. So sometimes we think about ice as like saran wrap over the surface of the ocean. There's not a lot of transfer across it. We have wind. So if you get big waves that are capturing bubbles, those bubbles put in actually a lot of carbon and oxygen, anything that's in the atmosphere, into the ocean. We have mixing. So if you think about, waters are just stirring up and down sometimes, that will affect where our carbon is. And then salinity and temperature also affect, as I mentioned, with temperature. Thinking about a soda, salinity also affects this kind of in a similar way. So we actually, as scientists, know a lot about these physical processes. I didn't do any of that work. That'll happen before I entered this field. What we don't know a lot about is, I just put up my phytoplankton bloom here. Here's my phytoplankton that I really, really love. So how these organisms are photosynthesizing is using carbon. We know that in general, but we don't really know the details of that. And it's kind of a black box, and it's like biology happens and it uses carbon. But I really want to dig into that of what's really happening. So again, similar diagram. Now I'm going to talk you through the parts of my work of how I get to this question of what's going on with the phytoplankton. So I've popped this back up here. We've seen this. We have our physical processes on the left, biological processes on the right. This is the black box that I'm going to try to open up. And then we have our carbon transferring from the surface into the ocean. My overall research goal is to determine the relationship between phytoplankton community composition and air sea CO2 fluxes. And this is the project I wrote to NSF with. And I said, will you fund me? I think this is really, really cool. I think it's really important. We should figure this out. And they said, yes, we agree. Go figure it out. So the first piece that we'll need to do is characterize the Southern Ocean phytoplankton community composition. So who is there? What's going on with this phytoplankton? We need to look at that. And then we need to look at the carbon fluxes, how the carbon is moving from the surface from the atmosphere into the surface ocean. We call that air sea CO2 flux. So where that carbon is going back and forth. And then I popped up this yellow thing that might look really funny. This is an Argo float. They are really, really cool tools. Here is me standing next to one. I'm 5'4", so I'm pretty short, but it's like about my height if I put my arm up, so you can imagine. This is a black one, which has a certain type of sensors, and then the yellow ones behind me have another set of sensors on them. This is at the campus of the University of Washington, in the building I'm sitting in right now, and they're getting equilibrated to the air. So these are like real instruments that are already in the ocean now. This was a year and a half ago, this picture. So these instruments, they're called Argo floats, and the black ones that have more of the biology information are called BGC, for biogeochemical Argo floats. And you deploy them, the top left of this figure, number one, off the side of a ship. We go out in the oceans, deploy them. They go down to 1,000 meters and they hang out there for 10 days, just drifting with the currents. And then they'll go down to 2,000 meters. Sometimes they go all the way down to 6,000 meters. The ones I work with go to 2,000. And then they profile all the way up, which means they're taking measurements all the way up. And you can see what that looks like on the right side of this figure. So there's temperature in orange, salinity in pinky purple color. And then we can get measurements all the way to the surface. And then that little antenna that you like, that little thing sticking up there, it sticks out of the surface of the ocean and satellites back the data. So we can get this near real time, which is amazing. And then we get this incredible data across the oceans. So I can look at carbon this way with these tools. And there's my little graphic that I made of them. So I'll put this on the slides when I'm showing BGC Argo data. So back to the overall picture of my project. Step one, we're going to look at the phytoplankton community composition. Who is there? And a little overview of who is there, why we care about it. These are pretty much all pictures that I took when I was in the Southern Ocean in Antarctica. There's a seal looking over to see what's in the water. And we have two main types of phytoplankton. On the left, we have diatoms, and those are pretty. They have glass shells, gorgeous. On the right, we have Phaeocystis, which the actual cells are the tiny little dark dots, and then it's in a mucus matrix. So it's like, makes this gummy stuff, just kind of like our mucus, that's full of carbon. It's entirely made out of carbon. The glass shells are made out of silica, not carbon. They have carbon in them, but they're not quite as carbon heavy. So things eat the diatoms, krill, copepods, and those feed the upper trophic levels, all the big, beautiful birds and seals and fish that we think about when we think about Antarctica and that we love. And Phaeocystis is very stinky. It smells like sulfur because they also have a lot of sulfur processing. They're eaten only by something called salps, which are kind of like jellyfish, and they salp poop and they make really heavy poops. And so all that carbon sinks out and they're not really eaten by things. They don't really stay in the ecosystem. So important to think about which is feeding things and which is going to the depth of the ocean. And then another detail, this is a paper by my PhD advisor, and this paper is what got me on this track that I've been like curious about this for very long. I didn't read it when it came out because I was not in the field then, but here we have Phaeocystis and diatoms. You don't need to worry about the data at all, but for any amount of nutrient, which is like other things that they need to grow and live, just like how we have to eat food, Phaeocystis uses twice as much carbon, which is on the y-axis there, as any other nutrient. compared to diatoms. So Phaeocystis is using way more carbon. So this is why I think maybe it depends, maybe who's there really matters for where the carbon is. And so we're going to look into this. This is a database of where somebody on a ship has gone and measured and looked at phytoplankton and said, who is there? The little gray dots are where we have all these Argo float measurements. And I will just note that these are not in the same place. They are not at the same time. And so this is like kind of a mathematical challenge to figure out how do we merge the information of who is there for phytoplankton and what the carbon is looking like. So I'm not going to get into details of the methods here, but they're really, really cool and fun. We use another model called Biogeochemical Southern Ocean State Estimate. So they take this Argo data, they put it in, and then they extrapolate what the fields look like. We take that with our actual real in situ observations, and we do machine learning called maxent species distribution modeling, which is a very fun, cool technique. And then we can map where we have our taxa. So on the top, I put diatoms, and I put a little diatom picture to remind you which one's diatoms. On the bottom, we have Phaeocystis. And then our color bar here is how likely is it to be present. So if it's dark blue, like we see outside of the diatoms, not very likely. If it's bright yellow, it's very likely. And here's finally our maps of Antarctica. And just to orient you, if you look kind of towards the left, kind of towards the top, that's South America. If you look all the way at the bottom, you can see New Zealand, but really it's like just ocean here. So we've characterized our community composition. Great. Now we need to look at our air sea CO2 fluxes. I grouped our float data into two groups to look at places where I grouped these using a different machine learning method where we have very similar chemistry and physics, so that if we see a difference, we can say it's probably biology. So we have our two groups, and then in the more southern group towards the continent is this blue color, which is called the sea ice zone and the Antarctic Southern Zone. Don't need to worry about their names, but the blue one, high DIC. We have high carbon in the water. The pink one, we have lower carbon. Don't worry about the numbers at all. It's just the relative difference. And then these are significantly different. So we have our carbon. Now we need to tie this all together, which is the fun part. Back to this slide that we just saw, where we have higher carbon in the blue one closer to Antarctica, slightly lower carbon as we go further north. And we have our phytoplankton distribution. So we have these same maps, look, same exact map. We have the points where we have carbon, and then we have a full map of where we think that we have each of these two phytoplankton taxa. So we can divide up the groupings of carbon based on which taxa is most likely to be there. So when we do that, this is like the really cool, fun, punchy result. Here we go. Get excited with me. Diatoms are in teal on the left side of this chart. Phaeocystis is in magenta on the right side of this chart. And then they're divided into the two buckets of the two regions. So within the bucket, we assume chemistry and physics are about the same. So if there's a difference, it's probably biology. And so we can look at the poleward one, sea ice zone and Antarctic Southern Zone, the blue column. There's no difference. That's not significant. The means, which are the thick lines, totally the same. If we look at the more northern region, the pink region, there's a huge difference. So when we have Phaeocystis present, we have much lower carbon. We have diatoms present, we have much higher carbon, which to me says that Phaeocystis is using the carbon from the water to make its bodies, really to make the mucus that it lives inside. And then we know that that is eaten only by salps, and then they make poop, fecal pellets, that sinks out. So this is super, super important in thinking about where the carbon is. And historically, scientists have said, oh, biology photosynthesizes all, uses the same carbon, and we put that into models. And I'm pushing to put in more details to say, not just that we have phytoplankton, that photosynthesis is happening, but who is there? They're using different amounts of carbon, and that will mean different carbon left in the surface ocean. That means different amount of carbon to exchange with the atmosphere. It means different amount of carbon down to the depth where it's sequestered. So this is the project that I've been working on. There we check. We did determine the relationship. Here's the overall picture one last time, all of the pieces that we put together to get there. And then just to conclude, I want to reiterate that the first part of this project, when I first started working on it, I was doing more of the machine learning stuff. That was funded entirely by NOAA. And the second part of this project has been funded by the National Science Foundation. As a postdoc, as a graduate student, I was funded by the Environmental Protection Agency because Phaeocystis is also a harmful algae and can cause destruction in some places. So I just want to put out there that all of my work has been publicly funded. I think it's super important work. I think it's really, really cool. And I'm just so appreciative that you're all here to hear about it. And I would love if anybody has any questions.
Thank you so much for that super engaging talk. I loved that, and I learned a lot because I haven't thought about this since I took it in school. Okay, we already have a bunch of questions in the chat. We have one here from Stephanie Henderson. Given the importance of the Southern Ocean, why do we have such a large lack of observations in that region?
That's a fantastic question, Stephanie. And I'm going to ask everyone listening to imagine themselves going to Antarctica and how far you would have to fly. When I've gone, I get on a ship in Chile at the southern tip of South America, 2 to 3 days crossing the Drake Passage, which is the roughest waters in the world. When I was there were 30-foot waves. Everybody's seasick. You finally get down there. I took one cruise, research cruise where we do this work, but we went all the way around and then up to Australia. So we went under the Pacific. That took 70 days. So I was out there for almost 3 months, and we are in freezing temperatures, breaking through ice with our ship. It's very hard to get instruments down there, and it all is extremely expensive. So it's the hardest place to get to in the world. And because of that, it's just really hard to get data. And that's when, so my PhD, I went down there and measured all of these things. Physically, I was there. I switched over to these robots, the floats that do these profiles, because it's so much easier to get way more data. But it's just really hard to get there. I agree, it's incredibly important, and we need more observations, and especially things like robots that will go down there and do it for us, because you can get like a lot more bang for your buck. You can way more data for the cost of the instrument.
Yeah, that's so cool that you've been down to Antarctica. And shout out to the Argo program. That's such a fan favorite. Has been for the last 53 hours. Okay, so we also had a question about ocean acidification and how that kind of interacts with what you've been talking about.
This is a great question. So the organisms that I've been talking about don't use calcium carbonate to build their shells, which is things like corals do. There's another phytoplankton called coccolithophores that do use calcium carbonate. And so just think of like the coral skeleton is what calcium carbonate is. And that's what's really affected by the acid. So it makes it harder to build your body if all your materials are getting stolen by those hydrogen ions. It's really hard to build your body. But if you're building your body out of silica and the hydrogen ions don't care about silica, then it doesn't affect you very much. Same with Phaeocystis. They're not using calcium carbonate. And so there's not a huge amount of calcium carbonate organisms that are this far south. If we're thinking more of the tropics, we have way more. If you're getting north in the Southern Ocean, so north of about 45 degrees south, which cuts just cuts through New Zealand, if you can imagine, like cutting off half of New Zealand and then north of that, that's where we get coccolithophore. So it would be way more important in those regions, but those are the regions that are less important for carbon flux from the surface to the depth. So also a super, super important question, just not as relevant for the things that I'm thinking about.
Awesome. We have a ton of interesting questions here. So we have one about phytoplankton blooms from another Hannah. Will climate change cause an increase in episodic phytoplankton blooms?
That's a great question. Climate change is changing things in many different directions. So when we add up something going up, something going down, it's like whichever one is bigger, and that changes regionally at pretty small regional scales. So in some cases, yes, if we get less ice cover, we'll get more light, which means we can have more phytoplankton growth. However, at one point, I briefly mentioned nutrients, so like things that they also need to grow their bodies. That tends to come from the depth because it's from rock. So water that's touching that rock that can bring that up, or from other remineralization. So when the microbes eat up the phytoplankton, they release their nutrients back too, which tends to happen at depth. So we need water to come up from depth to provide that for the phytoplankton. And with climate change, probably less water is going to be coming up. It's going to get more stratified is what we call it. So much warmer at the surface. And when it's like really warm, it's really light water, and really cold is really dense water. And those are much harder to mix. So it's like mixing oil and water versus mixing, I don't know, like jam and water. That's like kind of easier to mix that in together because they're more similar. So we'll probably get less nutrients coming up, which means that in that direction, we'll have less phytoplankton blooming. So it's kind of a guess right now. And that's one of the great things about models is we can put in our guesses and see what might happen in the future. But we need to figure this out, and we just need more observations and more time to understand how things are going to go in the future.
Awesome. So we have a question about how you got interested in this. And there were some conversations in the chat, I think, about somebody's kid who might be interested. I don't know. I wasn't totally paying attention, but maybe you can tell us about how you personally got interested in what you do.
Yeah. If you have a kid who's interested, send them my way. I'd love to chat with them. I was always interested in water as a kid. I grew up in multiple different places, but had spent a significant amount of my childhood in Ontario in Canada, and on the Great Lakes, where I saw firsthand things changing. And as a child, that was horrifying to me, of like, I could grow up and we could lose the amazing beauty that we have. And so I wanted to understand climate change. I really liked water. The previous speaker mentioned doing an REU, which is a research experience for undergraduates, which I also did one of those. One of my college professors pushed me into it and said, go figure something out. And I applied to 3 internships. 2 were on the Great Lakes because I thought I loved the Great Lakes. I was also in school in Chicago, so I was right there on Lake Michigan. 1 was oceanography because I thought the ocean's just a big lake, right? Like, it's kind of the same. The only one I got was the oceanography one. I learned that it is not just a big lake. It's quite different. And I was doing a modeling project then on the Southern Ocean, and I got to write in 2 different types of phytoplankton. So a lot of what I do now was sparked by a professor who told me this was a cool thing to do and taught me all about it. And I still have a scientific relationship with him, but that really set me on my trajectory. I also love exploring. I love traveling. I love photography. Like, getting the chance to go to the Antarctic was amazing. And in my PhD, I worked in the Arctic too. So I got to go to each place twice. It was just really fun. And it's really cool questions. And like, the idea that we don't know this and I could go figure it out is fascinating. And I've just always really loved the people that I worked with too. So following the fun people doing the fun work is how I ended up here.
Amazing. Okay, that was awesome. Thank you so much, Dr. Joy Warren. We have a really exciting talk coming up next about climate change and air quality. But before we do that, let's talk about why we're here, just as a quick reminder. We are in hour 53 of our 100-hour live stream. We really hope that you all are learning something, and we're here first and foremost to share with the public what it is that we do, and as weather and climate scientists. Weather and climate forecasts are super important. I think you can see that in your weather forecast when you open up your phone and you check the forecast. And the same is true for climate forecasts, climate projections. Even though it's maybe not as widely used by the average person as a weather forecast, climate projections are super important for decision making as we, for example, build buildings that we want to last for decades and that type of thing. We need to really have some sense of what the climate is doing. And the US has really been a leader in this area, and a lot of that has been publicly funded. And so we want to thank the public for their contributions to this science that we're all benefiting from. But unfortunately, right now, there are a lot of funding cuts that are impacting the ability to do this research. We're already seeing impacts on our weather forecasts. Unfortunately, we're not collecting as much data for our weather forecasts as we were a few months ago, and we're also seeing some staffing issues at the National Weather Service. So if you're concerned about any of this, if you like what you see here, please call your representatives. We have a little script that you can read at wclivestream.com/act. And we really, really appreciate all of you for being here, for listening, and bonus points if you call your representative. So coming up next, without further ado, let's move on to this next speaker. I don't want to take any more of your time when we could be learning about CTDs. So we have Dr. Andrew Thaler, an deep sea ecologist, conservation technologist, and ocean educator. Take it away.
All right. Well, thank you so much for that introduction and for hosting all of this. This is really an amazing experience to get to be a part of. So I am a deep sea ecologist. Most of my work and my research revolves around how technology impacts the deep ocean, primarily through deep sea mining, but also in terms of things like microplastic accumulation in the deep sea, or the effects of noise on deep sea species, or the impacts of ship sonars, or dredging, or bottom trawling. So I'm much more of an ecologist than I am a climatologist, but I'm also a little bit of an oceanographer. And through my work in the deep sea, I got really connected to marine technology, and in particular to this really tricky question of how do we make marine technology, the tools we need to make these primary measurements to understand how our world is changing, how do we make those tools available and accessible to the vast majority of ocean stakeholders, of ocean knowledge seekers who don't have access to things like capital equipment and research vessels and the kinds of tools that until very recently were only available to the wealthiest governments on the planet. And kind of the most important tool in the kit of all oceanographers is this humble little device called a CTD. So a CTD is an oceanographic instrument that measures salinity, temperature, and depth. It actually measures conductivity, but we use that to calculate salinity. And so it tells you kind of the basic parameters of what's happening in a water column. It tells you how deep you are in the water. It tells you what the salinity is throughout a water column profile. It tells you the temperature of the water. These are all kind of the essential foundational measurements we need to make for really any kind of marine scientific research. So if you're an ecologist studying dolphins, you're going to have a CTD, and you're going to do CTD casts to understand what the water body looks like that you're doing research in. If you are a chemical oceanographer, you're going to be doing CTD casts to understand what the water body looks like that you're doing things like measuring chlorophyll content in. Is if you are a sonar technician, if you are just doing like side scan sonar work, you need to do CTD casts so you can understand the density of the water column that you're working in, because that density changes depending on things like salinity, temperature, and depth. And that allows you to calculate the speed of sound in water, which then allows you to calibrate your sonar so you can get an accurate picture of the sea floor. So CTDs really are this kind of foundational, essential piece of equipment. If you want to do any kind of marine scientific research of any sort, anywhere in the world, you really need to have access to a CTD. And the problem with that is that CTDs are very expensive. So this slide just shows like a selection of different kinds of CTDs that you might encounter. Several of them, especially on the top, are CTDs attached to what's called a rosette, which allows you to take discrete water samples at the same time. Some of the ones at the bottom are smaller ones, a little bit more adaptable ones. But you know, the real take home there is that a CTD can cost hundreds of thousands of dollars for the really fanciest ones. And for even the smallest little handheld ones, this one in the bottom right corner is something called a YSI Castaway, which is one of the least expensive CTDs you can get. Even the YSI Castaway costs about $7,000. And so for a lot of people who work in ocean science, that kind of cost represents really an unacceptable barrier to conducting marine research for a lot of people and for a lot of communities, and even for a lot of nations. I have colleagues in, for example, Tanzania, who they want to do work and they don't have access to CTDs. They had a CTD donated to them by an NGO, but the cost not just of operating the CTD, but of calibrating it, of maintaining it, is so high that they haven't been able to deploy it. And so about 10 years ago, me and several colleagues got together and thought, you know, there's got to be a better way to do this. There's got to be a more accessible way to take these kinds of measurements that aren't so expensive that they make the fundamental measurements of marine science out of reach for the vast majority of people who want to study the ocean and who need to study the ocean and who want to know about changes happening in their local communities where they may not necessarily have a major research institution or may not even have a university nearby that can give them access to these tools. So that's where we created the OpenCTD. And the OpenCTD has been a project that's been almost 11 years running now, with a goal of creating a low-cost open source CTD that was accessible for the vast majority of ocean users, that could be built, calibrated, and maintained by the end user so that they didn't become dependent on something like a service contract that is necessary for some of the high-end fancy CTDs where you have to ship them off every year to be calibrated, that can be maintained by them and that can help grow local capacity so that they have ownership over the data that's being produced and the ability to produce high-quality data that can be used for marine scientific research. And so the OpenCTD was kind of a passion project born from a couple of very ambitious very ambitious postdocs, one of which being me, that knew just enough about marine technology to know it was technically possible, but not enough about marine technology to realize just how difficult a project we were undertaking. And so we thought this was the kind of thing that we could do over the course of a couple of field seasons. And 10 years later, we are still banging away at this project to make a low-cost, open source, accessible CTD. So I will tell you about how it works and what it does and the programs we do with it. But the first thing I want to do is talk about the data that comes out of it, because really the most important thing when you're developing a low-cost CTD is the data it produces of enough quality that a marine scientist can use it and can trust it and can publish with it. So this is just one example of some of the testing that we've been doing over the last few years, comparing a suite of different OpenCTDs that have been calibrated at different times to commercial instruments to really assess how far off they are from commercial instruments in terms of real-time use and real-world use, as well as how much the sensors drift over time once they're calibrated. So I don't need to go into tons of detail about this graph other than we have 3 OpenCTDs that were calibrated at different time points over about 18 months, compared to a very recent benchtop probe that was professionally calibrated to confirm that the readings that we got out of ours come within about 5% of the margin of error of the commercial probe. So another comparison that we've been doing is comparing it to the actual CTDs that professional marine scientists have been using in the field. This is a comparison with the YSI Castaway, the one I mentioned earlier, that is a great little CTD. I'm not down on the YSI Castaway. I think it's a fantastic tool, and it's used by an awful lot of ecologists who are working in nearshore environments where they don't necessarily need big, heavy equipment that has to be loaded onto a ship's A-frame and deployed off the side of a boat, but can be casted by hand or, in this case, a fishing rod. Just to prove to ourselves and to prove to everyone else that like the instrument that we are building produces data and the same level of quality as what you would expect from a traditional commercial instrument. And so sort of the takeaway from that is that what we've built with the OpenCTD is we've built a device that is appropriate for the vast majority of sort of marine conservation work that you might be wanting to do, the majority of marine ecology work that you'd be needing to do, but it's not necessarily probably appropriate for something like if you were doing physical or chemical oceanography, where you need really, really refined, really high accuracy readings. This is more the tool for an ecologist or a manager, conservation practitioners, people working in communities, people who are looking for specific variables to measure in their local waterways, but don't necessarily need the most sophisticated measurements that you can get from these kinds of tools. So we had a couple of different values when we set out to make the OpenCTD. The first was that it has to be low cost. Our original goal was to get a CTD that could be built for under $200. We never quite made it to $200. That's still been a little bit out of our realm, but the current OpenCTD can be built for $350. And built is really the key word there, because part of what we wanted it to be was a DIY tool. We wanted the end user to build their own CTD so they had a fundamental understanding of how it worked, how it could be maintained, how it can be repaired, and also how it could be calibrated. So it's really creates independence from the major manufacturers and creates a tool that people can use regardless of access to funding, regardless of access to resources that they may not necessarily have. We wanted it to be accessible, so we made it largely from readily available components, a lot of off-the-shelf electronics, a lot of materials you may find at a hardware store, and a lot of things that are generally readily available around the world, less so as tariffs go up, but that's a different story. But we've tried to minimize the number of custom parts and the number of proprietary parts on it, because we also want it to be open source. We wanted everything about the OpenCTD to be open and available. So we made the bill of materials available to anyone who wants to build them themselves. The source code is all open source, so it's free to use for anyone who wants to download the source code and anyone who wants to do the analyses that the CTDs conduct. The build manual for how to actually build the OpenCTD is freely available online, and we're continually updating it. I have a new edition coming out probably mid-June for some improvements to the build process. And the actual materials are relatively simple. The most complicated things we have in there, we have some 3D printed parts that you can avoid if you need to avoid them, but if you have access to a 3D printer, they make the build process much, much easier. And as you've probably noticed from the picture, it is built inside a PVC pipe, which is really one of the bigger advantages of the system, because when you're looking at marine technology, often the most expensive part is not the electronics, but it's the housing, the actual material you use to make it waterproof down to depth. So we've found through extensive testing, both in the field and in pressure vessels, that you can take a 2-inch PVC pipe with the cap that we use down to about 140 meters consistently without having it fail. And that gets you to most of the world's continental shelves. So this is a coastal tool that lets you take measurements in nearshore environments. It's built on an Arduino platform for people who are into DIY electronics. So we use an Arduino M0 chip from a company called Adafruit, which makes a fantastic range of relatively accessible electronic components. And it runs off a standard lithium polymer battery that's all stored within this housing. You can kind of see in this picture, it's got 3 different kinds of sensors. These silver ones are the temperature sensors. We take 3 temperature sensors and average them together to get a higher level of accuracy. We also get, there's a conductivity sensor here. This is the probe that measures salinity. And you can't really see it in this picture, but right in the middle is the pressure sensor, which is actually a chip that comes off of old dive watches that we've found to be very, very accurate for measuring pressure. So what can you do with the OpenCTD? We've done a lot of different projects over the last few years to both prove the instrument and to also provide data to stakeholders who need it. So this was a program we did called Community Oceanography while watching whales. We partnered with whale watching boats off of Boston and Maine. And the naturalists on board the whale watching boats were trained in how to take CTD casts and how to analyze the data. And when they went out with tourists on whale watching expeditions, of course, when you can't approach whales. So when whales are nearby, you have to stop the boat. And while the boat is stopped, they also do CTD casts and take water quality measurements during the pause while all of the tourists are watching whales, and talk to them a little bit about the oceanography of the area they're working in, for the most part, Stellwagen Bank, also off the coast of Maine. And show the tourists what kind of data that they're collecting. This data was then collated by BOEM, the Bureau of Ocean Energy Management, to use in some of their offshore wind planning. And on these graphs, we just have the kind of comparison points are the closest NOAA buoys to each of these deployments to kind of give us a good baseline for how accurate the instruments were continuing to read. We've done some other really, really fun projects. This one is one of my favorites. This is the North Carolina Wave Energy Generation Project. So one of the things that's really cool when you start an open source project like this is that other people will take what you've built and add to it and do new and interesting things. So the goal for this project was to deploy a suite of 25 CTDs across Albemarle Sound in North Carolina. And they weren't particularly interested in salinity. What they were interested in is looking at the energy potential for internal waves in the sound, to use that as a baseline to assess the potential for energy generation inside the sound using wave energy generators. So things that use like tidal flux to power turbines in order to produce electricity. And so we deployed 25 of these CTDs around. They were reprogrammed to do bursts of pressure sensing to really detect very, very minute internal waves to calculate the energy content of the sound. And when we deployed all these CTDs, we built 25 of them and calibrated them and deployed them out there. And the final cost of all 25 of those CTDs was still less than if they were going to buy a single commercial probe for that same cost. So that really, it saved the institution an awful lot of money that could then be going to personnel and could then be used to train interns and bring on students, and produced, they're currently out there right now, but they're producing a tremendous amount of really high quality data. And it's very, very exciting to see. And very interesting to see, because this was not my first, when I developed the OpenCTD, I didn't envision anything like this. And so partnering with an institution is like, we want to take what you built and completely change its purpose, but use functionally the same hardware to get to other really interesting questions in our local community. So speaking of local communities, I do wear a number of hats. And one of those hats I wear is that I am the Commissioner of Climate Change for my town, which is an objectively hilarious title and has been a lot of fun, but it is an infrastructure commission. It's me and 6 other individuals who are on the Climate Change Commission, with the goal of assessing climate vulnerability of different areas of our town, setting priority areas, and then developing infrastructure programs to do things like raise roads, or put in tide gates, or put in living shorelines, or establish berms, or repair bulkheads. And one of the things we realized we needed early on, because we're in a small town that is up the Chesapeake Bay. The Chesapeake Bay is a very well-studied and very hydrodynamically active region of the U.S. And the tidal cycles of the Chesapeake Bay are not nearly as predictable as you might think they are, because of the size of the Chesapeake Bay estuary. When high tide starts at the mouth of the bay, it'll take about 12 hours for that tidal surge to propagate up to somewhere like Baltimore. And so that has major implications for when high tides hit, when flooding hits, how things like rainfall coming down off the land impact tidal flooding in local areas. And so what we wanted to do is we didn't want to rely on the established tidal buoys that are relatively far away from where our town is in order to predict things like storm surges and coastal flooding. We wanted our own tidal monitor. And so we took the OpenCTD and turned it into a tide gauge using the depth sensor on it to then become a tidal sensor, and taking the temperature and the salinity probes so that we could get some more information off of that. And we connected it to a smart buoy that was donated to us by a company called So Far Ocean as part of their Bristlemouth Pioneer program. And we created our own tide gauge using the OpenCTD and deployed it in our local harbor so that we can get real-time, hyper-local estimates of coastal flooding in our area so that we can do things like assess how often the town floods, where those floods are happening, how out of sync it is with the tidal predictions from the nearest tidal gauges. And we are very out of sync. So for example, this was a 2-week deployment comparing our town to the nearest tide gauge, which is a USGS tide gauge in a town called Claiborne that is not particularly far away. But what we discovered is that our high tide and our coastal flooding in our town was anywhere from 20 minutes ahead to 40 minutes behind the nearest tide gauge, which has, I mean, that is an hour-long range that has tremendous implications for how you do things like emergency management when you have a 2, 3, or 4 foot flood coming in that can inundate the town and flood different areas. And so having the ability to then tie all that into very local tidal estimates became a very, very powerful tool for assessing priority areas around our town to do infrastructure improvements. So those are just a couple of the most recent projects we've done with the OpenCTD, but I want to talk about really kind of what I think makes the OpenCTD shine above a lot of other sorts of projects like this, and that is the workshop model that we've developed. So my original vision for this is I don't want to be an equipment manufacturer. I really don't want to be an equipment manufacturer. I want to go out and do science. But I also want to make sure that people who want to make their own local measurements have the capacity and the access to the tools to do it. And so we developed a workshop model where instead of selling a CTD, we go into communities, we work on developing grants to fund the project, and then we go into communities and we teach people how to build the OpenCTD, and more importantly, we also teach people how to run their own OpenCTD building workshops, so that there's then a level of local expertise that allows the project to persist beyond just the lifespan of my visit to the town. So we've done these workshops in a lot of different regions. Most recently, I did a series of workshops in Alaska, in Homer and in Fairbanks, with local educators who worked in indigenous communities, as well as with the University of Alaska Fairbanks graduate students, training people on not just how to build the OpenCTD, but how to run their own programs, so that they're not dependent on me flying out there and teaching a CTD building workshop, but they can then continue the project independent of me or independent of my own priorities. And we've had a tremendous amount of success and a tremendous amount of fun running these workshops all over the world at this point. I just finished up my first international one in the British Virgin Islands, which was really, really quite exciting. So these are just the kind of shots of the deployment. These are primarily designed to be hand deployed. You can put them and attach them to instruments and send them down. You can also do long-term moorings. The one that we have out in our town harbor has been out for 3 months now and is continuing to log. But, you know, the idea is it's an incredibly flexible instrument that builds local capacity and that builds independence and interdependence among communities. One of the things that I'm very hyper aware of, coming from a technology background, is this phenomenon called imported magic. And if you're familiar with the idea of parachute science, which is this idea that researchers will come into remote communities or come into developing countries and do a bunch of science that benefits their careers, but doesn't necessarily benefit the local community in any way, and then leave. And the people that live there don't really get any benefit from that kind of research. Imported magic is kind of the technology equivalent of that. It's this idea that, like, clever little boys from Silicon Valley, which I'm one of those. I'm not trying to be too disparaging, but technically precocious boys, I think, is the term that's used in the literature, from Silicon Valley, come up with solutions searching for problems, and then deploy them in communities that don't necessarily need or want those solutions. And then if they do decide there's some benefit from them, that's then built a dependence on those outside resources in order to keep and maintain those programs. So my goal is really to build a tool that is needed in a lot of communities, but is requested rather than forced upon those communities. So I'm building the CTD for people who want CTDs, and then building local capacity so that there isn't that independence on far off outside funders in order to continue the research and to make it independent, and to make, data ownership is a very important thing, especially in communities that tend to be exploited for their natural resources without necessarily getting a ton of benefits from them. So making sure that the tools we build are tools for the communities rather than tools for us that we then just throw off into the communities. So that is kind of my whole deal with the OpenCTD. We've had an awful lot of funding for this project over the years, including an awful lot of government funding. The Bureau of Ocean Energy Management is the Department of the Interior. We've had funding from NOAA, the National Marine Sanctuaries Program, as well as the National Marine Sanctuaries Foundation. UNOLS, which is the University National Oceanographic Laboratory System, which maintains a lot of university research vessels. And then we've had some crowdfunding as well. But you can learn more about it at oceanographyforeveryone.com. And I am very happy to take your questions.
Thank you so much, Dr. Thaler. That was awesome. So many things that I love about what we just learned. I love that you are concerned about the cost. I love that you're making this tool more accessible. And I love the interdisciplinary aspect of it. Just so many great things. Yeah. Okay. Somebody wants to know if there is, Claire wants to know, not somebody, is there potential to use these devices in rivers, streams, or lakes?
Absolutely there is. And one of the things we did when we were in Fairbanks is we tested a super low conductivity probe for looking at very low level salinities in freshwater systems that will allow you to do things like distinguish, say, runoff from a storm from like glacial melt. So you can absolutely use them in rivers, streams, or lakes. And it's actually a lot easier to use them in freshwater systems because if it floods, and they do inevitably flood because these are DIY tools, and everything you throw in the ocean will eventually get thrown back at you. But when they flood in freshwater, they tend not to be particularly damaged because freshwater is not very conductive.
Interesting. I have a related question. Maybe it'll make more sense to you than it does to me. Would you get different readings using this tool in different oceans? Maybe this is a calibration question.
So I guess that could be a couple of different kinds of questions. You're reading the same parameters in every ocean. Different oceans have different characteristics. So if you're in Bermuda in the middle of the Atlantic, you're going to measure a much higher salinity than if you're, say, in the Indian Ocean right off the coast of Madagascar. And those change seasonally as well as they vary depending on things like if there's been recent rainfall or if you're in an Arctic environment and there's recent glacial melt or things like that. So the readings aren't necessarily, it's not different types of readings, but yes, the characteristics do change depending on where in the world you are.
Yeah, that's really interesting. And I'm curious also, you talked about making these more cost effective to increase accessibility. I'm also curious about whether the cost effectiveness, if there's sort of a positive side effect of the cost effectiveness for programs like these larger, well-funded programs like Argo that maybe have historically been able to afford the more expensive CTD, if this allows them to keep the prices down and maybe have more sensors.
So you can it definitely keeps the price down. It definitely allows you to add more sensors. There's a couple of programs that we've worked with over the years. Educational Passages is an NGO that builds mini boats that are wind-driven, not drifters, but wind-driven small boats with sensor packets on them. And I've been working very closely with them to reduce the cost of their sensor package and to add things like salinity to it. So programs like that can definitely benefit from them. There are, a fun thing I did a couple of years ago is I was at MBARI, Monterey Bay Aquarium Research Institute, and a lot of their experimental systems use the exact same probes that we use for ours. One of the interesting things we've discovered with these very low-cost sensors is that the sacrifice you make when you go for low-cost sensor systems is not necessarily in the accuracy or in the precision, but it's in the speed of the sensor. So if you're less concerned about how fast you need the sensor to go, you can go much, much cheaper. So the OpenCTD is a slow instrument. It takes one reading a second. The temperature probes take a little bit longer to reach equilibrium than you'd get with a commercial probe. And one of the things we're working on is getting that equilibrium speed a little bit faster and getting that sampling rate a little bit faster. But when you do a cast with an OpenCTD, you're doing it at about a third the speed you do with a conventional CTD. And that trade-off adds up over time. If you're working in 6,000 meters of water, you're not going to use an OpenCTD, even if we had one that could go 6,000 meters. But at some point, the cost of operating the winch for that amount of time dramatically exceeds the cost of the equipment, which is one of the reasons why we aren't going for very deep operating systems. Because when you operate in the deep sea, ultimately, the most expensive part of your equipment is the wire that's coming off your boat.
Yeah, well, tremendous progress regardless. So really great talk. Thank you so much for joining us.
You're very welcome.
We have another really exciting talk coming up on a slightly different topic. And that is from Sonia Rauschenbach. Maybe she can pronounce her last name for you all. That talk is going to be about patterns of coastal fog in Oregon. So a bit of a new topic for us. I don't think we've heard about that yet. But before we get to Sonia, I want to read off our reminders. So first of all, just want to make sure we get out of the way that we know that the speakers Any views that they share are their own, and perspectives may differ from speaker to speaker, and they aren't necessarily representing their institution. We are in hour 54, I want to say, of the live stream, with 46 hours to go. We're super happy with how everything has gone so far, coming up to in this first more than half. And we're here doing this, speaking to you for 100 hours because we really want to share what we do as weather and climate scientists with you all. There's so much amazing science happening here, right here in the US, and so many breakthroughs, which are happening all the time. And we want to make sure that you all know what's happening, what those are, and how they're impacting your lives, your forecasts, and the climate projections. Unfortunately, there have been funding cuts to this weather and climate research, and there are more funding cuts proposed going forward. So if you like what we do, and if you're concerned about these funding cuts, we would be super grateful if you use the link on your screen to contact your representative. You'll be able to put in your address. It'll show you who your representative is and what their phone number is. And then there's a little script that we've written that you can use. You could also write your own. And that's totally optional. We're very happy to have you here watching, learning, asking questions. But if you were willing to do that, that would be like extra special to us. We do that. I think we're going to have a little bit of a host switch. Is that right? Yeah. Welcome, Nodder.
Hello, everybody. I'm Margaret.
Hi, how are you?
I'm great. It's been great to pop in and out of the live stream. I guess we're just about at hour 55. Oh man, someone was on it and it ticked up right on the dot. Margaret, you're doing an amazing job. I feel like every time I check in, you're either on screen or backstage. So thank you for everything you're doing.
Thank you. Yeah, take it away, Nodder. Hour 55.
Will do. All right. Thanks, Margaret. So I'm a federal research scientist based in Princeton, New Jersey. And we're going to have more great talks. You've heard about fog, you've heard about aerosols, you've heard about Argo floats and how they measure the salinity and temperature of the oceans, and that's just been in the last hour and a half. You've heard about all kinds of topics these last 50 hours. There's tons more content coming up. And of course, we are doing this because the scientific enterprise in the US is facing threats. And so it feels like there's never been a better time to articulate to the public, to all of you, what we do, why we do it, and what the value of it is. And so we've created this opportunity to get that information out there. It's a platform for us to tell you what we do and for you to peek behind the curtain of weather and climate science and see what it is we do all day in our laboratories, behind our computers, running our simulations, out there in the field, and even the talk just the last hour or two, I think that pretty plain. And so we're gonna keep on going with that. And next up, we have Alex Chang, a PhD student from UCLA. Welcome, Alex. He's going to talk to us about Amazon dryness and climate change. Alex, I just have to ask, looking at your bio, it sounds like you grew up in New Jersey. Now you're at UCLA, and I grew up a few miles south of UCLA, and now I live in New Jersey. So I got to ask you, where in New Jersey did you grow up?
So that's really funny that you say that, actually, because I am also from the Princeton area, and so it's really cool to see that we've basically swapped paths entirely.
Entirely amazing. All right, we can get more into that in the Q&A, but why don't you go ahead and take it away?
Yeah. Well, first of all, thank you for having me on the stream. It's been really awesome to see climate scientists and meteorologists from all across the country, and really even abroad to an extent, all coming together to talk about how important some of their work is within the climate sciences. And I wanted to give a huge shout out to all of the organizers like you and the volunteers who do a lot of the behind the scenes stuff to make this even possible in the first place. And so, yeah, this is what is this hour? This is hour 55 now, right? Yeah, so a little over halfway through all of these talks, and I guess, yeah, mine's next, but without further ado, I'm going to be presenting a very simplified version of the research that I've been doing for my PhD at UCLA, and it's about how climate change is drying the Amazon rainforest. So yeah, let's get right into it. And so I'd first like to start off with a little bit of background in what the Amazon's role is in Earth's climate system overall. And so a lot of you know that the Amazon is the largest tropical rainforest in the world. And if we see that it covers much of tropical South America and Brazil, as you can see on this map. And it harbors a lot of unique ecosystems and species of plants and animals, and just holds a ton of biodiversity in that part of the world that you probably haven't even seen yourself unless you've actually been to the Amazon before. But perhaps more importantly, in terms of the climate perspective, it removes a ton of atmospheric CO2 every single year through its thick canopy of trees and shrubs and all sorts of different vegetation in the region. And unfortunately, in recent years or decades, there have been changes in that ability for the Amazon to remove atmospheric CO2. And some studies have even suggested that it's a net carbon source instead of a net carbon sink overall today. And what I basically mean by that is that nowadays, well, historically, the Amazon has removed a ton of atmospheric CO2 and emitted a little bit, but nowadays that trend is reversed, where it's emitting more CO2 back into the atmosphere than it is removing. And this is quite alarming with respect to the greenhouse gas effect and warmer temperatures overall. And so, yeah, this figure from another study that looked at carbon sinks in the Amazon as well as African rainforests, if we focus on this gray line over here, we can see that the Amazon's net carbon sink has been trending downwards quite significantly over the past couple of decades. And if we extrapolate this to today, it is considered a net carbon source now instead. And so there have been a lot of concerns raised about the Amazon's ability to withstand against these changes overall. And in general, there have been three major ways in which the Amazon is changing, and it's largely getting drier, it's getting warmer, and it's been experiencing a lot more droughts in general. And so I wanted to take a deeper dive into how the Amazon is getting drier. And there's three main ways. And the first of which is through a little metric called vapor pressure deficit, or VPD. It's a fairly abstract concept, but it basically measures the atmosphere's quote unquote thirst. How thirsty is the atmosphere, to put it in simple terms. And we've seen significant increases in that over the past few decades. If we look at this figure here, where this study looked at VPD trends from 1987 to 2016, this area covers like the southern and eastern portions of the Amazon, and those are where the greatest VPD increases have occurred, and that's where the Amazon is becoming the most quote unquote thirsty compared to historical levels. In addition to that, the wet season in the Amazon is becoming shorter and the dry season is becoming longer. And this is mainly due to a shift towards the later wet season start dates. And what that basically means is the wet season is starting later and later compared to its historical date. I'll explain that more later, but this right here is a figure showing historical wet season and dry season patterns over the Amazon. If we focus on the x-axis, where it shows the months throughout the year, and then the years along the y-axis, we can see that this line here, which shows roughly when the wet season is starting, it's been shifting towards later and later days in September and trending towards October or even November. And that trend has continued past 2010, even though the figure only covers up to that point. And lastly, there have been a lot more frequent and severe droughts in the recent decades. Just this past year or two, the Amazon had its worst drought on record by several metrics, including like wildfire burn area, and if we focus on this figure specifically, water levels in the region. So if we focus on 2023, which is the solid red line, the data kind of stopped in late October 2023, at the time this study was published, but we can see, if we were to continue this trend, it would continue at record low water levels. And so the Amazon has experienced really bad droughts in recent years. And so in terms of my research, the main questions of focus are to basically tackle those three aspects of drying. What are the biggest factors controlling the VPD increases? Like, why is the Amazon becoming more thirsty for moisture in general? And secondly, what are the primary mechanisms that are shortening the Amazon monsoon? And lastly, what are the main drivers behind the worsening droughts in recent decades? We've seen like 4 record-breaking droughts since 2000, but before that, there were barely any record-breaking droughts. And so what's been going on with that? And so I won't be providing the answers to all of these questions. In fact, some of this PhD work is ongoing, and I haven't even started the third part. I'll be tackling that in the last year, but I will provide some insight into why it's so important to address these aspects of dryness in the Amazon. And so let's first go into vapor pressure deficit. As I mentioned before, it's a measure of how quote unquote thirsty the atmosphere is for water vapor. And if you've ever opened up your weather app and looked at the stat called humidity, it's very similar to that, except that relative humidity is always expressed in like percentages, and vapor pressure deficit is more absolute. And basically, vapor pressure deficit measures the capacity of water vapor in the atmosphere relative to its maximum. So how much water there is versus how much it can hold. And in general, the warmer the temperature is in the atmosphere, the more moisture that can be held in the atmosphere. And this relationship is known as the Clausius-Clapeyron equation. And I'm not going to show the equation here for simplicity, but we can think of it kind of like, let's just say we have a tank of water here. I realize it's just a rectangle, but let's just say that we have a tank of water and it holds this much water. The amount of water that's in the tank represents the actual humidity, and the size of the tank kind of represents the temperature-controlled component of it, and the maximum possible amount of water vapor that can be held in the atmosphere. And vapor pressure deficit basically measures how big is this gap between the water level and the maximum capacity. And when it comes to vapor pressure deficit increases, we can increase it in one or both of these two ways. The first is we can increase the temperature, and what that actually does is increase the size of the tank such that it can hold more water vapor even if we don't actually change the amount of water in the tank, the gap between the actual amount and the maximum increases, and so the vapor pressure deficit increases as a result of this. And basically, the atmosphere becomes more thirsty when you increase its maximum capacity because the deficit is bigger. And the other way we can increase vapor pressure deficit is by actually removing water from the tank or decreasing the humidity. And like this is perhaps the more obvious one, but when we remove humidity, the atmosphere will become more thirsty for moisture as a result. And in the Amazon, we are seeing both that temperature is increasing and humidity is decreasing, particularly in the southern Amazon. But until recently, it wasn't super clear which one was more responsible for increasing VPD. Is it mostly due to temperature increases, or is it mostly due to humidity decreases? And so keeping the temperature-controlled component, like increasing the size of the tank and removing water, the humidity component in mind, let's put that into more formal terms. I'm now going to define what's known as saturation and actual vapor pressures. And so saturation vapor pressure is basically that temperature-based component, the maximum possible amount of water vapor that the air can hold at a given temperature. And if we increase temperature, we increase saturation vapor pressure. And actual vapor pressure, on the other hand, is the actual amount of water vapor that's in the air. And so this is more controlled by humidity. And if we decrease humidity, we will decrease the actual vapor pressure, with all else being held constant. And vapor pressure deficit, or VPD, mathematically can be defined as the difference between the two. And so to determine whether VPD is being more controlled by temperature or humidity, we can simply look at which one, whether saturation vapor pressure increases more, or actual vapor pressure decreases more. And I'm going to show a couple plots for my research. And this right here is a plot showing the VPD trends over the past 45 years up to 2023 during the dry season. And we can clearly see that the greatest VPD increases occur in this like red box region, mostly over the southern and eastern portion of the Amazon. And if we split VPD into its temperature-based and humidity-based components, saturation and actual vapor pressure, these scales of these two plots are the same. And so we can clearly see that the increases in saturation vapor pressure are greater than the decreases in actual vapor pressure. And what that basically tells us is that the warming temperatures plays a bigger role or responsibility in increasing VPD compared to decreases in humidity. And so with the VPD increases that we've seen recently, what can we determine for how VPD is expected to change in the future? And the answer to that really depends on what's known as, well, first I'm going to show the plot here showing different climate scenarios. But in the talk of like the climate models and how they simulate future climates, they usually base it off of different scenarios, and one of which is through shared socioeconomic pathways, or SSPs. And they basically represent possible paths that Earth's climate system could follow in the future, depending on greenhouse gas emissions. And so there's usually 5 commonly used SSP scenarios, and I'm only going to be showing 3 for simplicity. But SSP 5 is known as the business as usual scenario, where we can see that if we follow the red line, VPD continues to increase to very dangerously high levels by the end of this century. This results in VPD being roughly 12 times higher than the current day levels, and current day levels are already even higher than historical levels. So that's quite alarming. A more middle of the road scenario is SSP2, which kind of combines a little bit of the we do a little bit of significant development towards reducing carbon emissions, but we still rely on fossil fuel development for a little bit. And this is kind of like in the middle. And we see that if we follow the yellow line, VPD increases to still somewhat dangerous levels, but clearly nowhere near as that seen in the worst case scenario, the business as usual scenario. Perhaps more optimistically, SSP1, which is otherwise known as the sustainability scenario, and it also represents like what happens if we were to shut all greenhouse gas emissions down right away. Well, this would result in VPD still increasing a little bit, but it would halt by the middle of the century. The blue line kind of flattens out, and VPD is kept outside of dangerous levels as a result. And so this is the future when it comes to VPD, depending on what path we take later on. And so now I want to shift gears into the shorter wet season in the Amazon and what's been happening with that. And so before I go into that, I want to talk about what are monsoonal climates. And basically monsoonal climates are climates where there are distinct dry and wet seasons, where like half of the year is a lot drier than average, and the other half of the year is wetter than average. Where I'm currently based in California, we have very distinct dry and wet season and have like a monsoonal climate in the sense that we basically get all our rain during the winter months from November to March, sometimes April and October. And the other months during the summer, we barely get any rain at all. And it's considered like an anomaly if we do. And the southern Amazon is very similar with that regard, except their dry season is from May or June to October or November, and the wet season encompasses the other months. And these are usually caused by seasonal shifts in the atmospheric circulation. And this is usually because like when the circulation shifts, the position of the heaviest rainfall areas, those change throughout the course of the year. And in general, monsoonal climates are, I wouldn't say they're unique. In fact, you can find them everywhere throughout the planet. If we take a look at this map, we can see that monsoonal climates occur in pretty much every continent except for Europe, and Antarctica is not included, but we don't see monsoonal climates in Antarctica, but they're everywhere. And I want to focus a little bit more on the South American monsoon. And in general, as I mentioned before, the South American has had a delayed monsoon start. So this is another figure showing the start of the wet season and how it's progressed over recent years. And in general, the higher the number, the later in the year it's starting. And we can clearly see there's a fairly significant increase in this increasing trend that represents that the Amazon is starting later in the year than normal. And in fact, if we were to take this plot, the wet season is actually about 1 month shorter on average today than it was 45 years ago. And what that means is that's 1 month where vegetation has to spend like being drier, or one more month where wildfire risk increases, and perhaps 1 more month where the risk of drought increases as well. And so it's quite alarming in that regard how the Amazon is becoming drier. And it's likely that VPD increases that I showed in the previous section, those play a role probably in shortening the wet season, but as of now, the link is not super clear, and I'm currently doing a lot of research hoping to disentangle that, and I hope to have some results on that shortly, and even though I won't be showing them today. I realize I'm a little bit short on time, but I did want to cover one last thing, which is the recent droughts in the Amazon. And you might be thinking, can droughts even occur in the Amazon? It's a rainforest after all. And it's true that the average precipitation in the Amazon every single year is roughly 6 to 10 feet, or 1.8 to 3 meters. And in this context, a drought is usually defined as a long time period. It's often 3 or more months where precipitation is considered below average or much below average. And during a drought, it doesn't necessarily mean that no precipitation falls at all. It just means that there's far less precipitation than in the case of the Amazon that can keep up for the very heavy amounts of vegetation and like huge canopies in the Amazon rainforest overall. Basically, the demand is far exceeding the supply of rainfall in the region during a drought. And this often results in lower ecosystem productivity and other impacts such as reduced crop yield. And there have been, as I mentioned before, 4 record-breaking droughts in the Amazon since 2000. They occurred during these years. And if we look at this figure that looked at droughts and water levels, if we focus on the highlighted periods that indicate the droughts, we can clearly see that in each of these regions of the Amazon, the water levels have generally dipped during the times of drought and are significantly below average if we focus on the standardized anomalies. And so I lastly wanted to show one more connection with drought and respect to VPD increases, since those are usually pretty related. And this right here is a figure showing what were the VPD values like during those years where we had the extreme drought since 2001. And on the right, we have the same thing, but the VPD values during the years where drought didn't occur. And we can clearly see that VPD is significantly higher during droughts. Droughts are making the Amazon, quote unquote, more and more thirsty, to put it in simpler terms. And it's still high during the non-drought years, but it's clearly much higher during the drought years. And this all occurs during the dry season. So it's likely that VPD makes droughts worse over the Amazon, but at the moment, the mechanisms are not super well understood. And hopefully, during my final year at UCLA, I hope to be able to tackle on this problem and provide some insight into this question overall. And so those are the ways in which the Amazon has been getting a lot drier overall. And so you might be wondering, well, what's the big deal if the Amazon gets drier? Why is this so important? And the answer to that, to answer that question, we have to go back to what the Amazon's role is in Earth's climate system. And if you remember what I mentioned at the beginning, the Amazon's role is removing a ton of atmospheric CO2. And in a way, some have described the Amazon as colloquially like the lungs of the Earth, in the sense that it breathes out oxygen and inhales a bunch of CO2 that's otherwise stuck in the atmosphere and keeps our planet's climate under control. And the recent increases that we've seen in VPD and the length of the dry season or shortening of the wet season, and even the recent droughts have all made it, quote unquote, harder for the Amazon to breathe. And if we think of it kind of like in the terms of lungs in this little cartoon over here, we're kind of like shrinking the size of the lungs when we make the Amazon drier. And I didn't really talk too much about this, but in terms of deforestation, which is also a big concern in parts of the Amazon, especially at the edge, when we think of deforestation, we are removing a bunch of trees that could otherwise remove a bunch of atmospheric CO2. And so we can kind of think of it as like we are literally cutting off the lungs of the Amazon and making it harder to breathe. And so all of these trends have raised concerns with respect to whether the Amazon can even sustain itself as a rainforest, whether it's reached a tipping point, or whether it'll collapse in the future, or whether we've already passed that. And this is really concerning, because if that were to ever happen, if the Amazon were to ever collapse, we would see a lot of CO2 being released into the atmosphere and further enhancing the greenhouse effect. And we would see huge losses of biodiversity and huge reductions in like agricultural productivity, and we would see even warmer temperatures than we already do. And this is just scratching the surface as to what other kinds of devastating impacts would occur if the Amazon were to collapse in the future. And so hopefully this provides some insight as to why the drying of the Amazon is super important to understand, and why we need to research this, and why really climate-related research is so important in general. And lastly, why it's important to continue funding all of this climate research for the future that we build later on in the years to come. Yeah, and with that in mind, I'm happy to take any questions from the audience at this point.
Excellent. Thank you for the great talk, Alex, on a topic that I think people have probably heard about, and heard about potential impacts of the Amazon drying and other climate impacts, the impacts of deforestation. But sometimes it's hard to kind of get a clear picture of what's going on. And so I think your talk did a lot to address that. There's a ton of great questions in the chat. Maybe I'll start with, so you touched on this at the end, that there's, about the relationship between drought and VPD, and drought there just meaning rainfall, a little bit below normal. And it sounds like the story there might be complicated, but we had a couple questions on it in the chat. Here's one. Is a decrease in VPD over the Amazon reflected in a decrease in precipitation? And so if I could rephrase that, is the thinking that when there's a drought, there's just less water available at the surface, and so the vapor pressure deficit goes up, or are there other ways, or does VPD itself influence precipitation, so the causality goes the other way, or how should we think about that relationship?
Yeah, it's a really good question. And the answer to that is that the relationship between VPD and precipitation is honestly more complex than I was expecting it to be. And I think a lot of that has to do with the fact that like precipitation in the Amazon is just really complex to model and observe in general, because we've only had like a rather limited record of precipitation in the region. And right now, we're seeing a lot of these decreases in VPD throughout much of the Amazon, but the precipitation trends don't really match that. And in fact, if we look at some of the recent climate studies that have tried to look at precipitation, they get mixed results, or like no significant changes in annual precipitation. And it really depends, because I think like it's really complex, because the Amazon spans two hemispheres technically, and so their precipitation cycles are different depending on which part of the Amazon you're referring to. And so there's a lot involving changes in precipitation depending on like which part of the Amazon, and how VPD doesn't really match that. And so the relationship between VPD and precipitation isn't particularly strong, surprisingly. It's actually more linked to temperature rather than moisture changes. So if we refer back to that water tank analogy, we're increasing the size of the tank more rather than removing the actual amount of water, if that answers your question. It looks like, oh no, it looks like we lost the host, but I'm just gonna look through. It looks like I can see some of the questions on YouTube right now. I don't know how much time there is, but let's see. Are we looking at species that can adapt? Oh, Stella, you're muted. I can't hear you.
I can be your host for a second and ask you some questions. I put one up on the screen here. Is the wet season getting shorter only in the Amazon, or is the shortening observed elsewhere too?
I do believe so I'm not an expert in regions outside of the Amazon, but I do believe that we are seeing wet season shortening. At least I know in like parts of the African rainforest, specifically like the Congo Basin, we're seeing the wet season shortening there as well. So it's definitely happening elsewhere, but I don't really know the specifics of exactly where beyond that.
Absolutely, totally fair. I guess maybe one quick other question. Let's see. Let's see here. Oh, there's so many good ones. You all have great questions. I guess maybe we're looking at, like, besides reforestation, could albedo modification help preserve the water in the Amazon area? I don't know if that's something you're familiar with, but seems like an interesting take.
Yeah, so yeah, let me think about that. So like surface cooling, albedo modification help. Yeah, so I'm not too knowledgeable in this aspect, but I did briefly, like early on in my research, I briefly looked at the impact of like albedo modification in the sense of how is I guess like cloud cover changing in the region. And so I think in a way we can see, oh, the host is changing again, but we can,
I'm back.
in a way, if we do increase the albedo, I imagine we would be able to see changes in like the amount of, like, for example, solar radiation that comes through if we were to increase the amount of clouds. But I am admittedly not an expert in this part, so that's all I can answer, unfortunately.
Thanks, Alex. And sorry for dropping out on you there.
Yeah, no
back
worries.
Now. And we got a few questions about the monsoons, which you mentioned here. And so you showed some nice evidence that, that the dry season was getting longer, the wet season was getting shorter. And is that part of a global trend, or something that's mostly only seen in the Amazon, or too soon to tell?
I wouldn't really call it a global trend so much as to say that this is that there's been a lot of relation to wet seasons like changing in all parts of the world, whether longer or shorter, and this is mostly through a process known as Hadley cell intensification. And for those of you who know where the intertropical convergence zone is, which is that like narrow band of precipitation near the equator, that has been getting narrower and more intense. And so like that, for example, has implications as to how intense the rainfall will be during the wet season, but can also shorten the wet season's length overall. So it's kind of like we're seeing more months with more months that are drier than average, but then the months that are during the wet season, they're like becoming even more wet. And so yeah, we're seeing this dry get drier, wet get wetter effect as we go into the future in general overall.
Got it. Excellent. Well, it looks like our time is up. Thank you so much, Alex, for joining us.
Yeah, thank you for letting me present, and I'll pass it on to the next person.
Excellent. So if you're with us, you are watching the Weather and Climate live stream, 100 hours of weather and climate science, straight from weather and climate scientists. And next up, we have Martha Buckley, an oceanographer supported by NOAA, NASA, and NSF. And she's going to tell us about Atlantic Ocean circulation and climate. Welcome, Martha. Are we able to hear you? Not yet. No. Oh, she's muted.
Okay. Can you hear me
There
now?
we go. We got you.
Okay. Thank you so much for having me, and thanks for the organizers for presenting. Yeah, the title of my talk is Why Are Sea Surface Temperatures in the Subpolar North Atlantic Predictable? And I'd like to acknowledge support from NSF, NOAA, and NASA. And without their support, research like myself and my colleagues would not be possible. Okay. So climate predictions are needed on all time scales, but different processes are different on different time scales. So for example, for weather, which is on time scales of days, even hours to weeks, internal tropospheric dynamics dominates. The stratosphere becomes important on subseasonal to seasonal timescales, as does soil moisture. El Nino Southern Oscillation is the dominant predictable mode on seasonal to annual timescales. And then on annual to decadal timescales, the extratropical ocean becomes important. And then on decadal to centennial timescales, the climate is generally the response to external forcing, primarily anthropogenic greenhouse gases, but also anthropogenic aerosols. And then there's also natural forcing, such as volcanic aerosols and solar radiation, solar changes. So I'll start with the short timescales, which people are most familiar with the predictions on. For example, weather forecasts. So weather forecasts are on timescales of hours to weeks. And numerical weather prediction is basically an initial value problem. And so when you think about this initial value problem, it depends very heavily on our observational network. And currently our observational network is in danger due to federal budget cuts. And if the observational network is degraded, the forecasts will be degraded substantially. So due to the chaotic nature of the troposphere, the predictability horizon for numerical weather prediction is generally thought to be around 2 weeks, but there's some recent studies that indicate modes such as the North Atlantic Oscillation may be predictable on much longer timescales. So now I'm going to go to the other end of the timescale spectrum and talk about centennial climate variations. So on centennial timescales, the climate state is the response to external forcing. So how do we study this? So the way to uncover the externally forced signal is to use large ensembles, either a single model large ensembles or multi-model large ensembles. So this is an example of a projection of the global mean sea surface temperature anomaly from the CSM1 large ensemble. So a single model large ensemble, and it's under historical forcing, and the future pathway is given by RCP 8.5. Okay, so how does the single model large ensemble work? So each ensemble member has a small perturbation in initial conditions. Here, it's just atmospheric initial conditions that are perturbed. And this results in many possible trajectories, which are shown by this gray shading. And the observations are shown in red. And the fact that these observations lie within the spread of the ensemble members indicates that this model is consistent with observations. So the black line shows the ensemble mean, and this is an estimate of the externally forced response. And the reason for that is that these are uninitialized simulations. They're not initialized with data, so the natural variability does not align in the ensemble members. And so the natural variability basically averages out, and you're just left with the externally forced response. And so this model suggests that the global mean surface temperature will increase by about 5 degrees Celsius by 2100. So now I'm going to talk about forecasts at lead times in between numerical weather prediction and externally forced centennial variations. So this figure shows the importance of initial conditions in blue and the importance of external forcing in red for temperature over the top 300 meters in the North Pacific on the left and in the North Atlantic on the right. So as forecast lead time increases, the importance of initial conditions decays, as you would expect, and the importance of external forcing increases. On these decadal timescales, both external forcing and initial conditions are important. So it makes forecasting at these timescales more complicated. Okay? Another thing to note is that the importance of initial conditions persists longer in the North Atlantic, around 9 years, than it does in the North Pacific, it's around 6 years. So how important natural variability and external forcing is can depend on region. It can also depend on spatial scale. So from the previous plot, we know that for decadal climate predictions, which means predictions on years to about a decade, both specification of initial conditions and external forcing is necessary. And on these timescales, the ocean and also sea ice is the primary reservoir of memory. And so in order to understand the role of ocean initialization in climate predictability, we use ensembles in which the ocean and sea ice are initialized. Okay. So this is an example of a large ensemble that's initialized. So this is called the Decadal Prediction Large Ensemble. It's a CSM1 product. And what is shown here is the skill of decadal predictions of sea surface temperature at various lead times. So years 1 to 4, forecasts at years 3 to 7, and forecasts at years 5 to 9. So how is this decadal prediction large ensemble created? So the ocean is initialized using a reanalysis forced simulation of CSM1 to give us a best guess of what the ocean circulation was doing at that time. The initialization is November 1st of each year from 1954 to 2014. And for each start date, a 40-member ensemble is created by perturbing the atmospheric initial conditions. So as a result, the ensemble mean forecast captures the impact of both ocean initialization and external forcing. So when we compare the skill of the forecast to ERSST version 5 observations, this is what we get. And so red numbers mean a skillful forecast. So you can see that this decadal prediction large ensemble has skill at predicting SST over most ocean regions. And this skill does not decrease a lot with lead time. So even at years 5 to 9, we're showing very high skill over most regions. But we don't know from this experiment whether this skill comes from ocean initialization or it actually just comes from specifying the external forcing. So how do we figure out the impact of ocean initialization? So we can use the uninitialized CSM1 large ensemble to calculate the skill from external forcing only. And then we can subtract this from the skill of the initialized ensemble to get the skill due to only ocean initialization. And so here we have a much different picture. Basically, the places where ocean initialization improves skill for SST forecasts is restricted to the subpolar North Atlantic. And actually this skill lasts, all the way out to years 5 to 9. But of course, it's very geographically constrained. So the subpolar North Atlantic is a special region where ocean initialization increases the skill for decadal SST predictions. And this is found in other models, not just CSM1, and you can see that in these references. Okay, so, now just stepping back, why do we care, right, about predictability of sea surface temperature when we live on land? So does the atmosphere inherit any predictability from the ocean? Okay, so this is the skill provided by ocean initialization for the decadal prediction large ensemble, so that same model, for predicting summertime precipitation at various lead times. And so you can see that there are places, in particular in the Sahel and parts of Europe, where ocean initialization does enhance your skill for predicting precipitation, summertime precipitation. But the skill is less robust than the skill for sea surface temperature. It's a bit more model dependent. Another thing to note is, precipitation is a bit less well-observed quantity compared to sea surface temperature. And so that is also part of the equation, right? So we have to keep in mind when we make predictions, we are making them with models, but the observations are important for both the initialization, but also for evaluating our forecasts. Okay, so now I'm going to go back to thinking about the predictability of SST, shown here. And so predictability is inherently a model-derived quantity. And so you might ask, can we use observations to probe the predictability of SST? And we can. So one way to do this is just to use a simple statistical measure of predictability. And here I've used a simple statistical measure called the decorrelation timescale. It's similar to an e-folding timescale, but it's able to capture more complex variations of the autocorrelation function, such as periodic behavior. And so when I calculate the decorrelation timescale from sea surface temperature, which has the global warming signal removed, by linear regression, this is what I get. So this is a time scale in years. You can think of it like an e-folding time scale. How long is sea surface temperature predictable for based on observations? And so you get a large signal in the subpolar North Atlantic, and the predictability time scale is around 4 years. And so, this matches the region where ocean initialization was found to enhance predictability in the CSM1 large ensemble and also other large ensembles. Okay, so we have a consistency between the models and the observations. Okay, so now the thing that really excites me is why is this region predictable? So to understand this, we need to know some of the features of the Atlantic Ocean circulation. So I'm going to talk briefly about the main features of the Atlantic Ocean. So this is the sea surface salinity over the world ocean from Aquarius. And so certain things jump out at you right away. So the equatorial regions and the polar regions are fresh, and that's because precipitation exceeds evaporation in those regions. The subtropics are salty, and that's because evaporation exceeds precipitation in those regions. But maybe a more subtle feature is that, on average, the Atlantic is a lot saltier than the Pacific. And that's because the Atlantic is a net evaporative basin. So because the Atlantic is saltier, the surface waters in the Atlantic are denser than the Pacific. So in the wintertime, we can get deep convection, deep mixed layer depths, and dense waters sinking. And so here, this is a figure that shows the March mixed layer depth from this study. And you can see it's very, very deep in the subpolar North Atlantic, particularly the Labrador Sea, depths of greater than 1,600 meters. The September mixed layer depths, so in the summertime, the mixed layer depths are much shallower in the subpolar North Atlantic, and they're deep, in the wintertime hemisphere, in the southern hemisphere. So as a result of this dense water formation, waters sink, and these dense waters travel southward at depth in the Atlantic. And these waters eventually upwell in the Southern Ocean, being transformed to lighter waters. And so these waters flowing southward at depth are balanced by a northward near surface return flow. And this is often referred to as the Atlantic Meridional Overturning Circulation, or AMOC. And the strength of the AMOC is around 20 sphere drops, and a sphere drop is 1 million cubic meters per second. And so as a result of the overturning circulation, the Atlantic Ocean transports heat northward in both hemispheres. So that's shown by this red line. Contrarily, the Pacific, shown in green, transports heat poleward in both hemispheres, from warm to cold, as you might expect. So the Atlantic is special because of this overturning circulation. Okay, So now I want to ask, so we learned a few things about the Atlantic Ocean. One, that it has very deep mixed layer depths. It has a very strong seasonal cycle in mixed layer depths. And also it has this overturning circulation. So we might ask, to what extent could the high predictability in the Atlantic be explained by either the annual mean mixed layer depth being deep, these seasonal variations in the mixed layer depth, or low frequency variations in the ocean circulation, such as the AMOC. So I'm going to take a really simple approach and just ask, can the observed SST predictability be captured by a very simple model in which the ocean is forced by stochastic or random atmospheric forcing, and it responds? And then when asked, are seasonal variations in the mixed layer depth important for the response of the ocean to stochastic atmospheric forcing? Okay, so this is a very simple stochastic climate model, and you can really just think about it as a bathtub, okay, or a bucket of water. So this is the random white noise atmospheric forcing, and these are the SST responses for two different depths of the mixed layer, or depths of your bucket. Now, if you put in the same amount of stochastic atmospheric forcing into something that has a shallow depth compared to a deeper depth, you will get more variability in the shallow fluid. Okay? So that's shown here. Note the y-axis is different on these two plots. So this one goes from 0 to 0.4 and this one from 0 to 0.1. And so this shallow mixed layer depth has much more variance. Okay? But the fluid, it has a temperature anomaly. It's also damped to the atmosphere. And so everyone knows that if you have a deeper bucket, it will take longer to cool down, to change temperature than a shallower bucket. So when you have the shallower one, you have lower persistence for a shallower mixed layer depth. For a deeper mixed layer depth, you have higher persistence. And that's really, all that a stochastic climate model is. Okay. So now how do the seasonal variations in the mixed layer depth change the SST variance? Okay, so air sea heat fluxes are less efficient in changing SST when the mixed layer is deep. This is just the deeper bucket, okay? So we expect the variance, the SST variance, to be bigger in the summertime than in the wintertime. This is slightly counterbalanced by the fact that air sea heat fluxes are actually stronger in the winter, but actually the mixed layer depth ends up winning out in the subpolar North Atlantic, so the SST variance is larger in the summertime. Okay, then there's also a fact of entrainment. So when the mixed layer deepens, it entrains fluid from below. So if you have an SST anomaly here in the summertime, as the mixed layer deepens, it will entrain fluid and damp that SST anomaly away. Okay, so that's how the seasonal mixed layer depth variations affect the SST variance. They reduce the SST variance in the wintertime. Now, how do they change the memory of the system? Well, in winter, we have a deeper mixed layer depth and thus a longer memory, just like the bucket, right? In the summer, we have a shallower mixed layer depth and a shorter memory. Okay. But there's another process related to this entrainment that changes the memory and actually enhances the memory in the wintertime, and it's called reemergence. So if we have an SST anomaly in the wintertime, when the seasonal thermocline forms in the summer, so the mixed layer depth is much, much shallower in the summer, this anomaly can get entrained below, it can get isolated below the mixed layer depth. And the following winter, this SST anomaly can reemerge. And so this enhances predictability of wintertime SST. Okay, so this is just simply the seasonal autocorrelation function from March for a few different SST observational projects, ERSST and HAD1SST. And the seasonal autocorrelation function from March is just an autocorrelation function, but lag 0 is just 1 month, March in this case. So what you can see is there's initial decay of the autocorrelation function, but the following winter, the autocorrelation function increases again. And then that actually happens at year 2 and a little bit at year 3 even. So this is a hint that this seasonal reemergence mechanism is very important for the higher predictability found in the North Atlantic, the subpolar North Atlantic. So now I'm going to look at this same seasonal autocorrelation function, but from the CSM1 model. This is actually a pre-industrial control simulation of the CSM1 model. And so in an excellent paper in Journal of Climate, Glenn Liu, who was a graduate student at Hui, who just graduated, he created a stochastic climate model and based on physical parameters, and he included this entrainment term, which leads to this seasonal reemergence. And so the fully coupled model, CSM1, is shown in this white dashed line. And the entraining stochastic climate model is shown in this orange line. And you can see that this entraining climate model really well matches the fully coupled model. So a very simple stochastic climate model matches the fully coupled. And so this means that at least in CSM1, a lot of this memory in the subpolar North Atlantic can be explained by reemergence. And so coming soon, Glenn is writing a paper on the application of the stochastic climate model to observations, and to see if you can say the same in observations, that the predictability really is due to this reemergence. Okay. So in conclusion, ocean initialization enhances predictability of sea surface temperatures in the subpolar North Atlantic. SST is predictability on timescales of 5 to 9 years in the subpolar North Atlantic. And this higher SST predictability in the subpolar North Atlantic compared to other basins is at least partially explained by the deeper wintertime mixed layer depths and the large seasonal cycle of mixed layer depths. So basically allowing these SST anomalies to reemerge the following winter and enhance predictability. The atmosphere may inherit some of the predictability from the ocean, leading to predictable variations in variables that we really care about, such as precipitation and surface air temperature. Okay. And in terms of predictions, it's always important to keep in mind that observations are needed for both initialization and validation of prediction. And so the federal budget cuts are imperiling our observational networks, and they will impede our ability to make predictions. Thank you. Happy to take questions.
Great. Thank you, Martha. We have some AMOC fans in the chat. So great to connect that. And probably this is, a different side of the AMOC than they're used to seeing, thinking about it in terms of predictability and how specific properties of the AMOC lend itself to predictability. There's a couple questions in the chat, but I'm wondering if before we get to those, if you could maybe just tease out some of the practical implications of this predictability. So you talk about a 5 to 10 year timeline of predictability. Folks may have heard that the AMOC plays a role in setting the climate of Europe by transporting heat poleward. So does this predictability have consequences for climate on land in Europe or elsewhere, or weather on land?
I mean, so there have been it's always a bit harder and more model dependent to get so this is very robust, this predictability in the subpolar North Atlantic, and different models show a bit of a different degree of impacts, right? But there have been a number of studies that showed impacts on temperatures in Europe related to both the AMOC, but just more generally variations in sea surface temperature in the subpolar North Atlantic, right? And so, I'm suggesting part of that comes not necessarily from the AMOC, but actually just from a more simple reemergence mechanism. But, in terms of the climate impacts, what really matters is the sea surface temperature and whether, there are downstream impacts on the atmosphere. And so there have been studies that show that, and, there was some sort of spotty precipitation impacts in Europe as well. Regarding the AMOC more specifically, so it's a bit interesting that at least in this model, there are really no ocean initialization does not enhance predictability like in the tropical Atlantic, but you do get these signatures in the Sahel. And so these signatures of Sahel precipitation have been tied to the AMOC, in particular in water hosing studies. So, the precipitation, the precipitation changes due to ocean initialization were modest and only statistically significant in a few regions, the Sahel being one of them. But that is consistent with this idea that that AMOC is important, and that is important for the Sahel precipitation. And that sort of idea came from these water hosing studies.
Gotcha. So some evidence that this predictability of SSTs in this area is gonna lead to some predictability of weather and weather on land.
Yeah.
Great. All right, we'll move on to some of the questions in the chat. Let's see here. So here's an interesting one. Does lessened salinity near the poles impact how deep the flow goes into warmer waters?
So if you decrease the salinity by the poles, you can disrupt this deep convection, right? And so, this is where these water hosing experiments have come in. This is why people think the AMOC may decline. So, part of the AMOC decline is just by warming of the subpolar waters, so they get less dense. But you can also make waters less dense by freshening them. So if you melt a bunch of ice, that will reduce the salinity, and you can get less deep water formation. And a reduced AMOC.
Got it. And then in initializing your ensemble for predictions, you describe the perturbations that differentiate your ensemble members as random. And so there's a question here: why start with random perturbation?
So interestingly, that's basically all that's needed.
Why we can use more physical perturbations, or do they really need to be random?
So the particular results I showed were from CSM1, and they did use just random perturbations in the atmosphere for the ensemble, and that's called micro-initialization. So this is kind of like the butterfly effect, right? So after some time, a little tiny perturbation grows, right? And it becomes a finite amplitude perturbation. Now, since the CSM1 time, in CSM2, the large ensemble, they've started what they call macro initialization, where they do sort of initialize, let's say, with different AMOC states. Okay, so that's to try to widen the spread of possible trajectories. So you're saying, and so that is sort of something that this ensemble has evolved from just these random perturbations that are in the study I described. That actually was not my work. It's Steve Yeager and a bunch, a huge number of people are involved in that. But the perturbations used have evolved over time.
Great, and I think it's useful to make the distinction between the atmospheric perturbations and the oceanic perturbations, which I guess maybe have a little bit more of a physical basis to them.
Yeah.
Fantastic. Thank you, Martha, for the talk and for sharing your science.
Okay, thank you so much for organizing.
You got it. So we are now going to move into the keynote section of the evening. And our next speaker is someone who is both, eminent and widely regarded in the climate community, and as well as someone who is a dear friend and mentor to me, Isaac Held. He is now retired, but a climate scientist who worked at the same government lab that I do in Princeton, New Jersey, for essentially his whole career, and actually got his PhD in a joint program between that lab and Princeton University. And then after a short stint at Harvard, worked at the lab and retired only recently after close to 50-year career. So Isaac, welcome to the live stream.
Hi, Nader. Good to be here.
Yeah, good to see you. Probably hard to have imagined that you'd be attending an event like this, earlier on in your career. So I know you're going to share some of your science in a little bit, but since you had such a long and and celebrated career in the field, and in particular as a federal employee at a government lab, I thought maybe we could talk about that lab. It's the Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey. And that lab itself has a storied history. Actually, the lab itself grew out of the first numerical weather predictions that took place in Princeton at the Institute for Advanced Study. the GFDL laboratory, where Isaac worked and where I work, was also where the first climate models were built. And you've probably, for folks who've been following the stream, they've maybe heard about these early models built by Suki Manabe, one of the pioneers of climate modeling at GFDL, who then more recently won the Nobel Prize. And Suki was your PhD supervisor, Isaac. And so when you joined the lab, some of these groundbreaking discoveries were still in progress. So I'm wondering if you can just tell us a little bit of what the atmosphere was like at the lab, and if folks had a sense of how pathbreaking this was at the time.
When I arrived at GFDL as a graduate student at Princeton, Suki and Dick Weatherald had about 5 years earlier wrote their famous paper on the raging convective equilibrium and the first plausible estimates of climate sensitivity. And so that already seemed like ancient history at the time to me. I didn't really feel like that was a recent development at all. And everyone at the lab was busy trying to construct three-dimensional general circulation models at that point. And it was really exciting to see these first GCMs generating their results. And it was really a ideal situation for me in that I learned so much. You learn a lot by building these models and just playing with them and seeing what matters, what doesn't matter. And Suki was leading that effort, and Joe Smagurinsky was directing the laboratory, and he had a vision for the whole lab, basically a very clear goal of just we can do it. We can simulate the climate on a computer. And looking back, we were working with punch cards at the time, and IBM punch cards. There's no email, no way of electronically communicating code from one place to another. It's amazing what they accomplished at that time. Things have changed so much, but it was just exciting to talk to people. And our graduate program was very small, just 4 or 5 students, and made some lifelong friends in the graduate program. So, and met my wife, and we liked living in Central Jersey around Princeton, and came back after I had a postdoc, and it was just a perfect fit for me over time. And it was a remarkably stable environment. I think that was critical, because I think a lot of people have found out, those who've tried building these general circulation models of the atmosphere and trying to improve on existing ones, that it's time consuming. It requires a lot of different kinds of expertise. You really need stable funding, I think, over decades. Maybe things could be changing as new computational tools, new machine learning algorithms. I don't know, but through my career, it was critical to have that stability of funding, and so that people could really, make a lot of mistakes, figure out what's going on, and not, have some artificial deadline and when they had to report on their results. And, I think that was critical. So naturally, I'm not at the lab anymore. Maybe I say we sometimes, but that loss of stability is something that could really be serious in the next, if that takes place in the next few years, whatever the future brings. But
yeah, seems like GFDL and the path-breaking work that was done there is an excellent example of the kind of work that could only be done, with stable funding that government can provide. And maybe it's worth noting that, even the developments that you described, that Suki and Dick Weatherald had done their one-dimensional model 5 years earlier, and then building these coupled models also seemed to progress in stages, right, that took several years at a time. Is that right?
Yeah, and I think the key, in retrospect, the key was coupling the atmosphere to the ocean. So it wasn't just Suki. Of course, it was a pretty big group, but the oceanographic part was led by Kirk Bryan, who's a brilliant scientist. And Kirk and Suki had this beautiful friendship, and just lasted for 50 years. And they just worked so well together, and they had very complementary expertise in the atmosphere and the ocean, and they just made it work somehow, leading a group of really remarkable junior scientists. And yeah, so I think that was the key. And once that was established, I think it put GFDL several years ahead of, quote unquote, the competition. I feel like it's all this friendly competition in this field, and so there's just a remarkable number of things started emerging from that coupled atmosphere-ocean model, and a lot of decisions had to be made. And I think it's fair to say that if you look at the coupled atmosphere-ocean models that are being used today as part of the CMIP effort, which informs IPCC as to the state of climate modeling. Was that beep me or is that you? And
I'm not sure.
Okay. That you can still see the decisions that were made by Suki and Kirk when they first started coupling their models. You can still see those decisions. They have the models still look quite similar in their broad outlines to what they developed. I mean, there have been dramatic improvements in those models, and things are beginning to change more dramatically now with machine learning entering the picture. But yeah, it was just an exciting time in those days.
Yeah. So it sounds like what they did really kind of laid out a blueprint that we've been following for decades since, I guess.
Yeah, I think that's a fair statement.
Yeah. And, you mentioned being a PhD student in this graduate program that was, I think, especially at the time, a pretty unique joint effort between the federal government and Princeton University. Fund students who could, be educated formally through Princeton, but then work with folks at the lab. What role do you think that played in all this, if any?
Well, it's critical for me that over the years, I've been able to work with a lot of graduate students and postdocs through Princeton. And there are a lot of brilliant students, and I could never have accomplished what I did without those students and postdocs. And let's face it, the Princeton name attracts some really bright students to there. And that just helped a lot. And that's been, the program's been in existence for quite some time. It's also evolved quite a bit. But I think, initially it was justified, if you like, by the claim that it was pretty hard to get students educated in climate modeling and development of climate models. And this was one way to do it. And so it was pretty easy initially to get funding for the graduate program. But, over the years, climate modeling has taken off around the world. And you have to, the graduate program, I think you can argue, it's a little bit harder to justify the funding of it by the argument of uniqueness. You have to do it by the quality of the students. But we've been able to do that. And that combination, it's run now through this cooperative institute between Princeton and GFDL. And that is also being threatened, as I think you realize. So it's a complicated situation. And things are, I sort of was there during your relatively idyllic and protected. I feel very protected and lucky, and things make it more complicated.
Yeah. And you've talked about, the absolutely groundbreaking work that was done in developing the atmospheric model, the ocean model, coupling it together. And GFDL is known throughout the climate science community for that path-breaking work, but it's also known for the path-breaking science that came out of that. And that's part of what was honored with the Nobel Prize. Manabe and Brian as collaborators seemed very adept at doing first-rate science while also developing the models. That's also something that you're known for. How did that work, being able to do both? Or did they kind of automatically go hand in hand?
In some sense, I think it's automatic in that developing climate models and just, you could say, playing with them, that's what Suki used to refer to it as, is just a wonderful way of learning things about the climate system, what matters, what doesn't matter. But more structurally, when Joe Smorgrinsky set up the lab, it was, I think that was the intention, to work on fundamental climate dynamics and trying to understand the atmosphere and ocean. That was why those models were being built. It was only with time that the climate change issue sort of gradually became the key centerpiece of the coupled modeling effort. But it's always been understanding how things work. It's always been in the laboratory. I think it's written into the mission of GFDL. I don't have that in front of me, but that we're trying to understand the atmosphere, ocean climate system through the use of models.
And it sounds like from the beginning, that just kind of a basic curiosity was the main driver, and sort of the practical implications of climate change sort of start to come to bear, more gradually over time.
I was just getting started. I can't say what was in the mind of the early, Suki and Joe and Kirk, what applications they were thinking of at that time, but the fundamental understanding was always at the center, as well as the applications.
Yeah. So I think you're going to tell us a little bit about some of the work you've done studying how the spatial distribution of precipitation will change with global warming. Before you get into that and we share your slides, maybe you can tell us a little bit. You've worked on so many problems over the years. Why the winds blow from west to east in the mid-latitudes, and studying the macro turbulence of weather, amongst a host of other topics. What led you to thinking about the spatial distribution of precipitation in particular?
Well, let me get back to, when I start my presentation, hopefully I'll make that clear where this problem was motivated.
Great. So why don't we bring up the slides then?
Let me get started. Okay, do I have control of this? Yeah, so that's my title, The Changing Distribution of Precipitation as the Climate Warms. And this is a figure that I'll come back to later, but that's basically, this short talk is a discussion of this one figure. So let's see if I can animate this. This is infrared radiation escaping to space as seen from a bunch of satellites. It's a beautiful stitching together of, I think, 6 or more satellites, both geostationary and polar orbiting, giving you a global view from the South Pole to the North Pole of this outgoing long-wave radiation. And it's what you're really seeing is a measure of the temperature of the emitting surface. And so you see clouds, and if you look carefully, you can see the surface in the cloud-free regions. I think this is from the January, and so, for example, hopefully you can see Australia, and it's getting hot. Black is hot, and white is cold. So you can see the diurnal cycle. It also gives you a sense of time passing. I think it's about 1 second per day, if I'm not mistaken, about 1 Mississippi, 2 Mississippi. Oops. Let's go back to that. So time's flying by pretty quickly here. So that's what we're seeing. And this basically cloud distribution is telling us so much about the atmosphere and posing so many questions that when I'm getting a little depressed and feel like I'm, after doing this kind of thing for 50 years, it sometimes happens that you feel like you're not making much progress anymore and you're hitting your head against the wall. I like to go back to a figure like this, and having trouble keeping the animation going. Just to think about, how beautiful the system is, how many different interesting things are going on. One of the things that comes out immediately is this sharp distinction between the tropics, between about 30 north and 30 south. The equator is about halfway down here. I think you can see Africa and South America, maybe not so clear. But you have the tropics and the extratropics, let's call them. In the extratropics, what you have are waves, finite amplitude waves. It's a very interesting kind of turbulence. As I think Nader said, I like to call this the macro turbulence of the troposphere. These are the waves you see in weather maps. And they're responsible for among many other things, for the heat transport from the equator to the subtropics to the poles. And so they're setting the equator to pole temperature gradient, for example. In the tropics, what you see are not waves so much as just, it's almost like a boiling pot of water. You see much smaller scales dominating the circulation, and those scales are transporting heat mostly upward from the surface to the upper troposphere. And so you go from this more up and down small scale bubbling in the tropics to much larger scale, not necessarily purely horizontal, but sort of pancake-like structures that are very flat. It's almost like we're living in two different worlds, and rain is falling in very different ways in those two regions. And in between them, we have the subtropics, where things are relatively dry. So one of the first questions that I would ask about this, and that I've thought about quite a bit over the years, is just what determines where the subtropics are. Why isn't the tropical region that looks like a bubbling pot of water, why isn't that wider or narrower? And why does it give way at around 30 or so degrees of latitude, this more wave-like structure that we're familiar with in mid-latitudes? And is that latitudinal boundary between the tropics and the subtropics, does that change with global warming? I'm not going to talk about it here, but models suggest that the tropics should widen a bit as the climate warms. It's a little controversial. And it's also controversial to explain why that's happening. That's something I've thought about over the years. I've also tried to think about, in the exotropics, what determines how much heat is transported from the equator to the pole by these mid-latitude eddies, this kind of macro turbulence, wave-like turbulence in mid-latitudes. And does that change with global warming? And would that imply some change in north-south temperature gradient? So all sorts of questions like this that I and many other people have discussed. Does the latitude of these tropical rain belts, especially what we see in the Eastern Pacific, very linear, called intertropical convergence, does that move with warming? We think that we tend to move into the hemisphere that warms the most, and we expect the northern hemisphere to warm more quickly than the southern hemisphere, and so we expect some poleward movement of those tropical rain belts. All those questions are pretty complicated. They relate to how the circulation might change with warming. And today I want to talk about something a little simpler and think about what happens if the circulation doesn't change at all, or doesn't change significantly as the climate warms. And is that going to help us explain this picture? This is from one particular IPCC document, and I was thinking about this problem most intensively in the 2000s, the decade of the 2000s, and so I've taken a lot of these pictures from the fourth assessment report from the IPCC, which I think came out in 2007 or so. So this is a pattern of precipitation change that's expected over the about 100 years of the 21st century, according to all of the models examined by this intergovernmental panel on climate change, and trying to summarize that information. We're looking both at December, January, February on the left, and June, July, August on the right. So northern hemisphere winter on the left and southern hemisphere summer, and vice versa on the right. And the coloring is such that regions that get wetter, I don't know if this coloring makes that much sense, but Regions that are getting wetter are blue and that are projected to get wetter, and regions that are projected to get drier are brown. And you see that a lot of the subtropics is we're already dry, are projected to get drier. The tropical rain belt itself, at least some of it, is projected to get even wetter, and especially in higher latitudes, we expect the climate to get wetter, precipitation increase. And the magnitude of these changes expected over the next century or so are about plus or minus 20%, which is, if you think about it, that's a lot. That's a pretty big perturbation of the climate. We'd like to understand that number. And the interesting thing about this figure, before we go any further, I showed you the same plot of the temperature projections. It would all be positive, maybe with a slight bit of cooling projected in the extreme northern North Atlantic. But it'd be nothing like here. It's not like we're definitely not projecting that the Earth is going to get wetter everywhere. It's going, it has this interesting pattern. And if you look through multiple IPCC documents, you see this pattern has been very robust over the years. There have been changes in detail, of course, but this pattern is very robust. It seems like it should be something that we should be able to explain in relatively certain simple terms. So let's try to do that. And here's the one piece of physics I'm going to use. It's called the Clausius-Clapeyron equation. I hope I spelled Clapeyron right, by the way. Maybe someone in the chat can correct my spelling if it's incorrect. But this one of the most famous results from thermodynamics in the 19th century, just classical, the period of the development of classical thermodynamics. And it tells you how the saturation vapor pressure changes of a gas, changes with temperature. And here we're applying it to water vapor. And if you put in the molecular properties of water vapor, you find that the Clausius-Clapeyron equation predicts that the amount of water vapor that the atmosphere can hold, that how much water vapor is in the atmosphere when it's saturated, increases with temperature at about roughly 7 degrees per degree centigrade. It's more or less exponential, so you get 7% for every additional degree centigrade. So you get about 20% for a 3 degree centigrade warming. And if I went, the figure that I just showed you projecting the precipitation changes, if you look at the temperature changes predicted by those models over that roughly 100-year period, it's on the average is about 3 degrees centigrade. So the claim here will be that the Clausius-Clapeyron equation is telling us the magnitude, is explaining why those those precipitation changes were plus or minus 20 degrees centigrade, roughly. So I don't think that's a mystery. I think that's precisely what we expect. And so with warming, the saturation vapor pressure in the atmosphere increases, but does the vapor pressure itself increase? The ratio of those two is the relative humidity. So we're asking, is the relative humidity more or less conserved as the climate warms? And the answer, according to the models, and there are also a number of theoretical arguments we can make, that this degree of subsaturation that's measured by the relative humidity should be more or less conserved with warming. And so we expect the actual vapor to increase along with the saturation vapor pressure increasing with temperature. And we see that very clearly already happening. That this is microwave satellite measurements of just over the global oceans. I'm going to come back to this, and what's happening over the oceans is just a lot simpler than what's happening over land. Unfortunately, most of us live on land, so I'm going to have to come back to the. Okay, the actual water vapor in the atmosphere has been increasing. I think you hear about that quite a bit when people talk about global warming. And this is, the number here is percent per decade, but if you convert that into a percent per degree warming, globally, it's in the right ballpark for being explained by Clausius-Clapeyron and fixed relative humidity. And in fact, this figure always surprised me, and this is Brian Soden showed me this result in 2006, but it shouldn't have surprised me in retrospect. I don't think you need a model, but here we're taking a general circulation model of the atmosphere, and in this model we're constraining, this is critical, we're constraining the ocean temperature to be that observed, the surface temperature of the ocean. And you run the atmosphere over those observed surface temperatures, which have been warming. And you see what the vapor pressure in the model is averaged over the oceans for apples comparison with these satellite measurements. And it's almost perfect. There are no free parameters in this fit. They're the same quantity. And seeing that as the tropics warms, it's not true point by point in the tropics, but in this average sense, most of the evaporation is in the tropics, but averaged over the oceans, the water vapor has been increasing in perfect step with the warming of the surface oceans. And those are very tightly. I won't talk about the tightness of this further here, but it's really, I think it also has a relatively simple explanation. It's pretty impressive. So anyway, we expect the water vapor itself to increase with warming, not just the saturation vapor pressure. And this is something else that Brian Soden put together at that time. And a number of people have been thinking about this recently, re-examining this, including our host today. And that if you look at these same models and you look at how water vapor increases over the coming century in these projections, you see that that's the vertical axis is the percent increase in water vapor. I think this is just globally. It's not just over the ocean. You see, they differ somewhat in this percentage. If you compare these to the temperature change, these models, some models warm more, some models warm less. But the amount of water vapor increase is very nicely proportional to the temperature increase. But the global mean precipitation, and it also follows a roughly Clausius-Clapeyron scaling. Precipitation average over the whole Earth also increases. And this is a really interesting thing to think about. But that increase in precipitation is a lot less than the increase in the water vapor. And that has a lot of consequences that we won't be discussing here. By the way, I have no idea what other people have talked about during the 50 or so presentations that have preceded mine, which is kind of an interesting concept. So I could be repeating things that other people have said, but I don't think that's a problem, because if you're like me, you have to hear something at least 2 or 3 times before it starts sinking in. So people may have talked about this kind of figure before, but for our purposes here, it's just explaining why we see this pattern, which I'm going to claim is sometimes called the wet get wetter and the dry get drier pattern, is just a stronger. This pattern is increasing in amplitude more rapidly than the global average increase in precipitation. So what you see dominating the picture is the pattern and not the global mean precipitation. In fact, the precipitation doesn't scale very nicely with temperature. Okay, so this is a little flavor of the kind of thing I really enjoy doing. So why not talk about things that we really enjoy? And that is to start from a comprehensive climate model where you're trying to do the best you can to simulate the Earth, given all the physics that you know and your computational resources that are available to you, and call that a comprehensive climate model. And you take that and you simplify it in various ways. Why do that? It's testing your understanding and maybe discovering new things, new hypotheses to test. If you have a theory that this distribution of the change in precipitation is controlled simply by Clausius-Clapeyron and by an argument that I'll present in just a moment. That should be relevant in what we call here an aquaplanet model, which is take out all the continents, you take out the seasonal cycle, just have an atmosphere over this saturated water surface. And why is that so much simpler than the comprehensive model? Well, you don't have all these regional climates to think about. The land does have a lot of additional complexity. There's no dynamic ocean here. It's just a slab of water. And the climate of this model, it's still, this is a snapshot of the rain in this model. It still has these features that we're familiar with, this sharp distinction between the tropics and the exotropics. That climate is only a function of latitude, because by construction, you've made a model that's where the physics is symmetric in longitude and is also independent of the time of year. So you're going from a climate that's a function of latitude, longitude, and time of year into a climate that's just a function of latitude. So there's just less to think about, and it's a much simpler system. Interesting to test hypotheses. If the kind of argument I'm presenting here is going to apply to a more comprehensive model, and then presumably to the atmosphere as well, it has to apply to the simpler model as well. And so this, by the way, is the distribution of precipitation and evaporation as a function of latitude in this model. And in this model, the two hemispheres are identical too. So you get a symmetric pattern with a rainfall maximum that is also showing the evaporation here. The precipitation and the evaporation, of course, balance globally, but they don't balance locally. There's evaporation is relatively smooth, and but the precipitation has its maximum at the equator and in the mid-latitude rain belts and dry subtropics. So how does that happen? Because the only way that can, and by the way, when I say the wet get wetter and the dry get drier, this is really what I mean. You might ask, what does wet mean? What does dry mean? And wet in this context means precipitation is greater than evaporation, and dry means precipitation is less than evaporation. And we can subtract the precipitation from the evaporation. We get precipitation minus evaporation. You get this blue curve. And okay, I missed one slide, unfortunately. So how does this happen? Well, the only way this kind of situation can be maintained, if you think about it, is that the atmosphere is transporting water vapor, from these dry regions to these wet regions. There's a lot of evaporation in the subtropics. It's moving both into the tropics and into higher latitudes. And if the circulation, this is the key assumption, if the circulation isn't changing much, then these transports are going to increase just because the amount of water vapor in the atmosphere is increasing, which means that these horizontal fluxes of vapor are going to be increasing. So you're going to get more rain falling in the regions where you have precipitation exceeding evaporation. That is, in regions where you're converging water, you're just going to converge more water. And so you just put together a little model. It's almost embarrassing to call this a model, but I think it's legitimate. Models can be simple after all. And you can make a prediction of the change in precipitation minus evaporation. And all this precipitation, when you warm the climate, you're increasing the CO2 to warm this simple model. And there are no free parameters in this fit. The blue is the prediction. The red is what happens in this aquaplanet model when you warm the climate. And that's not perfect, of course, but it's telling you, giving you a pretty good picture, remarkably good picture for what happens in this ocean-only world. And evaporation itself doesn't change that much, so you're really getting a theory for the precipitation and not just the precipitation minus the evaporation. Again, it's a story here about why the evaporation doesn't change that much. Okay, does any of this happening? I think I may be talking a little too slowly, but over the oceans, we actually have a really interesting observational result that the salinity of the surface ocean is changing. I find this to be quite remarkable in that this is a picture of the sort of climatological distribution of salinity in the ocean. The Atlantic is pretty saline, and the subtropics are relatively saline. And so what are the trends in the surface salinity pattern over the past 50 years? This is a complicated thing to map to put together. It includes both recent, Argo float measurements. I think you've had some talks about the Argo float program, and there are some, earlier ship measurements as well. And the ocean integrates the response of the atmosphere. The atmosphere is very noisy. The ocean integrates out a lot of that noise and smooths it out, and so we get a distribution of salinity that we see the fresh getting fresher and the salty getting salter, which is precisely what you expect from precipitation over the ocean that increases in the regions that are already very rainy and decreases in the subtropics. And this is a lot of people are looking at this kind of way of trying to confirm what's happening in the past. If our simple picture works. Over land, it's more complicated. I think I may be running out of time, so I'm just going to say that, first of all, things are more complicated, and these mean changes in precipitation are just, I think, beginning to emerge from the noise. But it seems like there are other things that you can explain from these cautious Clapeyron-based arguments, including the fact that when you rain, you expect to rain more. And so precipitation gets more intense. And in these same models that I've been talking about, that happens everywhere. That happens both in dry regions and moist regions. And if you think about it for a moment, that's exactly what you expect. But to balance that, if you're going to dry in the subtropics, here we're looking at land, but then you have to have more dry days. So your precipitation has to be skewed if both the mean is drying and the precipitation, when it occurs, becomes more intense. I don't have too much time to say more about that, but this is my last slide, and this is a really unique time to be studying climate change. I think it's really exciting, and I hope it's exciting for the younger scientists entering this field. And it's one of the saddest things that's happened in the recent months, that the people who have suffered most from the personnel cuts, especially at government laboratories, are the youngest scientists. That's really heartbreaking. This is really, I hope we don't lose those people. They're saying why I find this time so exciting is that it's just that time that these trends are rising above the noise. And we've been making this prediction. We've been doing this experiment. When you do an experiment, the really exciting part is when the results start coming in, and you gathered enough statistics that you can really compare in detail to your predictions of our models. And some things have been relatively easy to study over the years, in the global mean temperature change, for example. But this distribution of precipitation is a pretty noisy thing, and as the signal rises above the noise, what happens, and this should not be a surprise to anyone, and this is what I think is the exciting part, in fact, that model deficiencies are emerging. This is when we really learn things. You don't learn that much if your models agree with the observations, the observed trends. So you really learn things when you see model deficiencies. Now, two quick examples, which I hope other people will be talking about during this streaming event. And one is that the land surface is, especially in semi-arid regions, seem to be drying out faster than our models are predicting. And the second example, which is a very important consequence, the second example is a little more complicated, but if you look at the equatorial Pacific, say the region where El Nino occurs, for example, models are predict that the equatorial Pacific should become more El Nino-like, with more warming in the east than in the west, but we haven't seen that pattern yet. In fact, the opposite may be happening, that the observed warming is larger in the east than the west. And that has profound importance for any regions which you can think of as any regions influenced by El Nino. These equatorial Pacific ocean temperatures have really dramatic consequences globally. And you might argue we should, for those regions that are affected really strongly by El Nino, we should probably have a moratorium on making detailed projections of regional climate change until we understand what's actually going on in the equatorial Pacific. So not to redouble our efforts at this time is a tragedy because this is when things are really happening, and if we don't do it, it limits our ability to adjust to the response with this evolving knowledge. So I better stop there because I've probably gone on too long. Sorry about that.
Thank you, Isaac, for that tour of your career and through this specific set of ideas that have had such an influence on our fields. I mean, like any other climate scientist, I've studied this wet get wetter paradigm, but hearing you talk about it from inception through conclusion has been really illuminating. We do only have a couple of minutes left, and so there's maybe one quick question here about the nature of these aquaplanets that you talked about. This may have been the first time on the stream that we've heard about those. And so there's a question here: wouldn't time of year affect the aquaplanet because of changes in insolation of the poles? The winter summer to climate, I think, would be drastically different.
Right. When in this particular situation, we replace the actual distribution of solar insolation, the energy coming from the sun, with a pattern that has the same annual mean as the observed insolation, but has no seasonal cycle. So there's no seasonally varying solar forcing here. Otherwise, you'd be absolutely correct. We'd have a large seasonal cycle potentially to worry about. Just because you remove land, you still have a seasonal cycle, but we've removed that explicitly.
Yeah, so those are the two big simplifications: no land and
right.
Removal of the seasonal cycle. And then kind of zooming out more generally, and maybe, consonant with your last point, given your long career, in your opinion, what's the most encouraging change you've seen in the public's understanding of climate from the beginning of your career to now?
That's an interesting question. Mostly we worry about the opposite of what is not getting through to the public. But I think the fact that the Earth is warming and that that's going to have an effect not just on the mean climate, which is mostly what I've talked about today, but on extremes. Extremes in climate affect people so much more directly than the mean. I think we shouldn't change the implications of changes in the mean climate for agriculture, water resources. There are some profound changes that occur because of the change in mean, but it's a little bit harder to convey, especially in a country like ours, where we're not that susceptible to, we're not as close to nature and as susceptible to these, 10 or 20% or 7% changes in the mean precipitation, but the science underlying the connections between these extremes and global warming is just growing exponentially. We shouldn't simplify it by saying all extremes are made more extreme by global warming. They each have their idiosyncrasies, but it's certainly an issue of real importance that we're going to be affecting extremes in climate and not just the mean. And I think that's coming through. If anything, sometimes people oversimplify, but so that's something we struggle with, to communicate but not to oversimplify.
Yeah, great. I think that's all we have time for. But Isaac, thank you so much for participating in this event and lending the depth of your career to these proceedings. So thank you again.
Sure. Well, thanks for the invitation and great job you're doing in this live stream.
All right. Goodbye, Isaac. So we just heard from a legend of climate science, and I assume that came across. If you're just joining us, this is the Weather and Climate live stream, 100 hours of weather and climate science. that you didn't think you wanted to know about, but you do. And you're finding that out now, watching the stream. We're at hour 56, and our next guest is Jeff Masters. Jeff Masters has had a long and storied career, and I think he's going to tell you some of those stories. He was a hurricane hunter, flying in planes into hurricanes. He's worked on climate communication through Yale Climate Connections, and he was one of the earliest people disseminating weather forecasts through the internet. And that's just a sample of what he's done. And I think today he's going to tell us about some of the wild rides that he's had as a hurricane hunter. So Jeff, take it away.
Okay, very good. Thank you so much. And let's see if I'm doing the right thing here. How are we doing here? Should I be sharing it differently than this, or?
I think you could go into presentation mode. We're seeing your thumbnails on the left there.
Oh, okay, presentation mode. So let's see.
Although it also looks pretty good, and so if that's the best we can do, I think it's okay.
Okay, fine. We'll just go with it as is here.
Let's roll with it.
All right, fine. So yeah, I mean, I've been a meteorologist for, gosh, since 1982. And I got a master's degree in 83. And between my master's and my PhD, you can see there was kind of a large gap there. I mean, 14 years between getting degrees. And I wasn't in school all that time. I took a break. And I decided that, you know, sitting behind a desk and doing obscure science and writing for journals was not for me. I wanted to go out and see the world, see the world's greatest weather, and work with some of the world's greatest climate and weather scientists. So I had the unique opportunity to fly with the hurricane hunters for 4 years. From 1986 to 1990, I worked as a meteorologist for the NOAA hurricane hunters out of Miami, Florida. And during that stay there, I got to fly through this beast, Hurricane Hugo, in 1989, which was a Cat 5 storm, one of two Cat 5s I flew through. I actually flew through Hurricane Gilbert as well in 1988, which was the strongest hurricane ever recorded in the Atlantic up to that time. So I'm going to tell you a little story about flying through a Category 5 storm, what that's like. I used to tell people that the most dangerous part of my day was driving to work in the morning, but that was not always true. And certainly on this day, it was not true. So for your edification, the NOAA hurricane hunters have 3 hurricane hunter aircraft right now. 2 are P3 Orion 4-engine turboprops, which was the kind of plane I flew through. And 1 is a high-altitude jet, which we didn't have back then. So we did a 2-plane mission out of Barbados in the Lesser Antilles Islands. And we based there to watch what eventually became Hurricane Hugo come off the coast of Africa. So here on September 10th, 1989 is the coast of Africa and the disturbance that became Hurricane Hugo. Here it is a day later. And a day after that, now it's a tropical storm. Gathering organization here. And now on September 14th, it has an eye. It's Category 1 hurricane. So off to the left of this image is the island of Barbados. And it's a situation where somebody's got to be the first to intercept a storm when you're flying with the hurricane hunters. You can only access storms that are within about a 3-hour plane ride of land. And so that means you go down to the Lesser Antilles to catch storms coming off the coast of Africa as they move across the main development region of the Atlantic. And for this particular storm, here's our crew deplaning in Barbados. We were a little bit of a press sensation as we arrived in the islands because they take hurricanes very seriously in the Lesser Antilles for good reason. So here's a picture of our 2 P3 Orion aircraft, Miss Piggy and Kermit, flying together. And if you look at the tail of these aircraft, you can see something kind of funny looking there. that is the tail Doppler radar that we carry. And there is the Doppler radar unveiled without its cone on. The only airborne Doppler radars in the world at that time. And there are only a few more since. And these aircraft didn't only go fly into hurricanes. In the winter, we would fly winter storms. Here's a shot of the project I did in Alaska in the Aleutian Islands one winter. So it was really a dream job for a meteorologist. In the summer, we'd fly hurricanes. In the winter, we'd go fly winter storms, or sometimes we do radical projects like we got to go to the shuttle test facility at Edwards Air Force Base in California and test out heat tiles on the space shuttle. We'd mount them on our wings, fly through rain showers, and see with our fancy instrumentation how they fared. So I got to work with the world's greatest scientists. I worked with T. Theodore Fujita, Dr. Tornado, back in 1987, studying severe thunderstorms and microbursts. And I worked with all the world's greatest hurricane scientists. Every mission that we flew into a hurricane, we'd carry researchers from NOAA's Hurricane Research Division. So what a dream job it was until it wasn't. And Hurricane Hugo was the flight where I decided that maybe I should be finding work behind a desk doing some quiet research somewhere. So this was actually my workspace on the NOAA P-3 aircraft. That's the flight director station. And my job on the airplane was to act as the liaison between the crew and the hurricane scientists. So the hurricane scientists would come up with a plan of what they wanted to do, the flight patterns they wanted to engage in the hurricane. And it was my responsibility to take that plan and work with the actual flight crew, the pilots and the engineers and so on, and execute it from a safe point of view. So I was responsible for safety of the mission from a meteorological point of view. So here we are getting ready to take off. This is a view from the cockpit. You can see our other aircraft in the background there getting ready to take off with us. And here's the view that we had taking off from Barbados, heading out towards Hurricane Hugo. So this is what we had to work with going out to the storm to plan for this mission. This was the satellite image from the GOES satellite showing what we suspected would be a Category 3 storm with 120 mile per hour winds. Now, as I was alluding to earlier, somebody's got to be the first. And we were the first Hurricane Hunter aircraft to go into Hugo. And it's always a bit of a nerve-wracking thing when you're the first to go in because you don't really know what you're going to find. I mean, yeah, you've got estimates from satellites, but the real truth comes from flying into the storms. That's why we do it. You can't just get all the data you need to know what a hurricane's doing from a satellite. You actually have to go beneath the clouds, which the satellites cannot see through so well, and take data. So we planned the mission to fly into what we thought would be a Category 3 hurricane. It was a 2-plane mission. I was on the low plane. We were going to go in at low altitude to try and sample the strongest winds of the hurricane, which is the most interesting part from a research standpoint. You really want to look under the hood and see what's going on near the surface of the ocean, because that's where the real intensification process gets going. Hurricanes are heat engines that pull heat energy from the oceans, converts it to the kinetic energy of their winds, and you really want to be able to study down low what's going on. And it's a bit of a risk, obviously, because the lower you fly to the ocean, the more dangerous it is. One downdraft can take you right into the ocean if you hit an exceptionally strong storm. So it's generally customary practice that you don't fly into a Category 3 hurricane at an altitude less than 10,000 feet. It's just not very safe. Now, we had gotten away with it the previous week in a different hurricane, a Cat 3 named Gabrielle. And we really wanted to get another data set to complement that one to study the interactions of the ocean surface with the atmosphere. So we said, hey, we got another Cat 3. We're going to try it again. We got away with it last week into Gabrielle. So, hey, let's go and fly into Hugo at 1,500 feet, which is quite low for any kind of hurricane, much less a Cat 3. So here's the view we had as we approached the first outer spiral band of the hurricane. This is called a feeder band. It's a little line of cumulus clouds that are spiraling into the center of the storm. And you can see kind of on the left of this image up high, that's the main cirrus shield that covers the storm itself. So now we're a little closer to the hurricane. Now we're underneath these cirrus clouds that cover the entire storm. And you can see the cumulus at the surface are starting to thicken up a little bit. And now we're approaching the first major spiral band of Hugo. The cumulus are getting quite tall, and we're getting ready to do our first penetration of what could be some significant turbulence. So there's the first spiral band of Hurricane Hugo in front of us. We had a good depiction of it from the radar. It showed, you know, we would probably encounter hurricane force winds of about 75 miles per hour. Our tail Doppler radar was telling us that. So we put on our heavy duty seat belts, fastened all the gear around the cabin that might potentially fly loose and cause trouble when we're in turbulence, and got ready to experience Hurricane Hugo. So here's the view I took looking out my window of the surface of the ocean at 1,500 feet in the hurricane. And that's a pretty typical scene of what you see in a hurricane. Winds are about 80 miles per hour here, causing, you know, a lot of blowing spray and some pretty significant whitecaps at the surface. So a little bit of a bump, you know, nothing worse than I've seen on a bad commercial air flight. So not a big deal. And we were confident that, yes, indeed, Hugo was going to be a Category 3 hurricane as advertised. Now, this is the radar display that we had to look at as we approached the storm. We approached from the southwest side on the lower left corner of this image, and you can see there's a pretty intense area of echoes, these pink colors. That was the spiral band we passed through. After we passed through that, it only lasted a half a minute or so. We broke into this moat region here, pretty much clear of echoes, and the wind speeds dropped to about 50 miles per hour here. And we again said, well, okay, only 50 mile per hour winds in the moat region of a hurricane. This is probably a Cat 3. But if you look at the radar presentation of the core of the hurricane here, you're seeing some pretty intense echoes here. These white colors here, we didn't notice at the time because we had some radar problems and we had scaled the radar for the previous flight a week ago. It was actually off scale. If you look at the scale of the radar here, the white colors, you don't have anything above that. So we were not seeing the full depiction of what was going on in the hurricane. And unbeknownst to us, we weren't getting the full picture either from that satellite estimate of the Category 3 strength we had of Hurricane Hugo. And that was because that year, 1989, normally you've got two what are called geostationary satellites measuring the hurricane, but one had burned out. So we only had one satellite, and they moved it over to an intermediate position over the eastern US. And now that single satellite was having a very oblique angle looking down at Hurricane Hugo from a great distance, and was not measuring the full intensity of the hurricane. So missing data was causing big troubles with our estimation of what this hurricane could do. Partially our fault from not scaling the radar correctly, and also partially from not having the kind of satellite data that normally we would have. So I took a look at this and said, yeah, okay, 1,500 feet in a Cat 3, we can do this. We did it last week. The world's top hurricane scientists were all on board the aircraft. And, you know, I looked to them for their experience as well. And they could have aborted the mission from a safety point of view as well by, you know, saying, well, maybe we should chance this at 1,500 feet. And the pilots also could have done the same. But none of the three of us took exception to the data we had in front of us and said, hey, maybe we shouldn't go into this storm at 1,500 feet. And as you look at it, the most intense echoes of the storm are on the southwest side, and that was directly where we were going to penetrate through. So we hit the eye wall of Hurricane Hugo at 1,500 feet. And right away, we knew we were in a bit of a stronger storm than advertised. The winds were Cat 4. They were 135 miles per hour, gusting higher. And we were starting to get some significant turbulence. Some, you know, updrafts and downdrafts were bouncing the plane around. But when you start to penetrate the eye wall of a hurricane, you're committed at that point. Your engines don't have enough power to climb to a higher safe altitude. You're just concerned with maintaining straight and level flight and gutting it out and getting into the calm eye. And you've only got to do it for about 2 minutes. That's how long it takes to get through the eye wall of a hurricane. So we said, okay, 2 minutes, we can probably do this. It's a Cat 4, but we've done Cat 4s once before at 1,500 feet. Back in 1980, this plane did it in Hurricane Allen. So 1 minute in, 1 minute to go. Now we're getting Cat 5 winds, and we're very concerned because we're getting 0 Gs. We're weightless. Now we're getting slammed down 2 Gs. Things we didn't fasten so well around the cabin are starting to vibrate loose and bounce around a little bit. This is not safe. We should not be at 1,500 feet in a Category 5 hurricane. It is very dangerous to do that. These updrafts and downdrafts we're seeing, they're on the order of 10 miles per hour. And if you get a really powerful downdraft, say of 30, 40 miles per hour, you're in danger of splashing the Atlantic Ocean. So, we grin and bear it. The intercom that we're all connected to, listening to each other, goes very silent, and you're not wanting to bug the pilots. They're fighting off those downdrafts. They're crabbing over the aircraft at about a 20-degree angle to correct for the 155, 160 mile per hour winds now that are blowing at the side of the aircraft. So now, just about 15 seconds from hitting the calm eye, we hit 3 Gs of acceleration. We hit an updraft of about 30 miles per hour, followed by a downdraft of 15 miles per hour. That's a lot of wind shear. I mean, if you think about having an updraft on the tail, a downdraft on the nose, the plane is bucking around like a Bronco. And then finally, it starts to lighten up outside. We're at the edge of the eye, and I'm thinking, hallelujah, we did it. We made it into the eye of a Category 5 hurricane at 1,500 feet. But right at that instant, as it started to lighten up out there, we hit the most incredible turbulence that a Hurricane Hunter aircraft has ever hit and survived. We hit 5.5 Gs and followed by 2.5 Gs in the negative direction. So the plane is getting slammed by the most incredible wind shear you can imagine. In 7 seconds, we hit an updraft of about 45 mile per hour, downdraft of 25, updraft of 30 miles per hour, all in the span of 7 seconds when the winds went from Cat 5 down to Cat 1 in horizontal. So the plane is literally skewing through the air, bucking around. The pilot lost control of the aircraft. The number 3 engine exploded into flames. We're feeling the heat through the fuselage of the aircraft. Things are flying around inside the aircraft. The 200-pound life raft broke loose, hit the ceiling, bent a bar up there, crashed down, missed people. The tool chest flew open, and there's chisels and hammers and stuff flying around inside. The ice chest in the galley broke loose, and there's sodas flying around, knives and forks. It was a miracle nobody got injured by all the flying stuff inside the cabin. And right at that moment, as the engine is in flames, we're sinking down out of control, we pop into the eye and see this. So the pilot pulled us out 800 feet above the waves in the eye of Hurricane Hugo and pulled the lever to extinguish the fire in the engine. And there we were in the eye of a Cat 5 at 800 feet, looking around us saying, holy cow. What do we do now? So the pilot saw in front of him a wall of clouds. He didn't quite know what to do. Is that the eye wall? Is that harmless scud inside the eye? So he made this really, really tight turn inside the eye to try and avoid what he thought might be the eye wall. And it turned out it was not. But we were at the edge of the eye, and he was trying to make an impossibly tight turn to stay in the eye. And we ended up putting a wing of the aircraft in the eye wall. We're getting bounced around again. But fortunately, well, with only 3 engines, one of the engines on the wing that's missing the engine is working really hard. It goes into the red zone. And we worried that we're going to burn out that engine too. So he had to partially fly with basically one wing in the eye wall to make that super tight turn. Finally, he leveled us out into the more or less center of the eye, and we were temporarily safe. safe enough that we could orbit the eye and take stock of our damage. So here's a photo of what it was like inside the eye as we're orbiting. That's our 200-pound life raft, that big orange thing there. A computer trailing its paper from the top. You can see it gashed a hole in the ceiling of the aircraft here. And these are our two flight engineers looking out the window, monitoring what's going on. And what they're monitoring is not good. And I'll tell you in a second what they were doing. So there's the galley, all the, knives and forks and stuff. You didn't want to go in the loo. It was a disaster in there. So what we ended up doing while we're orbiting the eye here, trying to figure out what to do, we're cleaning up all this, throwing everything we didn't know what to do with inside the head, so it would at least stay out of the way. And we were going to have to exit this hurricane again with only 3 engines now, and it was going to be a Cat 5. So we were very concerned for our survival. And this is the site that we had to see, surrounded on all sides by an impenetrable wall of intense cumulonimbus clouds that you could actually kind of see rotating slowly around you as you looked out. It was like being in a prison of blinding white. So we decided we needed to lighten the aircraft, because if you lighten up the plane, you can potentially climb higher and exit the storm at a safer altitude where there's less turbulence. So this is what it looks like to see a fuel dump. We dumped half of our fuel into the Atlantic Ocean to lighten the aircraft. We chucked all of our probes into the ocean, all of our drop sondes and all of our sonobuoys to measure the ocean. We had the most well-sampled hurricane ever inside the eye of that storm. And here's a little radar zoom shot showing our trajectory as we were orbiting in the eye. You can see on the left, here's where we penetrated through the most intense part of the eye wall. And now all these little circles are where we were circling inside the eye of Hugo, trying to gain altitude, trying to take stock of our situation. And we called for help. So our sister aircraft was actually quite a ways away. And, they hustled over and said, we'll come in the eye with you and scout you out for any potential damage. But it turned out there was an Air Force aircraft that was closer by that was also tasked with investigating the storm. And they came in the eye with us, and they spiraled down to our altitude. And those 2 pilots did the most incredible thing. Inside the 10-mile diameter shrinking eye of a Cat 5 hurricane, they did a close flyby. The Air Force aircraft trying to figure out if we had any extra damage on our aircraft to be reported on. And it turned out, yes, they did see there was actually a piece of debris hanging from the number 4 engine, the same wing as we lost our 1 engine that burned out on. And it was actually a de-icing boot, a piece of rubber that goes onto the engine to protect it from icing. And it had partially torn loose. And if it tore loose completely and got caught in propellers, it had the potential to destroy that engine. So they told us about that item, and they said, we don't see any other damage on you. And our pilot asked, okay, can you do us a really big favor and punch in and out of the eye wall of Hurricane Hugo to find a soft spot for us? And they said, sure. And they proceeded to do just that as we tried to climb higher. Now, there's 3 problems with trying to climb higher in the eye of a hurricane. 1, we were banked over at a sharp angle. That makes it tough to climb. 2, it's a low pressure system, so you're down 10%, so you've got less lift because there's less air. And 3, we're missing an engine, so we've got less thrust. So that plane, which normally gets up to 25,000 feet, could only get to 6,000 feet. So the Air Force aircraft very bravely punched in and out of the eye wall of Hurricane Hugo multiple times at 6,000 feet for us. And we were listening to their communications while they did it. And they, would tell us, whoa, 0 Gs, whoa, 3 Gs, don't go that way. And then, they try again, and oh, that was rough too. And finally, their 3rd penetration out, we were starting to get low on fuel because we dumped so much in the ocean. And we said, I sure hope you found us a soft spot. And they said, yes. If you look at the north eye wall here, there's a thin spot. Follow us out through that. It wasn't too rough. Yeah, the winds were gusting 200 miles per hour, still Cat 5 winds, but the turbulence was not bad. And sure enough, we followed them right out that weak part of the northern eye wall. Turbulence wasn't too bad. And we ferried back towards Barbados. Here's the view of the sun that I saw, praising the sun god vigorously as we headed back to Barbados. And there's the shot of our feathered number 3 engine as we ferried back to Barbados. You can see our sister plane up there escorting us home. And here's the shot of Barbados as we came into land, where they had all the, emergency trucks out there and ambulances, and just in case there was a problem. And we did have some trouble landing. I don't think the pilot was used to having only 3 engines on landing, and he caused a bit of a cloud of smoke as we landed because, having to do reverse thrust and hit the brakes. But everything was fine. The landing was a success, and that was my final flight with the Hurricane Hunters. So here's a cross-section view of the flights during the eye wall penetration. The thick black line is the horizontal winds, which got up to Cat 5 here. These things labeled 1, 2, and 3 are the updrafts and downdrafts that we hit in the eye wall of the hurricane. And what happened there? Well, it turned out we hit a tornado scale vortex embedded within the eye wall of the hurricane, something that had been suspected but never observed. And we had the bad/good fortune scientifically of actually observing one of these mesovortices, as they're called. And we do know now that they are quite common in intense hurricanes, and they can cause significant damage. They're responsible for a lot of intense damage you'll see in a major hurricane. So Hugo went on to clobber the Lesser Antilles, particularly the island of Montserrat, where it killed 10 people and did damage equivalent to 500% of their GDP. After Montserrat, it hit the Virgin Islands and winged Puerto Rico. Here's the view of El Yunque rainforest on Puerto Rico. And here is a press clipping of what happened in the island of St. Croix in the U.S. Virgin Islands, where they had to bring in federal troops. The hurricane was not done then. It went on and eventually hit South Carolina as a Category 4 storm. And this is actually the maximum storm surge that was observed just north of Charleston. 20-foot storm surge caused a tremendous amount of damage in North Carolina, including the severing of the bridge here to the mainland of one of the barrier islands. And Hurricane Hugo maintained its strength as a hurricane 140 miles inland all the way to North Carolina. And it cost $23 billion, which was the costliest hurricane on record at the time. So, intellectual exercise, guess where Hugo now ranks on the list of costliest hurricanes on record. This was 1989, about 35 years ago. How many more expensive hurricanes have there been? Well, I'll show you. It ranks number 19 now. And just in the last 8 years, we've had 10 more hurricanes. 10 of the top 19 most damaging hurricanes on record have occurred in the last 10 years. So we have gotten an unprecedented pummeling from major hurricanes in the US since 2017. Oh, and I need to go to this one. This shows the NOAA's billion-dollar disaster list since 1980, showing there's been a sharp increase in expensive hurricanes, billion-dollar hurricanes over the last 30, 40, 45 years now. And unfortunately, that database has now been discontinued, so it's going to be a lot harder to figure out what's going on. So what is going on? We're pretty sure that most of the reason that we're seeing increased hurricane damage is because there's more people with more stuff in harm's way. So there's simply a lot more development that's gone on. We're building in risky places foolishly. But we're also seeing climate change start to take an increasing effect. Now, it's a fact that when you put more heat energy in the oceans, you're going to see at the higher end stronger winds. And it doesn't take much of an increase in wind speed to cause a lot more damage. A Cat 4 does about 5 times the damage of a Cat 3. It's an exponential function. So if you increase the winds by just 5 or 10%, which we expect to happen with climate change increasing ocean temperatures, you're going to see a substantial increase in damage from hurricanes. In addition, you're going to see more storm surge damage because sea level rise is occurring because of climate change. And you're going to see heavier rains because a hotter ocean will evaporate more water vapor into the atmosphere, which will then fall as rain. So here's a plot since 1900 of category 4 and 5 storms that have hit the mainland US. You can see over the last 8 years, we've taken an unprecedented pummeling. Is that the harbinger of the future? We'll see. It would be really nice to know a lot more what's going on. And certainly the cuts to NOAA and the discontinuation of their billion-dollar weather database is not a helpful thing at all at a time when we need the most information we have about hurricanes. So I'll cut it short there. I've done my 30 minutes, and I'll take any questions that might be.
Oh my gosh, you have the chat in the palm of your hands. They were all completely gripped by that story. In fact, we have a lot of people saying that, asking if you have got any propositions to make this into a movie.
You know, it's been made into a episode of what's called Air Disaster, which is a Smithsonian Channel series where they've got a bunch of seasons. It's also called Mayday. And if you've got a subscription to, I believe it's Paramount Plus, you can see an episode called Into the Eye where I'm interviewed and the pilot's interviewed. It's a 45-minute thing where they put a set in Toronto and they shook it around to simulate flying through Hurricane Hugo. They hired actors to play all the people on the crew. So yeah, look for Air Disaster, aka Mayday, a 45-minute Smithsonian Channel episode. And there's actually a, if you search for it online, you can find a bootleg version of that episode in it's got Arabic subtitles, but it's all in English, the video. So it's been done.
Amazing. Okay, that's great. I hope everyone can go look that up. And I have one question before I get to the chat questions of my own. So you found the soft spot in the Cat 5. How would that soft spot compare to lesser, like, is it still worse than flying through a Cat 3 or Cat 4? Or is it comparable?
The soft spot was not that worse. It was like I was flying through a Cat 1. Not a big deal. In fact, my roughest commercial flight I've ever had was about equivalent turbulence. You can get some pretty bad turbulence on a commercial jetliner. Certainly, jet stream turbulence can be significant. So it was something that an ordinary airplane could probably have survived. But it's a really bad idea to fly an ordinary airplane through the eye wall of a hurricane because they fly so much faster. When you're flying very rapidly at, say, 500 miles per hour, wind shear is going to impact the airplane much more significantly than a 250 mile per hour penetration, which is what we would do, half that speed.
Okay. I mean, it's kind of related to these questions that are asking simply how that plane stayed together, especially with losing an engine and all the damage internally.
Yeah, I mean, these planes are tough. In fact, they've been in service since 1975. They've been re-winged. They put new wings on them a few years ago. They're scheduled to be removed from service in the year 2030, but the new NOAA budget doesn't have room for that now. So we may be without the NOAA hurricane hunters unless there's a substantial change in our attitude towards funding NOAA.
Gotcha. And I guess this is also the question I was curious of is this why you stopped flying into hurricanes, or was it scheduled beforehand?
I was going to leave anyway. It would not have been my last flight, but for the fact that we put this aircraft out of service for the year. It was done. It had to be ferried to what was called scheduled depot level maintenance. They took that airplane and they x-rayed every single rivet on it. They stripped it apart and examined it for damage because we were not at all sure that we had stressed it in major ways. That plane is only rated for 6 Gs of acceleration before the wings are supposed to snap off, and it hit 5.5. So that was a severe stress it took, and they found no hurricane-related damage to the aircraft except for, it turned out, a fuel controller failed on the number 3 engine, which caused that flame out that we had. So it was just that fuel controller, which was the only damage that Hugo did to the aircraft.
Wow, that's amazing. And I guess kind of related, maybe a little more gossipy. All Things Pi wants to know what your SFMR set while you're flying into. if it's safe to say.
We didn't have it on that flight. That was like the first year it started going on the aircraft, and for whatever reason, it was not installed on the flight at that time. And it's a lesson to you that it's not unusual for the satellite estimate of a hurricane strength to be off by a category or two. We've seen that in multiple cases now, particularly with violent hurricanes with a very tight eye. We saw that, I think, with Hurricane Patricia. The hurricane hunters flew in there and it had 215-mile-an-hour winds back in 2015. And I think satellite estimates were down maybe 180, so much weaker.
I guess all things I actually put that question as a joke, so I'm sorry. I've embarrassed them in the chat apparently. And I guess kind of so moving from your experience sort of into the science side of this, and you got into it a little bit at the end, but folks are asking, is it just the heat from climate change that's making these storms more intense, or are there other contributing factors?
Hurricanes are complicated. It's not just heat you need to get a hurricane. You have to have low wind shear as well. And it's unclear in the future climate whether we're going to see a increase in wind shear or lowering. I mean, there's some indication we'll see a decrease. So we'll actually see fewer hurricanes. But the ones that do form are going to have a higher upper end. When everything comes together, you've got a higher maximum potential intensity that these storms can get. So the other thing that you need is moist air to get a hurricane. And there's also some indication that you're going to have trouble getting moisture at mid-levels of the atmosphere in a future climate. So it could be the fact, this is what most hurricane models in the future are showing, you'll see a decrease in the total number of storms, but the stronger storms will get stronger because they're heat engines. If there's more heat available, when everything else goes right, then you're going to get a high-end storm. And the highest end, we're going to see 215-mile-an-hour storms like we saw in 2015 with Patricia in the Eastern Pacific.
And then, so from climate change to sort of today's outlook, do you have any thoughts on, we're just about to start hurricane season. Any thoughts on what's to come?
Yeah, I mean, the oceans are a lot cooler than they were last year, but they're still top 5, top 6 on record in the main development region for hurricanes, at least the Caribbean part of it. The Gulf of Mexico is also near record warm. So that's a lot of heat energy. And we don't know what the steering currents are going to do yet. I mean, we're due for a break. We've just gotten pummeled every single year since 2017 with a major hurricane landfall, except maybe one year. Maybe we'll get a break this year. We're due for one, but no way of telling at this point. And the right forecast is for an above average season with probably at least 3 hurricane landfalls in the US, one of them being a major.
Yeah. And I guess I'm jumping around. There's so many good questions you've got here. G. Willikers is asking, obviously you got a lot of data from much of the tools you used, but you dropped a ton of stuff. Were you able to get measurements from all of them? Or were some just lost in the sea?
Yeah, I mean, it was oversampled. I mean, there's only so much data you can get from a single point where you throw all those probes in there. But there was a paper written on Hurricane Hugo led by Frank Marks, who was the director of the Hurricane Research Division of NOAA at the time, just retired. So you can read that paper, and it's considered a bit of a classic paper in the field because it was the first time we observed a mesovortice in the eye wall of a hurricane.
Yeah, I mean, you definitely got good data out of it, despite it seems like a pretty harrowing experience.
Yeah, like I was mentioning earlier, I was going to be done anyway. I had gotten accepted to PhD school, so I did leave after that season, even though I never flew the rest of that season. That was the end of my tenure at NOAA. So I went on, got my PhD in 7 years, got a little distracted by co-founding Weather Underground, and then starting in 2005, I started writing blogs about hurricanes again. So here I am. It's been 20 years now. I've been writing blogs about hurricanes, and I'll do it again this year.
Amazing. Yeah. And I guess kind of even going further back, we have one person, G. Willikers, once again asking, how did you get into doing that kind of work to start with?
I just saw a job. I was looking at the government billboards, and the job was advertised, and I said, oh, well, I'll never get this job, but hey, I'll apply for it anyway. And, 3 months later, here was the director of the Aircraft Operations Center giving me a call saying, "You're hired if you want it." And I was like, yes, I'll take that job. Being young and in my 20s and indestructible, that was a job exactly I wanted.
That's amazing. Like, were there any qualifications you had from anything, or you just?
Well, I had a master's degree and I'd published some research, and the job was more than just flying into hurricanes. Afterwards, you were responsible for doing research. I would research calibrations of the instruments, how to make better wind measurements from an aircraft. Turns out it's hard to make a precise measurement within a mile per hour of the wind speed of a hurricane when you're flying at 250 miles per hour. Small difference between two large numbers. You have to subtract off the velocity of the aircraft from what you're measuring the airspeed to be. And it's a tough problem. So I was a very successful researcher, published a couple papers when I was with the hurricane hunters, and that's what they wanted. They wanted somebody who could do research.
That makes sense. Yeah, and then I guess you put it to good use. I don't know, we have 2 minutes left here if you want to give any kind of spiel about what you went on to do after your PhD.
Well, I went on and founded the Weather Underground, and I'm retired from that pretty much now. I'm volunteering with Yale Climate Connections, still writing about weather, extreme weather, and climate change. And I'll keep doing that as long as we're continuing to move towards the future we are. I mean, I encourage everyone to read one of my posts I did called "When Will Climate Change Turn Life in the US Upside Down?" It's already begun some. We're not ready. It's going to get very extreme. And if you live in a high-risk area, you better pay attention to your value of your property if you own property, because that's the first domino that's going to fall. The climate change crisis is going to be the most important thing in almost everybody's life. I don't know when that's going to start, sometime in the next 15 years. It could be any year. It could start this year or next year. We don't know. But extreme weather is an extreme threat to society, and I will continue to write about that. And I'm very interested in keeping people who need to be aware of the most important things that are happening in the weather and climate change world.
And we are very glad that you're doing that. I know other talks have already shared some articles from Yale Climate Connections, and we're so grateful that you came on the stream and told us the story. I mean, obviously the chat had an incredible time. People are going back and rewatching it at 2x speed. So thank you so much for stopping by. And we're gonna move on to our next talk now.
Thanks, Miriam.
All right, so real quick, we're halfway through the 57th hour. We've been doing this for a long time. Thank you to everyone who's been here for many of, if not all of the hours, although I hope no one's been here the whole time. I hope people are sleeping. I'm just gonna real quick up top say hi, I'm Miriam. I haven't been live except for a little blip. I'm a PhD student studying hydroclimate extremes. And I'm hosting for the next hour and a half. And I just want to remind everyone while we're here, we're sharing our science. All of these incredible researchers and meteorologists are taking time out of their day at sometimes very strange hours. It's 9:30 p.m. here in New York to tell you about all the freaking fantastic work that they're doing, often funded by federal government funding. And as you've heard over and over through the stream, a lot of that is getting cut or is under risk of really strong cuts. So you can see in this banner going across the bottom half of the screen right now, we've made a little handy URL that you can go to call your representatives and tell them, if you've heard any really wonderful science that's inspired you or you didn't know about, you can call your representatives and tell them just how important it is just the future of our forecasts, general science knowledge in general twice, sorry. Let them know why this is all worth doing. And hopefully there's a script so you can say something much more coherent than what I just said.
It's 10:15 in New York, so we've just entered into the 58th hour, if the ticker is correct, which is amazing. Can I do the math? How much we have left? 42, right? 42 hours remaining. So at the top of the hour, Susanna kind of teed this up for us a few minutes ago, but reminder that we are here because we are seeing decreases in funding for weather and climate science. And we've heard from countless speakers about how that's affecting their ability to do research and the ability to hire postdocs and doctoral students, and having all these ramifications throughout our ability to forecast the weather, warn us before these hurricanes hit, whether inland or on the coasts. So if you have a chance and you're bored of us saying this every time in between speakers, that's the perfect time to head to wclivestream.com/act. But with that, I'm going to introduce our next speaker, who is Jen Kay, and is going to give us an incredible talk on advancing polar science as the world warms. Presumably. Maybe?
Hello.
Yeah, great. Hello, welcome to the stream.
Good evening, all. Yeah, thanks so much for tuning in and for the organizers for the opportunity to speak. We're going to do something really different than hurricanes. I've been listening to the last couple of speakers and also to Isaac, and they all just gave such fantastic talks. We're going to talk about the polar regions and also about climate change and variability in this talk. And so, yeah, I'll start with this background slide, which is just some sea ice off the coast of Alaska. Sea ice forms when the ocean freezes. And this is some first year ice. So it just formed and was very thin, about 40 centimeters thick. And I was up in Alaska doing some field research. And, it's really interesting to be way up there doing research. You're really, off the grid in so many ways. There's things like seals that you might pass by. But this particular sea ice was very, very thin and unexpectedly thin for us. So, we almost fell through, which was pretty insane. Anyways, the polar regions are really fascinating. They're cold. There's a lot of ice up there. And, that ice starts to melt as you warm things. I mean, we all know this from an ice cube melting in our warm summer drink. But, one of the things that's so fascinating to me is just we have information about the spatial pattern of where the temperatures have increased the most. And it's at these high northern latitudes. And those high northern latitudes, there's not a ton of people living up there. There are people living up there, though, and they are very affected by this. And so, one natural question you might have is, why do we care what's happening way up there when no one's living up there? And I think that's an interesting question. As a scientist, I find it fascinating to understand what controls the spatial pattern of warming and whether we can reproduce that in models. But from a society standpoint, there's a lot of ice up there and we can melt that ice, and that changes things. It changes, our navigability of the ocean. We can, now get across the Arctic Ocean in a boat a lot easier without an icebreaker. But also some of that ice that melts, if it formed first on the land and then goes into the ocean, it can contribute to sea level rise. And so, even if you're not living in the poles, if you live close to the ocean, which many people do, you'll be affected by melting ice many, many, many miles or kilometers away from you. So here's just an example of what you might find if you head up to the Arctic in the late summer. This is September of 2012, which is the lowest monthly Arctic sea ice extent on the satellite record that we have. And it's just crazy. You can get in a ship and circumnavigate the North Pole. If you wanted to take a boat from Canada to Russia, you can do it. And 2012 was a pretty low year, but there's many years where this kind of navigability is increasing, and we can move things across the Arctic Ocean. And I always find this fascinating because when I was in middle school, I remember reading about the expeditions in kind of the northern Canadian archipelago and how it was impossible to get through some of these straits, and there was so much ice. And it's just such a visible example of how, we've changed the planet and really, changed the amount of ice at our polar ice cap. It's something you could see from space and that has a lot of, geopolitical and, environmental consequences. So you might ask if this came as a surprise to scientists. And actually, one of the fascinating things is that observed Arctic sea ice loss and greater than global Arctic warming were actually predicted decades ago. They were predicted by, some of the earliest climate models that we have. So like Manabe and Stouffer, 1980, here's a direct quote from their paper. The CO2-induced warming of the surface air is particularly large in the high latitudes. And so here's, the state of the art in those days, which was a lot of printouts. And, here's their supercomputer with 0.5 megabyte of memory. I mean, you don't have to know much about memory to know that, even just the pictures that you're looking at on your screen have more memory than this supercomputer. And it took up an entire room. So you had to be really careful. These early scientists were really good at thinking about what the physics were that, they wanted to include in their model, because there wasn't a lot of supercomputing power to run the numerical solutions to the equations that they wanted to solve. And so taken together, that's pretty fascinating that they were able to make these predictions, that the Arctic was going to warm more than the lower latitudes. So here's just a couple of the key figures from some of these early papers. And one of them is just showing how the Arctic and also the entire globe responds to a quadrupling of carbon dioxide. And what you can see is that the largest numbers are actually at the surface near the North Pole. So 90 degrees north, you have 9, 8, 7 degrees Celsius of warming near the surface. And that warming is really associated with changes in the ocean in these models that were run. And the change in the ocean was a change in the phase of the ocean. So the models had a sea ice component in them. So the ocean is changing phase from being ice to being liquid. And that change in the phase of the ocean leads to some pretty unique positive feedbacks. So these are feedbacks that amplify the amount of warming that you get. That's because it's positive. Positive means that it amplifies. A negative feedback just means that it dampens. And so these, early models really saw that associated with summer ocean heat gain and delayed surface warming in regions of sea ice loss, you could really get some of the most important feedbacks for explaining why the polar regions, and in this case, the Arctic, warmed more than the lower latitudes. So I've been always very impressed with these early papers, and I was really flattered when I got tenure that I actually received a cutting of a begonia. And this begonia has a long story, actually. So it came to me from a scientist who's a mentor of mine, and she got it from her dad, who got it from Suki Manabe, who got it from Einstein. So this plant has quite the history. And during the pandemic, I spent a lot of time, at home trying to do science and, write papers. I did some really cool numerical model experiments, often inspired by some of the early climate model simulations that were done by Suki Manabe. So I was just thrilled when he, along with others, won the Nobel Prize in Physics. It was so well-deserving. And you think about the tools that these early scientists had in climate, our field, and what they did with them. And it's just amazing. So every time I read the Manabe papers, other papers from that era, and really think about how this work was done, with these computers with 0.5 megabyte of memory, I'm just really, really impressed and inspired. And so, yeah, I'm glad I have this begonia, and I'm happy to share a cutting if anyone wants one. So I guess I just want to talk a little bit about the science that really, I think, changes our views on things. Obviously, being able to know what equations to solve is great, but you need observations too. Observations are really important. And what we learn from making new observations of uncharted territory teaches us so much. So, in my own personal circumstances, I, was really strongly influenced by the launch of 2 satellites in 2006. And they were pair, CloudSat and Calypso, a spaceborne LiDAR and radar. Yes, lasers in space, radars in space. They measure the vertical structure of clouds and precipitation over the whole globe. We had never had observations like those before. And I was really lucky. I was finishing my PhD and I saw this, ad for a postdoc, and I thought, okay, this is great. I'm going to go look at these new observations, and I'm going to try to understand how to incorporate them into global climate models. And so it was a real opportunity, and really lucky to be able to work with these data and to really learn a lot from them. I've had amazing mentors through my scientific career. Leaving the end of my PhD, I did my PhD on cloud microphysics. So the really small scale processes that affect the way that clouds evolve in the atmosphere, a lot of that is happening kind of at the micron scale. So, well below what you would try to directly simulate in a global model. And so it was really inspiring to think about how to take what I had learned in my PhD at this really micro scale and try to apply it at a global scale and really try to understand how these processes affected the climate system. And that's really what I've done through my career. And it's really been motivated by trying to understand how our planet is changing and what the implications are, for us and, for everyone who comes after us. So I really like this quote, which comes from actually a geologist. Scientific discoveries occur when one associates oneself with new observations of what appear to be prominent yet unexplored or poorly understood features of Earth. And so, the polar regions, the vertical structure of clouds and precipitation, these are really rich areas where we don't have a ton of observations, and we don't have a long record sometimes going back. There's no paleoclimate of clouds. Clouds are more ephemeral than that. So it's really, really fun to think about these things and to try to understand what we might learn. So, discoveries happen when you collect new observations. And the first 2 years of these spaceborne radar and LiDAR were really interesting years in the Arctic especially. 2007 was a really low year for Arctic sea ice. So the ocean was much more water covered than ice covered. And one of the discoveries that we made with these new satellites was just trying to understand how clouds influence that, dramatic drop in sea ice that happened from 2006 to 2007. And basically what we observed with the satellites was that there were a lot fewer clouds in 2007 than there were in 2006. And that, along with, an anomalous atmospheric circulation, which brought a lot of moist air from lower latitudes, the associated ocean processes, all of these things worked together to cause this big drop from one year to the next. And I think, people often ask, why are you talking about the clouds? There's always this expression, where the wind blows, the ice goes. So all you need to know to understand how sea ice works is the winds. But really, understanding sea ice really involves understanding shortwave radiation, because that's what's melting the sea ice in the summer in the high northern latitudes. And so, this cartoon here, a lot of people think of the high latitudes as, okay, the sun comes in, it melts the surface. The surface, if it's ice, it gets darker. And then if it's a darker surface, it's going to absorb more sunlight. And then it's this positive feedback that leads to more ice loss. Well, in reality, the Arctic is a very cloudy place. So a lot of that light from the sun doesn't even make it to the surface. And so, in kind of an end member or an extreme scenario, you could basically shut down all of this positive feedbacks that are enabled by absorbing sunlight in the surface ocean. The real world is obviously somewhere in between, but it shows you the importance of being able to measure the clouds at the high latitudes and understand what's going on up there. So we published this work as scientists do. The first version of it was rejected. That happens all of the time. We get used to that, and we always are improving and trying to think about, okay, how is our science? How can we make it better? And the reasons that it was rejected were that the reviewers wanted more context. They wanted to know why this was important, and so we added to the paper, and the paper just got better. And that's what scientists do. We really care about what each other think, and so we work hard to make things better and really understand things and push things as much as we can. And so the conclusion from this paper was basically that in a warmer world with thinner ice, we have natural summertime circulation and cloud variability, but they become increasingly important for controlling how much ice we have in the Arctic Ocean for the sea ice extent. So we continue to make additional discoveries related to this. That was just 2 years where we were looking, but we continue to look at how the sunlight and how much was absorbed in the surface ocean changed and how it was associated with sea ice loss. And what we really started to see was this consistent picture that over time, we were seeing more shortwave radiation being absorbed, and that was due to the loss of ice. And so, we published this paper in 2016 where we tried to look at these relationships spatially. We're scientists, we make a lot of maps, and we try to look at longer term trends. And, just today, I was having a conversation with a couple of colleagues about how we want to continue to do this kind of work and think about how these things have even changed since 2016. So we're always updating our science and thinking of new things and what comes next. One of the things that I think is really important to note is, yes, the clouds are present in the Arctic, but you might think, how are the clouds changing? Are they changing as you're getting more open water and you have less sea ice up at the high latitudes? And this is another thing that we advanced, was thinking about the air-sea coupling hypothesis. So this idea that in the middle of the summer, there's actually not a strong response of the clouds to summer sea ice loss. But we are seeing evidence for clouds increasing over newly open water during fall. And this is the kind of thing we can look at in our spaceborne radar and LiDAR observations, but also things you can just see with your eyes. So these are just two visible images, one from July and one from September. The one from July, you can kind of see some clouds floating around and some sea ice, but you don't see any obvious connection between the two. And then in the bottom, we see these typical roll clouds. These are indicative of low level convection, so strong coupling between the lower atmosphere and the surface ocean below. So all of this is really, from NASA observations. These are observations from the MODIS satellite, and also the spaceborne radar and LiDAR, also from NASA. And so, this is just another paper that kind of looks at the observations showing a small impact of the cloud sea ice feedbacks on the observed warming. This looked over many years and just made profiles of the clouds over sea ice and over open water. And basically, I was shocked when I saw this figure that was made by my former student, Ariel Morrison, and she found basically that the clouds over open water and over sea ice were almost identical, which is really interesting to see. And then in the fall, these increases in low-level clouds associated with the opening of the Arctic Ocean. So I'm going to transition a little bit here. I've been talking about observations, especially those from satellites launched by NASA. I think those are super useful and helpful. But obviously, if you want to go into the future, you need to have some sort of basis for doing so. And I really like this quote, prediction is very difficult, especially about the future. So, as scientists, especially, weather and climate scientists, we're making predictions all of the time. And it's a hard thing to do. And you really have to understand, first of all, where there is predictability, where you expect to have skill, and also, what the limits are for the types of predictions that you're going to make. Because, if I were to ask you, what's the weather going to be like on your birthday next year, you're very aware that, probably there's not a 38-day or 200-day forecast out there, right? Depending on how many days away your birthday is. And that's because there's limits to how much we can forecast the weather. The climate system, the weather systems, there's limits to how predictable they are. And so that's why we can't predict the weather on your birthday. If we could, we would certainly try, but we know, after a couple of weeks, we don't have a lot of skill, and that's just because the atmosphere is super chaotic. So, it's really important to emphasize that this kind of uncertainty, is not ignorance. And I think about this a lot in terms of uncertainty sources for climate projections. So there's kind of three main sources of uncertainty here. The first is related to the internally generated variability. And this variability is intrinsic to any given climate state. So it existed, before humans, it'll exist, forever. And it basically is uncertainty we cannot reduce. So we need to live with that variability. And we're all familiar with that, through the day-to-day fluctuations in weather. It may be summer, but one day in summer is really, really hot, and one day in summer is really cold. And that's just the variability that we have in our system. But there's some other drivers here. Obviously, the forcing uncertainty is important. It does matter, for example, how many greenhouse gases we have in our atmosphere. We have other small, tiny reflecting particles in our atmosphere called aerosols. Those all affect, the climate. And so if we're doing things to change the CO2 or the little particles in our atmosphere, like aerosols, they're really going to affect our climate. And there's some uncertainty in how much, we're going to do there. I want to say that a lot of that uncertainty looking into the future relates to human decisions. So it's, not really in the hands of scientists. We try to plan for a range of outcomes and give people a good sense of what you might expect, but we don't know exactly what's going to happen in terms of greenhouse gas emissions, for example. And then the third thing, this is, what everybody thinks scientists do, physical process uncertainty. And indeed, this is where we can make an effort to really reduce uncertainty by understanding and modeling the physical processes of the system. And, the understanding has to come first because we have to translate that understanding into equations that we use in our models to predict what the future is going to be. So that's kind of where our role is there. So one of the tools that gets used for trying to understand sort of these different sources of uncertainty and, to make projections and also test scientific hypotheses are these kind of global coupled models. One example, the Community Earth System model, but there's a number of these models that are developed at different centers around the world. And the core of these models is just a coupled atmosphere, ocean, land, sea ice, land ice model. And they're run at a variety of different resolutions, with, of course, the higher resolutions and the horizontal being a lot more expensive to run, so you don't get to run as much. Many, many lines of computer code. This is not the kind of thing I can solve on my laptop computer. You need a really big supercomputer to do it. Many, many lines of computer code go into them. But the thing that's really amazing about these models is, well, first, just how much physics and how much, people power has to go to make them, but just also that they have these emergent features. We see things like El Nino and La Nina in them. We see global warming in them. And, those are things that emerge from the physics that we write up as equations and try to predict what's going to happen. So that's, I think, really, really cool. So I'm going to end this discussion here talking a little bit about a project that I was involved with, co-leading actually with Clara Zasser, who's a scientist in Boulder. And this project has really been an amazing project. It was designed as a community resource for studying climate change in the presence of internal climate variability. And it's really served as a foundation for many other studies in our field. And that's because it really tries to understand how the climate is changing and also how much variability we expect too. So what do I mean by variability? I talked about that a little bit as an irreducible source of uncertainty, but let me just return to it just to make sure we're all on the same page. So internal climate variability, this is unforced climate variability intrinsic to any given climate state. And it arises from atmospheric, oceanic, land, and cryospheric processes. Cryosphere is just the ice, and they're coupled interactions. And this is a source of variability that's just around in our system. It's always will be. It's especially large on small spatial timescales and on short timescales. So you can average to kind of beat down the noise of the internal climate variability by looking at, a long time series where you have a lot of different events, so you can average over all the variability, or by doing things like taking the global mean, where you're averaging over all the spatial variability. So this variability, again, it's chaotic. We've known about it for a while. And in fact, this internal climate variability was discovered in the climate world, by Ed Lorenz, a faculty member at MIT. And basically what the scientists were doing was looking at sensitivity in their models, and they reran their model, the exact same equations, the exact same initial condition, and just a small little difference at the beginning. And they found chaos. They found their two solutions diverged. So same equations, slightly different initial conditions, kind of like at the level of, the numerical round off error of the computer, and they got a different answer. And that's because, the climate system, there's a lot of nonlinearities in it. It's chaotic, it's sensitive to small perturbations. And it's one of the reasons that our forecast skills, for example, for weather forecasting, are really limited in time. Some other implications: model simulations with slightly different initial conditions will evolve differently due to the internal variability. And then also the timing of unforced events, we see them differently, and that's okay. The climate system is going to have slight differences in the timing of events. We really need to understand the statistics, and that's what climate is. It's the statistics of things. So what's so cool is that, we've really evolved a lot from the 1970s, and we have a lot of supercomputing power. And so we can really represent more processes and run at higher resolutions with our numerical models of the atmosphere and of the climate system. And one of the things that we do is really try to probe this variability, this internal climate variability. So one of the ways that we do that is we run long simulations with constant forcing. These are often called control runs. So perpetual 1850, and we see some variability in the global mean surface temperature. But we can also do things like rerun experiments multiple times with small differences in the initial condition. And now, instead of making one forecast for how the climate is going to change into the future, we make 30. And all of those forecasts, all of those predictions, they share the same model. They're run by the same greenhouse gas, other external sun forcing, volcano forcings, but they have a small difference in their initial condition, in this case, a 10 to the minus 14th air temperature difference. And just that little tickle, just like Ed Lorenz's model, is enough to send these projections into slightly different directions. And so it helps us plan for the future by knowing just, what is the spread and expectations of the future climate that we might have that's due to this internal climate variability alone. So yeah, we can start to look. This was one of the first plots. We were looking to try to make sure, we have this descent into chaos. We definitely see at the beginning all the members together, and then they start to spread out. This project produced a lot of output. It has a lot of citations, and it's been used in all different ways. Like, there's people using this as a test bed for machine learning studies. There's people using this to try to understand the hydrologic cycle and how it changes under warming, and all of these different things. So it's really an exciting and useful tool for our field. So I'm going to wrap up here because I think I'm out of time. Maybe went a little bit too many in the plots, just end just by giving some advice for advancing science. It's really important at this time that we continue to advance science and ask and answer important science questions. It's really important that we have observations and models to make discoveries and to inform our understanding of things. And it's really important that we communicate. We need to communicate important information so that everyone can make good decisions and, work with colleagues together all over the globe to do this. So thank you very much. Thanks for having me, and I'll stop there.
Thank you so much. That was absolutely wonderful. You covered, your whole career. You explained some of the more difficult to translate ideas of uncertainties. You explained what a climate model is. You really just kind of took this whole live stream. You're like, can I put it all in one little 45-minute talk? That was amazing.
Might have tried to do too much, but there we go. You can always, contact me. I'm happy to chat more.
No, it was wonderful. And I think people were definitely really liking it. If you get a chance to look at the chat, we're seeing people like, this is fascinating. They're having a great time. And I think we got to go all the way back to the beginning, though, because everyone's still talking about the begonia that you have. And Mr. Radisheim has this wonderful comment about how it's such a beautiful metaphor for, like scientific family trees and how all our work builds on top of each other. But we also want to know, do you know what species of begonia it is?
Oh my gosh, no, don't.
Okay.
These silver speckles on it. It's beautiful. And sometimes it blooms. It's just
wow. Do we have any plant people in the chat who can start telling us begonia species? I also don't. I love plants. I have a lot of them, but I don't know anything about them species wise. Okay, so from that kind of lovely thing, we're going to jump straight into a geoengineering question. So Fish, who's been all over our chat, has asked, they've heard of a project that wants to artificially create sea ice to help albedo and slow down climate change a little. Do you think that's effective? Is it possible? Do you have any warning signs?
Yeah, geoengineering is a very sensitive topic, so I won't dive into it too much, but just to say that I think the tools that we develop, for example, these coupled Earth system models, I think are good ways to test ideas and see if they're possible or feasible. Yeah, so I think it's really important. Maybe that's a good message to send, that, if you want to do something in the environment, testing it in a model is a really good way to start. And then if you make a mistake, at least, yeah. Angel wing begonia. Oh,
that's a beautiful name, if true. Yeah, I think I'll kind of echo that sentiment. I think I work a lot with climate models, and one of the beautiful things about it is you can do all sorts of weird stuff. All of your weird ideas, like you can put volcanoes everywhere. You can, turn everything into a desert, see what happens. It's fun to play in that sandbox. Less so with our actual only single Earth.
Yeah.
So you kind of covered that you used a lot of satellite data, but Mark is curious if you're using any kind of ground-based observations as well, if you want to talk about that.
Yeah, that's a great question. So I use ground-based observations more by trying to understand processes and stuff. But my interests are often in how things are changing over an entire region, over a couple of decades or even a couple of years, and it's really just hard to be on the ground everywhere. And so it's limiting. You kind of have to know the limitations of the different observational strategies that you're using. But yeah, ground-based observations are super important, but so are satellite observations, and they give us really complementary information about how the system is changing.
Totally. And then we had one follow-up question to that, and we've had kind of a lot of questions about this oops, sorry, I'm clicking all the wrong buttons. If there's any kind of citizen scientist work that, you'd encourage people to look for to kind of contribute to those sort of ground-based observations.
Yeah, I mean, the thing about going to the Arctic is that's an expensive place to go to do field work. You have to get on an icebreaker or a really nicely equipped ship if you want to be on the Arctic Ocean, or, go up to the North Shore of Alaska, all the way up there. It's a long ways. In terms of citizen science stuff, though, I mean, there's a lot that you can do just looking at what's going on up in the Arctic and talking about it with your neighbors and your friends. And, the MODIS satellite that I mentioned that has the satellite images of the Arctic, I check in on those almost daily. It's just beautiful to see what's going on up there. There's a bunch of smoke from the Canadian wildfires that are in the images from this week. You can see all the clouds, you can see Greenland, you can see the sea ice. It's just, it's a really interesting and fascinating region. And, something like Greenland melting affects the whole globe through, melting land ice and raising sea level. Sorry. Yeah.
I mean, I guess related to that, we're kind of, you spoke about this a little bit in the beginning of your talk, but someone's asking what's sort of the largest impact on ice loss? What are
Oh,
the
besides sea level rise.
Yeah.
Yeah, I mean, it's changing kind of the energy budget at the high latitudes, right? You know, because you have maybe an open ocean instead of an ice-covered ocean. So that does things like change temperature gradients on the planet, which are really important for driving the global circulation. So, you know, there's a lot going on that can happen in the Arctic, and maybe it's a little bit like Vegas. You know, what happens in Vegas, you know, should stay in Vegas, but doesn't always, you know, it's the same thing. In the Arctic, some things stay in the Arctic, but a lot of things make it to the lower latitudes too. So.
And you talked about, you know, getting seeing this postdoc application, but what kind of got you, even before that, what sort of led you into research? Is this sort of something you always wanted to do, or is there kind of an exciting moment?
Yeah, I mean, I love ice. Like I really, one of my favorite classes in grad school was called The Formation of Snow and Ice Masses. And I liked this class so much that I took it twice, which people are like, what are you doing? But I just, you know, the instructor, the professor he was riveting. And, you know, he was just at a chalkboard writing down equations about how glaciers work and how sea ice works. And I was like, whoa, you can write equations for how that works? Like math just got so much more exciting for me. So yeah, I think I really credit my time, you know, in grad school. I did a science undergraduate degree too, but I think I was really, really inspired to get into kind of ice research and, you know, polar research and climate research when I was in grad.
That's wonderful. That's good to know. We have another kind of fun sort of, if you had unlimited computing resources, you had every single supercomputer at your disposal, what kind of simulation would you run? And, you know, what kind of questions do you have?
Oh my gosh. So I'm such a fan of long runs, you know, and I mean like long climate modeling runs, but also I mean, I used to do a lot of running too. So I like long runs of many kinds. But yeah, I love these really long runs that really help you understand how the climate system is responding, and then also what the variability is, so that you can really kind of decompose what is actually variability and what is actually a response to a change that you've made to the model and the forcing. I think the Large Ensemble project, that project just opens so many eyes, including mine, about just how much variability there can be, but then also how consistent the response is to something like increasing CO2. You know, it's like you really start to see it emerge above that variability. And I think we're right at that point, you know, in those simulations. And so it's a really interesting time to be able to run more simulations and really try to understand the variability and understand the change too.
Yeah, definitely. I agree, especially because I feel like there's a little bit of a trend to sort of just do to 2050, just do to 2100. So getting to play around in those long runs, 2300, see what happens is very fun, although it does take a while to run.
Mackenzie said unlimited.
That's true. Yeah, no, I mean, especially if it could run it fast, then it would be perfect. And I guess sort of related to what you were saying earlier, Amanda C42, you kind of mentioned talking about this with your neighbor. How do you help them make that connection with the polar regions, especially for someone who's super far away from those sort of spaces?
Yeah, I mean, I think this idea that we're all connected, and so we're all experiencing the same forcing and the same changes, but that the Arctic is warming a lot more. And so this idea of like, why is it warming more? You know, what are the implications up there? You know, how is this affecting people up there? You know, I think in terms of calling a representative, you know, I think talking about how climate change is affecting you, or how weather forecasts affect you and your local situation, you know, I think that's also really, really important. So yeah, I think it's a good way to test our physical understanding, and obviously the sea level rise is something that affects, you know, lots and lots of people along coasts. There's a lot of people along the coasts.
Yeah, the vast majority of people live along the coast, so it's always going to be important. Now we're kind of jumping back and forth between ice and climate modeling, but how are you seeing AI impact climate modeling? We've had a few people come in and talk about how their work is working with AI and climate modeling, but if you could talk about that for those who were not able to see those talks.
Yeah, sure. I mean, I'm not doing a lot of AI myself, but I think, for example, this CESM large ensemble project that I mentioned, like, it took a lot of resources to do it. It, took over a year on one of the largest supercomputers on the planet to produce those simulations. But now those simulations are a benchmark for AI. So you could build, emulators to try to see if you can get some of the same physical processes, maybe make it a little bit less expensive to test some ideas in science. I think that's one thing, you do. It's nice to have the benchmark though. And so, yeah, I think there's a lot going on with AI, and I don't know if I can summarize it quickly here, but it's definitely changing how we're thinking about modeling.
Yeah. I mean, you pulled in so many different ideas. Like that's the only one you didn't include in your talk, so you got to touch on it in the Q&A. And then we get, I guess, kind of combining the two, ice and modeling. Have you looked at modeling ice on other planets, exoplanets? Played around with that at all?
I haven't, but I have a graduate student right now who's really excited about ice on other planets. So this is one of the wonderful things about being around such amazing, bright people. There's, always new questions being asked, and, not new questions to the whole science, but to me. And so you're always learning and trying to, improve your understanding. So I haven't, but I may start soon if one of my students is really excited about it.
That's wonderful. I mean, it's good that you're letting your students sort of explore all those different avenues, even if they're not what your areas of expertise is. I feel like that's a sign of a good advisor for sure.
Well, you need to match, scientific passion with scientific funding, right? Going to graduate school definitely requires funding. So bringing it back to a little bit why we're here. But also, that passion part is really important. And so, aligning what people want to do with funding I feel like that's one of my main jobs.
Yeah, and I guess kind of related to that, we have all these supercomputers, but getting time on those, is that funding normally coming from federal agencies? Is that kind of where your funding is coming from?
Yeah, the supercomputer that we use all of the time is the National Science Foundation, and it's used for all different kinds of scientific research, physics and biology. And so, yeah, I would say climate and weather forecasting, weather forecasting in particular is one of the big applications of supercomputing. And it has so much societal benefit, like people just look at their phones and they know what the weather is going to be. I mean, that's incredible. It's incredible. And people should not take that for granted.
No, definitely not. It's so important. And so much of how everything runs on a daily basis is based on all of that federal funding. So, anyway, I think that we have to reset the stream when your talk is done. And thank you so much for spending so much time with all of us. If you have a chance, we're going to reset it. You can go back to the end of the video and see all the comments of how much people really enjoyed being here. But thank you so much.
Thanks.
All right, all. So we got to reset the stream so that we can keep an archive of these videos and YouTube doesn't crash on us. So you can see the link right here below me. You got to go to wclivestream.com/watch once the stream ends. And we'll continue an amazing night full of climate science and meteorological talks for hours and hours and more. We still got 42 hours left. 41. It's about to be 41 in like 1 minute. So everyone prepare your URL writing so you can hop on over as soon as we end this thing. We know how many of you there are. We would like you to all keep watching. Thank you.